What if the solid ground beneath your feet, the warmth of the sun on your skin, and the very thoughts inside your head were not what they seem? What if reality itself is the greatest trick the universe has ever played on us? This isn't just a philosophical daydream. It's a question that has haunted the greatest minds for centuries, and it forces us to confront the deepest mystery of all. What is the true nature of reality? We live our lives assuming that our senses give us an accurate picture of the world, a straightforward broadcast of truth. But what if that broadcast is filled with static, edited, or is merely a shadow play on the wall of a cosmic cave? The very act of questioning reality pulls the rug out from under our everyday existence, opening up a dizzying abyss of possibilities that challenges everything we think we know. This journey we're beginning today is not for the faint of heart. It's an expedition to the very edges of human understanding, where physics blurs into philosophy and the line between science fiction and scientific fact becomes terrifyingly thin. We are about to embark on an exploration of 50 of the most groundbreaking, mind-bending, and utterly astonishing theories about what reality might actually be. From the ancient idea that our world is a mere illusion to the modern quantum theories that suggest particles exist in multiple states at once, we will traverse a landscape of ideas so vast and strange it will permanently alter your perspective. This is more than a list. It's a map of the greatest unsolved puzzle, a guide to the cosmos's best-kept secrets, and an invitation to look behind the curtain of existence itself. So prepare to have your mind stretched. We are going to question the fabric of space and time, entertain the possibility of countless parallel universes, and even consider that consciousness itself might be the fundamental ingredient of everything. Each theory we uncover is a piece of a grander puzzle, a different lens through which to view the incredible, bewildering, and beautiful cosmos we find ourselves in. This is a story about human curiosity at its most ambitious, our relentless drive to understand our place in the grand scheme of things. The answers we find may be unsettling, they may be awe-inspiring, but one thing is certain. By the end, the word reality will never feel quite the same again. But before we venture into the farthest reaches of cosmic speculation, let's begin with a theory that has captured the modern imagination like no other, one that feels ripped from the pages of science fiction yet is taken seriously by some of our leading thinkers. This is the simulation hypothesis, the provocative idea that everything we perceive as reality, the stars in the night sky, the history of our planet, and the very sense of your own self, is nothing more than an incredibly sophisticated computer simulation, akin to a hyper-realistic video game. In this view, we are not beings of flesh and blood in a physical universe, but rather complex strings of code running on the supercomputer of a vastly more advanced civilization, perhaps our own descendants in the far future. The argument was most famously formalized by the philosopher Nick Bostrom in 2003. He proposed a logical trilemma, suggesting that at least one of three propositions must be true. First, that virtually all civilizations like ours go extinct before reaching a level of technological maturity capable of creating such simulations. Second, that any civilization which does reach that stage would have absolutely zero interest in running simulations of its own ancestral past. Or third, that we are almost certainly living in a simulation right now. The logic is haunting because if you believe that a technologically mature civilization is possible, and that they might have even a slight curiosity about their history or the nature of consciousness, then the number of simulated realities they could create would be astronomically greater than the one base reality. Statistically, therefore, the odds are overwhelming that we are living in one of the countless simulations. Proponents of this idea point to certain quirks in our universe that resemble features of a constructed system. They ask, for instance, why does reality appear to be pixelated at the smallest scales? The Planck length, the smallest possible unit of distance in physics, could be seen as the fundamental resolution of the simulation. The strange, probabilistic rules of quantum mechanics, where particles exist in a haze of possibility until observed, might be explained as a processing-saving technique, a way for the cosmic computer to only render the fine details of reality when someone is actually looking. Even the speed of light, that ultimate cosmic speed limit, could be interpreted as the processor clock rate of the universe, preventing information from moving so fast that it crashes the system. Yet, the simulation hypothesis is not without its powerful critics. Some physicists argue that simulating every single particle in a universe down to the quantum level would require more computing power than could possibly exist, even for a super-advanced civilization. The energy requirements would be literally astronomical. Others point out that if our reality is a simulation, it contains an immense amount of seemingly useless information, like the precise position of every atom in a distant, uninhabited galaxy. Why would a programmer waste precious processing cycles on rendering details that no one will ever observe? Furthermore, the hypothesis leads to dizzying regress. If our post-human creators are running a simulation of us, who is to say that their reality isn't also a simulation, created by an even higher form of intelligence, leading to an infinite tower of simulations within simulations? Beyond the scientific arguments, the philosophical implications are profound. If this is a simulation, does our lives have any intrinsic meaning, or are we merely characters in someone else's story? Does the pain we feel or the love we experience carry any less weight if it is digitally constructed? Some find the idea terrifying, a form of cosmic nihilism. Others see a strange kind of hope, suggesting that if our reality is designed, then there might be a purpose behind it all, or even the possibility of an afterlife if the simulation is reset or archived. It forces us to confront the very nature of existence, blurring the line between creator and creation, and challenging us to define what, if anything, makes a reality real. But if we are living inside a grand simulation, how could we ever hope to detect it? Proponents of the hypothesis suggest we might look for what we could call glitches in the matrix, small anomalies or patterns in the fabric of reality that hint at an underlying code. One of the most compelling places to look is the quantum realm, where the behavior of particles is so utterly bizarre that it defies all our classical intuition. The famous double-slit experiment, for instance, shows that particles like electrons can behave as both particles and waves. Even stranger, they seem to know when they are being observed, changing their behavior accordingly. Could this wave function collapse be a form of rendering where the simulation only calculates a definite outcome when a conscious observer is present to witness it, a clever bit of programming to save on computational resources? The inherent uncertainty and probability baked into quantum mechanics might not be a fundamental feature of the universe, but rather a limitation of the processing power available to our cosmic computer. Beyond the lab, some point to peculiar psychological experiences as potential evidence. The sensation of déjà vu, that eerie feeling that you have lived through a moment before, could be interpreted as a minor timing glitch, a brief moment where data is accessed or repeated incorrectly. Mysterious coincidences or synchronicities that feel too perfect to be random might be signs of underlying algorithms at work, or perhaps even the subtle hand of a programmer. Even the Mandela effect, where large groups of people share a specific false memory, like remembering Nelson Mandela dying in prison in the 1980s, could be explained as a software update that wasn't perfectly applied across all instances of the simulation, leaving some with residual data from a previous version. Of course, neuroscientists and psychologists have more conventional explanations for these phenomena, but within the framework of the simulation hypothesis, they take on a far more intriguing character. The ethical and philosophical implications of discovering we are in a simulation are staggering. If we confirmed this theory, it would trigger the most profound identity crisis in human history. It would force us to ask, what is the moral status of a simulated being? Do our rights and our sufferings matter if we are just patterns of information? This question becomes even more pressing if we ourselves are on the verge of creating advanced artificial intelligence. If we are simulated, then our creation of simulated minds would mean we are building simulations within a simulation, raising nightmarish questions about our responsibility. Are we obligated to ensure the happiness of the consciousnesses we create? Or does our own potentially simulated nature absolve us of any real consequence? The discovery would also completely reshape our understanding of purpose and meaning. For some, it could lead to existential despair, a sense that nothing is real and therefore nothing truly matters. But another perspective is possible. If our reality is a simulation, it was created for a reason. Perhaps we are part of a historical archive, a scientific experiment to understand the rise of consciousness, or even a form of entertainment. This doesn't necessarily invalidate our experiences. The love we feel and the beauty we perceive are no less potent for being coded. In fact, it could imbue our lives with a new kind of meaning, as if we are participants in a grand cosmic story. It challenges us to consider that the purpose of life might not be to uncover some external truth, but to live our narrative as fully and authentically as possible, regardless of the medium. The ultimate rebellion against our programmers might not be to escape the simulation, but to live so meaningfully that we transcend its intended design. While the simulation hypothesis asks if we live in a digital construct, another theory emerging from the forefront of physics presents an even stranger picture of reality, one where the entire universe might be a cosmic mirage. This is the holographic principle, an idea so revolutionary it suggests that the solid, three-dimensional world we experience is nothing more than a projection, a hologram emanating from a flat, two-dimensional surface at the edge of the known universe. Just like a credit card hologram that creates a seemingly three-dimensional image from a two-dimensional film, our reality, with all its depth and richness, could be a vast and incredibly complex illusion. The seeds of this mind-bending concept were planted not in the study of illusions, but in the most enigmatic objects in the cosmos, black holes. In the 1970s, physicist Jacob Bekenstein made a startling discovery. He realized that a black hole's entropy, which is a measure of the disorder or information content within a system, is not proportional to its volume as one might expect for a three-dimensional object. Instead, it is proportional to the surface area of its event horizon, the point of no return. This was a profound clue. It suggested that all the information about everything that ever fell into the black hole, every star, every planet, every book ever written, could be encoded on the two-dimensional boundary of the hole itself, not stored within its vast interior. Stephen Hawking later built on this, showing that black holes slowly radiate energy and evaporate over time, raising a terrifying paradox. If a black hole evaporates, what happens to all that information? The laws of quantum mechanics state that information can never be truly destroyed. The holographic principle offered an elegant solution. The information isn't lost because it was never truly inside the black hole to begin with. It was always stored on the surface like a cosmic hard drive and is slowly released back into the universe as the black hole fades away. This connection between a volume of space and its bounding surface was a seismic shift in physics. In the mid-1990s, physicists Gerard T. Hooft and Leonard Susskind took this idea and extended it to the entire universe. They proposed that the holographic principle might be a fundamental property of reality. Our three-dimensional cosmos, with its galaxies, stars, and people, could be a projection from a two-dimensional surface at the farthest reaches of space. Every event that happens here, every particle interaction, is simply a reflection of processes taking place on this distant, flat boundary. To grasp this, think of watching a high-definition movie on a screen. The image appears to have depth and movement, but all the information needed to create that illusion is encoded in the two-dimensional pixels of the screen. In the same way, the holographic principle suggests that our brains are decoding a three-dimensional experience from a two-dimensional source of information. String theory, the ambitious attempt to unify all forces of nature, provides a mathematical framework for this idea. In certain models of string theory, a universe with gravity in three spatial dimensions can be perfectly described by a quantum field theory without gravity operating on its two-dimensional boundary. This is known as the AD/CFT correspondence, and it is a concrete, mathematically sound realization of the holographic principle. It's as if the entire universe is being described by a simpler, flatland physics operating on a giant sphere surrounding us. This doesn't mean the third dimension is an illusion in the sense that it doesn't exist. It exists in the same way a holographic image exists. It's real to us, the observers within the system, but its fundamental origins are flatter and stranger than we ever imagined. The implications of this are staggering. If the holographic principle is correct, it would mean that the universe has a finite amount of information, much like a computer hard drive has a maximum storage capacity. There is a fundamental limit to how much information can be contained in any given region of space, and it's determined by the area of its boundary, not its volume. This resolves another deep paradox in physics and suggests that reality at its most basic level is not smooth and continuous, but is instead pixelated, composed of tiny, indivisible units of space and time, often called Planck pixels. The smooth continuity we experience would then be an emergent property, just as a digital photograph appears smooth from a distance even though it's made of distinct pixels. But how could we ever test such an extraordinary claim? Scientists are looking for evidence in the fabric of spacetime itself. Just as a hologram can become blurry or grainy if you look too closely, some researchers believe that if we could probe reality at the smallest possible scales, we might detect a fundamental fuzziness or noise, a hallmark of the underlying pixelation. Experiments using incredibly precise laser interferometers, like those used to detect gravitational waves, are searching for this very holographic noise. While no definitive proof has been found yet, the very possibility that we could conduct an experiment to see if the universe is a hologram shows how far this idea has moved from pure speculation to a serious scientific frontier. The holographic principle forces a complete re-evaluation of what is real. It tells us that the world of appearances, the world of tangible objects and vast distances, is a magnificent and convincing illusion. The true reality, the source code of the universe, exists on a distant, two-dimensional surface we can never see or touch. It elegantly weaves together the physics of the very large black holes and cosmology with the physics of the very small quantum mechanics and information theory. In doing so, it doesn't just offer a new theory of reality, it offers a new way of seeing our place within it, suggesting that the deepest truths about existence are written not in the world around us, but on the cosmic horizon that contains it. This idea that our universe might be a projection or a simulation pushes the boundaries of what we consider possible, but it still operates within a single cosmic framework. What if the truth is even more expansive? What if our universe isn't alone, but is just one page in an infinite book of realities? This brings us to the multiverse theory, a concept that proposes the existence of countless parallel universes, each with its own unique history, laws of physics, and perhaps even versions of you. This isn't a single idea, but a family of theories emerging from different branches of physics, all pointing toward the same staggering conclusion, that everything that can happen does happen somewhere. The first and perhaps most famous version comes from the strange world of quantum mechanics. In the 1950s, a young physicist named Hugh Everett Roman III proposed a radical solution to one of quantum theory's biggest puzzles, the nature of observation. In the classic Copenhagen interpretation, a particle exists in a blurry state of all possible states, called a superposition, until it is measured, at which point it randomly chooses a single definite state. Everett found this unsatisfactory. Why should the act of observation have such a special, magical power? His many worlds interpretation offered a breathtaking alternative. He suggested that the wave function, which describes all the possibilities, never actually collapses. Instead, every time a quantum event has multiple possible outcomes, the entire universe splits into branches, each one realizing a different possibility. In one branch, a radioactive atom decays and a cat in a box dies. In another, equally real branch, the atom does not decay and the cat lives. There is no single outcome, there are only all outcomes, each playing out in its own newly created universe. In this view, every decision you've ever made, from what you had for breakfast to the life path you chose, has a counterpart in another world where you made a different choice, creating a mind-bogglingly vast tree of alternate histories. A second, equally compelling version of the multiverse arises from cosmology and the theory of cosmic inflation. This theory describes a moment of exponential expansion in the universe's first fraction of a second. But many physicists, like Andre Lind, suggest that this inflation isn't a one-time event that started and stopped. Instead, it may be eternal. Picture an endlessly bubbling cosmic cauldron of space-time. In most of this froth, inflation ends, allowing a stable universe like ours to form, a single bubble in a vast foam. But in other regions, inflation continues forever, constantly giving birth to new bubble universes. Each of these bubbles could have different fundamental constants and physical laws. In our bubble, the strength of gravity and the mass of an electron are fixed, allowing for stars, planets, and life. But in another bubble, gravity might be stronger, causing universes to collapse instantly, or the nuclear forces might be weaker, preventing atoms from ever forming. We simply live in one of the rare bubbles where the numbers are just right for us to exist, a concept known as the anthropic principle. A third profound source for the multiverse comes from string theory, the leading candidate for a theory of everything. To be mathematically consistent, string theory requires more than the 3 spatial dimensions we experience. It suggests there are actually 10 or 11 dimensions, with the extra ones curled up into shapes too small for us to perceive. The specific way these dimensions are curled or compactified determines the laws of physics in that universe. The problem is, the number of possible ways to curl these dimensions is astronomically large, perhaps around 10 to the power of 500. This is the string theory landscape, a vast ensemble of possible universes, each with its own unique physics. Just as the eternal inflation scenario suggests, we may inhabit just one of these possible universes in a wider multiverse, a single planet in a cosmic archipelago whose full diversity is beyond our comprehension. The implications of any multiverse theory are as profound as they are unsettling. It suggests that every tragedy, every missed opportunity, and every historical catastrophe has been avoided or resolved happily in some other branch of reality. It can feel liberating, diminishing the weight of our choices, or it can feel nihilistic, suggesting that our lives are just one random draw from an infinite deck of possibilities. For scientists, the multiverse presents a challenge. If these other universes are forever beyond our observational reach, can the idea even be considered science? Proponents argue that the theories that predict a multiverse, like inflation and quantum mechanics, have independent evidence, and the multiverse is a natural consequence. They also suggest we might find indirect evidence, like a strange pattern in the cosmic microwave background radiation caused by our bubble universe colliding with another in the distant past. Ultimately, the multiverse theory forces us to confront the sheer scale of existence. Our universe, with its hundreds of billions of galaxies, may be unimaginably vast to us, but it could be an infinitesimal speck in a much grander, perhaps infinite meta-universe. It redefines our place in the cosmos, not as the center of a single creation, but as one thread in an infinite tapestry of realities, each weaving its own unique story. While the multiverse paints a picture of infinite possibilities spread across a cosmic landscape, a far older theory suggests that the true nature of reality isn't about quantity, but about quality. Long before supercomputers or quantum physics, the ancient Greek philosopher Plato was already proposing that our everyday world is a profound and convincing illusion. His theory of forms, articulated over 2,000 years ago, remains one of the most enduring and influential ideas about what is truly real, a philosophical cornerstone that still resonates with modern scientific thought. To understand Plato's radical proposition, we must step inside his famous allegory of the cave. Imagine a group of people who have lived their entire lives chained deep inside a cavern facing a blank wall. Behind them, a fire burns, and between the fire and the prisoners, people carry various objects, casting shadows onto the wall in front of the captives. For these prisoners, these shadows are reality. They name them, discuss them, and believe them to be the entirety of existence. They have no conception of the three-dimensional objects behind them, let alone the fire that is the source of the light or the world outside the cave. Plato suggests that we are those prisoners. The world we perceive through our senses, the trees, the animals, the chairs we sit on, are merely the flickering shadows. They are imperfect, transient copies of something far more real. What then is casting these shadows? Plato argues that beyond our physical world lies a transcendent realm of perfect, eternal, and unchanging essences that he calls forms. These are the ideal blueprints. Take the concept of a circle. In our world, you can draw a circle, but it will never be perfect. Under a microscope, the line will be jagged, it will be slightly lopsided. Yet, we all possess the idea of a perfect circle, a set of points equidistant from a single center. That perfect circle, according to Plato, is the real one. It exists in the realm of forms. The same is true for abstract concepts like justice, beauty, or equality. Every just act we witness in our world is an imperfect, shadowy reflection of the perfect, eternal form of justice itself. Our world is one of becoming, of constant change and decay, while the realm of forms is one of pure being, timeless and absolute. This idea might seem like a purely metaphysical curiosity, but it finds a startling echo in the language of modern science, particularly in mathematics. Many mathematicians and physicists are what is known as mathematical Platonists. They don't believe that mathematicians invent mathematical truths, they believe they discover them. The number pi, the ratio of a circle's circumference to its diameter, is not a human convention. It is a constant that appears throughout the universe in the structure of distant galaxies and the vibrations of atoms. A mathematical Platonist would argue that pi, along with the entire intricate landscape of mathematics, prime numbers, geometric theorems, and complex equations, exists independently of human minds in a timeless, non-physical realm that is astonishingly similar to Plato's world of forms. When a mathematician proves a theorem, they are not creating something new. They are uncovering a truth that has always been true, much like an explorer mapping a pre-existing continent. The connection deepens when we consider the unreasonable effectiveness of mathematics, a phrase coined by physicist Eugene Wigner. Why is it that a system of logic and symbols dreamed up by humans, often with no practical application in mind, turns out to be the perfect tool for describing the fundamental laws of the physical universe? The equations James Clerk Maxwell wrote down in the 19th century perfectly predicted radio waves. The complex mathematics of Einstein's general relativity accurately describes the warping of space-time by gravity. If mathematics is just a human invention, this predictive power seems like a miraculous coincidence. But if mathematics is a description of the eternal, objective forms that underpin reality, its effectiveness makes perfect sense. Physicists are, in essence, studying the shadows on the cave wall and using the relationships between those shadows to reverse engineer the nature of the perfect objects casting them. They are seeking the fundamental truths that exist beyond our flawed sensory experience. This quest for a deeper truth beyond appearances is the core legacy of Plato's theory. It validates the human intuition that there is an order to the cosmos, a set of fundamental principles that are more real than the chaotic flux of our daily lives. It suggests that true knowledge is not about accumulating sensory data, but about using our reason to grasp these underlying eternal realities. In this view, a scientist studying the law of gravity is not just measuring how fast apples fall. They are attempting to comprehend the form of gravitational attraction. A philosopher debating ethics is not just listing good deeds, they are straining to perceive the form of the good itself. Of course, Plato's theory of forms is not without its critics. The most immediate question is, where is this realm of forms? It is not a physical place in space and time. How do we, as imperfect beings trapped in a world of shadows, have any access to it? Plato's answer was that our souls, before being born into our bodies, existed in the realm of forms, and what we call learning is actually a process of recollection or anamnesis. When we recognize that two sticks are approximately equal in length, we are dimly remembering the perfect form of equality we once knew. This introduces a deeply mystical element that many modern thinkers find difficult to accept. Furthermore, the theory can lead to an infinite regress, often called the third man problem. If a man is a copy of the form of man, what is the relationship between the form of man and the form of itself? Does that require yet another higher form? Despite these challenges, the power of Plato's idea endures. It provides a profound framework for understanding the relationship between the messy, imperfect world we inhabit and the elegant, precise laws that seem to govern it. It elevates the pursuit of knowledge from a simple cataloging of experiences to a sacred journey toward absolute truth. In an age of quantum uncertainty and relativistic perspectives, the theory of forms offers a comforting, if demanding, vision that beneath the apparent chaos of existence lies a realm of perfect, timeless order, and that our highest calling as conscious beings is to turn away from the shadows on the wall and seek the luminous reality that casts them. Plato's world of perfect forms suggests a transcendent reality behind our own, but what if the very act of looking for that reality is the problem? What if our minds are not clear windows to the world, but rather active architects, constructing the world we perceive from the ground up? This brings us to a philosophical earthquake that reshaped Western thought, Immanuel Kant's transcendental idealism. In the late 18th century, Kant famously declared that he had staged a Copernican revolution in philosophy. Just as Copernicus realized the Earth revolves around the Sun, not the other way around, Kant argued that objective reality does not simply impose itself on our passive minds. Instead, our minds actively structure and shape all of our experiences. According to Kant, we can never know reality as it truly is in itself. We can only ever know reality as it appears to us, filtered through the built-in frameworks of our own consciousness. Kant was trying to solve a deep conflict between two dominant schools of thought, empiricism and rationalism. Empiricists like John Locke argued that all knowledge comes from sensory experience, that our mind is a blank slate, a tabula rasa, written upon by the world. Rationalists like René Descartes argued that true knowledge comes from reason and innate ideas. Kant saw flaws in both. If knowledge comes only from senses, how can we have certain universal knowledge like mathematics that holds true regardless of our individual experiences? And if we have innate ideas, how do we connect them to the real world? Kant's revolutionary synthesis was that while all our knowledge begins with experience, it is not solely derived from it. The raw data, the sensory input, comes from the world, but our minds come pre-equipped with a kind of operating system that organizes this chaotic data into a coherent experience. This operating system consists of what Kant called the forms of intuition and the categories of the understanding. The most fundamental frameworks are space and time. Kant argued that we cannot even conceive of an object that is not located somewhere in space or an event that does not occur in time. But here's the radical part. He proposed that space and time are not features of the external world. They are not a grand container that the universe sits inside. Instead, they are the necessary lenses through which we, as human observers, must perceive everything. They are the forms of our sensibility. The world may be very different in itself, but we are doomed to see it as a series of events unfolding in a temporal sequence within a three-dimensional spatial arena. It's as if we are born wearing rose-colored glasses permanently fused to our faces. We can never take them off to see what color the world really is. Beyond space and time, Kant identified 12 fundamental categories that our understanding uses to process the raw data of sensation into coherent thoughts. These include concepts like causality, substance, unity, and possibility. We don't learn the law of cause and effect by observing one billiard ball hit another over and over. According to Kant, our minds are hardwired to impose a causal relationship on events. We cannot experience the world except as a chain of causes and effects. When you see a baseball shatter a window, you don't merely see two separate events, a ball moving and then a window breaking. You immediately and necessarily perceive the first as causing the second. This structure is not out there in the world in itself. It is a rule of your own mental processing, a category you use to make sense of the flux of experience. This leads to Kant's most famous and profound distinction, the difference between the phenomenon and the noumenon. The phenomenal world is the world of appearances, the world we all experience and can talk about scientifically. It is the world of trees, rocks, stars, and other people. A world structured by our space, time, and categories. This world is real. It is objective in the sense that all humans with similar cognitive equipment will experience it in the same way. But behind this phenomenal world, Kant posits, lies the noumenal world, the world of things in themselves. This is reality utterly independent of our perception of it. And here is the crucial, mind-bending conclusion. The noumenal world is fundamentally unknowable to us. We can think about it, we can postulate its existence as the source of our sensations, but we can never have any direct knowledge of it. It is like a radio signal being broadcast. Our minds are the radio receivers that tune that signal into music and speech. We can study the music in great detail, but we can never know what the raw signal is like before our receiver decodes it. The thing in itself remains forever beyond the horizon of human knowledge. The implications of this are staggering for our quest to understand the nature of reality. It suggests that science, for all its power, is not describing the world as it is in itself. Science is describing the phenomenal world, the world as it appears to human observers using instruments that extend our innate categories. Physics brilliantly maps the laws of causality in space and time, but it cannot tell us what a photon or an electron is when it is not being measured, when it is a noumenon. This doesn't make science invalid, it simply redefines its domain. Science gives us an extraordinarily accurate and predictive map of the world of appearances, but the territory itself remains hidden. Kant's idealism is transcendental because it is concerned with the conditions for the possibility of experience itself. He asks, what must be true about our minds for us to have the consistent, shareable experiences that we do? This philosophy creates a fascinating bridge between subjective perception and objective reality. The world we experience is not a purely personal, subjective illusion. Because we all share the same fundamental cognitive architecture, the laws of our perception are universal. The categories of causality and substance apply to everyone. This is why we can have a shared public science. The world is objectively real for us as perceiving subjects. However, this objective reality is still transcendently ideal. It is dependent on the structures of a mind. If we encountered an alien intelligence with a completely different cognitive apparatus, their objective reality might be unrecognizable to us. They might not experience space or causality at all. Kant's work therefore places a permanent question mark over any claim to have finally grasped absolute, mind-independent reality. It humbles our knowledge while simultaneously explaining its power and consistency, a profound and enduring legacy that continues to challenge physicists and philosophers to this day. Yet, this radical rethinking of reality is not solely a product of Western philosophy. For over 2,000 years, Eastern traditions have been exploring a conception of existence that is, in many ways, even more profound and challenging. We arrive now at the Buddhist concept of sunyata, most accurately translated as emptiness. This is not a nihilistic emptiness, a void of nothingness as we might imagine a dark, empty space. Instead, sunyata points to a revolutionary idea that all things without exception are empty of a permanent, independent, and self-contained essence. Nothing exists on its own. Everything is what it is only because of its relationship to everything else. To grasp this, we must understand its counterpart, the concept of svabhava, or inherent existence. Our default way of seeing the world, deeply ingrained in Western thought, is to perceive objects as having their own intrinsic nature. We look at a table and believe it possesses an essential tableness within itself. We see ourselves as having a solid, continuous self, an I that exists independently from the world around it. Buddhism argues that this perception is the root of our suffering. It is a fundamental misperception of reality. Sunyata is the deep truth that shatters this illusion. The table is not a truly independent entity. It is a temporary assembly of wood, which itself is a collection of cells, which are composed of molecules, which are made of atoms, which are mostly empty space buzzing with energy. The table's existence is wholly dependent on the tree it came from, the carpenter who built it, the nails holding it together, and the room it occupies. It has no separate, standalone reality. The mechanism through which this emptiness manifests is called pratityasamutpada, or dependent origination. This is the profound Buddhist law of causality, which states that all phenomena arise together in a mutually interdependent web of cause and effect. A simple way to visualize this is to think of a net of jewels, where each jewel reflects every other jewel in the net. There is no single source of light. Each jewel's brilliance is entirely dependent on the reflection of all the others. In the same way, you are who you are because of your parents, your culture, the food you eat, the air you breathe, and every interaction you've ever had. Your self is not a static thing but a dynamic, ever-changing process, a fleeting pattern in the vast flow of existence. To believe in a permanent, isolated self is like believing a single wave in the ocean is a separate entity from the water that forms it and the energy that moves it. This view presents a dramatic challenge to the substance-based metaphysics that has dominated Western philosophy since the ancient Greeks. Thinkers like Aristotle searched for the underlying substance, the unchanging essence that defines what a thing is. Buddhism, in contrast, argues there is no underlying substance to find. Reality is not made of static nouns but of dynamic verbs. It is a continuous process of arising, interacting, and passing away. Where Western science might seek to break things down to their fundamental, independent particles, Sunyata suggests that such a search is ultimately futile because there are no truly independent particles to be found. Even the most elementary particles in quantum physics exist only in relation to other particles and fields, their properties defined by interaction and observation. This creates a fascinating resonance between an ancient spiritual insight and the forefront of modern physics. The most intimate and challenging application of sunyata is to our own sense of self, what Buddhism calls anatta, or no self. We cling to the idea of an enduring I, that is the thinker of our thoughts and the feeler of our feelings. But if we examine our experience closely, can we actually find this stable self? Our thoughts come and go unprompted. Our emotions rise and fall. The cells in our body are constantly being replaced. The person you were 10 years ago is, in a very real sense, not the same person you are today. The self is more like a flame than a stone. A flame appears to be a single, continuous entity, but it is actually a constant process of fuel being consumed and transformed. It depends entirely on the candle, the oxygen, and the spark that lit it. There is no flameness hidden inside the fire. Similarly, what we call the self is a convenient label for a constantly flowing aggregation of physical and mental processes: form, sensation, perception, mental formations, and consciousness, all of which are themselves empty of inherent existence. The philosophical implications of realizing Sunyata are transformative. It suggests that the fundamental problem of human existence is not sin or error, but ignorance, a deep-seated misunderstanding of how things really are. Our suffering, our anxiety, and our conflicts arise from clinging to things and identities we believe to be permanent and separate, when in truth they are transient and interconnected. The path to liberation, then, is not about building a better self or acquiring more possessions, but about seeing through the illusion of separateness. It is about waking up to the interdependent nature of all life. This does not lead to apathy or disengagement. On the contrary, understanding our profound interconnectedness fosters a powerful sense of compassion and responsibility. If your well-being is inextricably linked to my well-being, then harming you is ultimately harming a part of the whole to which I also belong. This perspective offers a unique insight into the nature of consciousness itself. From the view of Sunyata, consciousness is not a thing that we possess, but an event that arises. It is not a static container for experiences, but a dynamic process that co-arises with its object. There is no consciousness without something to be conscious of. This interdependence challenges the classical subject-object duality that is so foundational to Western thought. Instead of a solid I observing a separate external world, there is only a seamless, flowing interaction. The observer and the observed are two sides of the same coin, mutually defining each other in each moment of experience. In this light, the hard problem of consciousness, how subjective experience arises from physical matter, might be a false problem based on the mistaken assumption that mind and matter are two independent substances. Sunyata suggests they are empty, interdependent aspects of a single, unified reality, a concept that modern thinkers exploring panpsychism or non-dual awareness are only beginning to catch up with. If the world of Plato and Kant suggests reality is shaped by our perception, then quantum mechanics presents us with a laboratory where this philosophical speculation becomes a physical, measurable phenomenon. This brings us to a cornerstone of modern physics that directly challenges our classical intuition: the idea that at its most fundamental level, reality does not exist in a definite state until it is observed. This is the bizarre and beautiful world of quantum mechanics, and its implications are so profound they force us to reconsider the very act of being a witness to the universe. The story begins in the early 20th century when physicists probing the atom found that the familiar rules of Isaac Newton's physics simply broke down. They discovered that particles like electrons don't behave like tiny billiard balls with definite positions and speeds. Instead, they exist in a ghostly state of potentiality known as a superposition. This means that an electron is not simply here or there. Until measured, it has a probability of being in many different places at once. It's not that we don't know where it is, it's that it doesn't have a definite location. This fuzzy cloud of possibilities is described by what physicists call the wave function, a mathematical equation that encapsulates all the potential states of a particle. The predominant way of understanding this strangeness is the Copenhagen interpretation, championed by figures like Niels Bohr and Werner Heisenberg. This interpretation presents a dramatic division in the world. There is the quantum realm, where particles exist in superpositions governed by probabilities. And then there is the classical world of everyday objects, where things have definite properties. The crucial moment is the act of measurement. According to Copenhagen, when a measurement is made, the wave function collapses. The infinite possibilities vanish, and the particle snaps into a single, definite reality. It's as if the particle is asked a question, and only upon being asked does it decide on an answer. This transition from the possible to the actual is the infamous observer effect, and it places the act of observation at the very heart of reality creation. To highlight how bizarre this idea is, physicist Erwin Schrödinger devised a famous thought experiment in 1935, now known as Schrödinger's cat. Imagine a cat sealed inside a steel chamber. Alongside the cat is a tiny, radioactive atom, a Geiger counter, a hammer, and a vial of poison. The experiment is set up so that if the radioactive atom decays, the Geiger counter will detect it, trigger the hammer to break the vial, and release the poison, killing the cat. According to the rules of quantum mechanics, the radioactive atom is in a superposition. It has both decayed and not decayed. But since the fate of the cat is tied directly to the state of the atom, the Copenhagen interpretation suggests that the cat itself must also be in a superposition. It is simultaneously alive and dead, a gruesome blend of both states, until someone opens the box and looks inside. The act of observation is what forces the system to choose a living cat or a dead one. Schrödinger intended this as a criticism, to show how absurd it was to apply quantum weirdness to the everyday world. But the paradox has endured as a powerful illustration of the measurement problem. This immediately raises a profound and unsettling question. What exactly counts as an observer that can collapse the wave function? Is it a conscious human being? A cat, a Geiger counter, the photons bouncing off the object. This is where the frontier of physics bleeds into the philosophy of mind. Some interpretations, like the one put forward by Nobel laureate Eugene Wigner, seriously entertain the idea that consciousness itself is the ultimate catalyst. Wigner suggested that a measuring device, like the Geiger counter in the box, could become entangled with the quantum system, entering a superposition itself. Only when the information from that device registers in the consciousness of a person does the entire wave function finally collapse into a single reality. In this view, consciousness is not a passive byproduct of the brain, but an active participant in shaping the physical world. However, the majority of physicists today find the consciousness-centric view problematic. It seems to grant a special, almost magical status to conscious beings, creating an awkward divide between animate and inanimate observers. A more common view is that a measurement occurs through a process called decoherence. This is when a fragile quantum system interacts with its environment, even a single photon of light or a molecule of air. This interaction is like a leak of information. The quantum superposition becomes entangled with the vast number of particles in the environment, and this entanglement effectively destroys the delicate superposition, making it appear as if a collapse has occurred. In the case of Schrödinger's cat, the moment the radioactive atom interacts with the Geiger counter, decoherence would occur, settling the outcome long before a human ever opens the box. The cat, being a large, complex object constantly interacting with its environment, would never truly be in a superposition of alive and dead. Yet, even with decoherence, a deep mystery remains. Decoherence explains why we don't see quantum superpositions in the large-scale world, but it doesn't fully solve the measurement problem. It explains how the appearance of a definite outcome arises for all practical purposes, but it doesn't specify why one particular outcome happens instead of another. The underlying quantum reality, according to the equations, still contains all possibilities. This has led to other interpretations, like the many worlds theory we discussed earlier, which avoids collapse altogether by suggesting that every possible outcome actually happens in a branching multiverse. The Copenhagen interpretation, with its mysterious collapse, remains a pragmatic tool for making predictions, but it leaves us with an unresolved enigma about the relationship between the observer and the observed. The implications of the observer effect ripple far beyond the physics lab, touching on the deepest questions about our place in the cosmos. It suggests that we are not merely passive spectators watching a pre-recorded cosmic film. We are active participants, and the very questions we choose to ask of nature influence the answers we receive. The universe seems to require a conversation, a dialogue between the potential and the actual. This doesn't mean we can simply wish reality into being with our thoughts, but it does imply that the classical ideal of a completely objective, detached observation is an illusion. The physicist John Wheeler captured this beautifully with his concept of a participatory universe. He envisioned reality as a vast game of 20 questions, where the universe answers our questions in a way that is consistent with the history we have helped to create through our previous inquiries. In this view, the universe becomes a co-creation, a cosmic dance between what is possible and what is witnessed, a story that has no meaning without someone to read it. This idea that our observation might play a role in shaping reality is a dizzying departure from the common-sense view of a world ticking along independently of us. But what if our most fundamental intuition, the steady, relentless flow of time from past to present to future, is itself the grandest illusion of all? This brings us to a theory that emerges directly from the bedrock of modern physics, one that paints a picture of reality so still and complete it can feel both awe-inspiring and deeply unsettling. This is the block universe theory, a concept that proposes that past, present, and future are not sequential moments but exist together, eternally and simultaneously, in a single, frozen, four-dimensional structure. The seeds of this radical idea are found in Albert Einstein's theory of special relativity. Before Einstein, time was considered absolute, a universal clock ticking at the same rate for everyone, everywhere. But Einstein showed that this simply isn't true. The rate at which time passes is relative. It depends on your speed and the strength of the gravitational field you're in. If one twin rockets away from Earth at near the speed of light and then returns, she will be younger than her stay-at-home sibling. Her clock literally ticked more slowly. This is not a theoretical curiosity. It is a measured fact essential for the GPS satellites that guide our cars. Relativity fused the three dimensions of space with the one dimension of time into a single, inseparable fabric, space-time. In this four-dimensional continuum, every event, your birth, the fall of the Roman Empire, the light from a distant star reaching your eye, has a unique set of space-time coordinates. From this perspective, the block universe theory suggests that this entire four-dimensional space-time manifold simply is. It is a fixed, unchanging structure, much like a loaf of bread. Slicing the loaf one way gives you a particular moment in time, a three-dimensional now that includes everything in the universe at that instant, but the entire loaf from end to end exists all at once. In this block, the past is not gone. It is simply a different region of the space-time loaf. The future is not unborn. It is another region already laid out. Your childhood, your life today, and your eventual death are all equally real, permanent parts of this cosmic tapestry. The feeling that time is flowing is just that, a feeling, a subjective experience of consciousness moving along the timeline, like a spotlight scanning across the frames of a film reel. The reel itself, containing all the frames, exists completely and eternally. This view is powerfully supported by the relativity of simultaneity. Einstein demonstrated that there is no universal now. Two events that are simultaneous for one observer may happen at different times for another observer moving at a different speed. Imagine two flashes of light occurring at either end of a moving spaceship. For an astronaut inside the ship, positioned exactly in the middle, The flashes arrive at the same time, they are simultaneous. But for an observer on a nearby planet watching the ship zoom by, the flash from the front of the ship will be seen before the flash from the back, because the ship is moving toward the light from the front and away from the light from the back. Which observer is correct about which event happened first? Relativity tells us they both are. There is no privileged frame of reference to define a single, objective present moment for the entire universe. This makes the idea of a moving, universal now scientifically untenable. If the present is not an objective feature of reality, then the past and future must be just as real. The implications for our understanding of change are profound. In the block universe, nothing ever truly changes. Change, as we perceive it, is an illusion. A tree is not a sapling that changes into a mature tree and then decays. In the four-dimensional block, the sapling, the mature tree, and the rotting log are all equally real, each occupying a different location along the timeline. They are different temporal parts of the same four-dimensional object, just as the trunk, branches, and leaves are different spatial parts of the tree at a single moment. The universe doesn't become, it just is in its full four-dimensional glory. This can feel like a sterile, almost lifeless view of reality, stripping away the dynamism and process that seems so central to our existence. This leads directly to one of the most contentious philosophical debates, the fate of free will. If the future is already written into the fabric of space-time, fixed and unchangeable like the past, then what becomes of our choices? This is a modern version of determinism, often called eternalism. It suggests that every decision you will ever make is already a part of the block, as predetermined as the orbits of the planets. You have the illusion of choosing, but the path is already laid out. This is a formidable challenge to our sense of agency. However, some philosophers and physicists offer a different perspective. They argue that free will and the block universe are not necessarily incompatible. Your conscious deliberation is itself a process that is encoded within the block. The complex chain of cause and effect that leads to your decisions, your thoughts, your desires, your reasoning, is all part of the four-dimensional structure. In this view, you are free to act according to your nature, but your nature is a fixed part of the cosmic story. Your life is not a script you are forced to read. It is a novel that has already been written, but one in which you are the authentic author of your actions, your choices woven into the very plot of the universe. Ultimately, the block universe theory presents a majestic, if disorienting, vision of reality. It asks us to trade our visceral experience of a flowing, dynamic present for a God's eye view of eternity. It can feel impersonal, reducing our vibrant lives to mere static patterns in a frozen landscape. Yet it also offers a strange kind of comfort. In the block, nothing is ever truly lost. Every moment of joy, every great achievement, every act of love exists forever, etched into the fundamental structure of space-time. It suggests that our lives are not fleeting sparks in the darkness, but permanent threads in an immense and beautiful tapestry. While we may experience our journey one moment at a time, the entire path is real, and in a profound sense, the entire story is always there, waiting to be discovered. The block universe theory presents a reality that is cold, fixed, and complete, a four-dimensional sculpture where our conscious experience is merely a flickering light moving along a predetermined track. But this immediately raises a profound question that physics alone cannot answer. What is the nature of this light? What is consciousness itself, and how does it emerge from the silent, apparently mindless dance of particles? For centuries, the prevailing scientific view has been that consciousness is an emergent property, a complex software that miraculously boots up when the hardware of the brain reaches a certain level of sophistication. Yet, this view runs headlong into what philosopher David Chalmers famously termed the hard problem of consciousness. It's one thing to explain how the brain processes information, integrates sensory data, and controls behavior. These are the easy problems. The hard problem is explaining why and how any of this physical activity should give rise to subjective, qualitative experience at all. Why do we feel the searing red of a sunset, the ache of sadness, or the sweetness of sugar? Why isn't all this neural computation just happening in the dark without an inner witness? This is where we encounter a theory that turns the standard materialist story on its head. It's called panpsychism, and it proposes a truly radical solution to the hard problem. The word itself comes from the Greek pan, meaning all, and psyche, meaning soul or mind. Panpsychism suggests that consciousness is not a latecomer in the universe, a rare and mysterious product of complex brains. Instead, it posits that consciousness, or at least some primitive form of experience, is a fundamental and ubiquitous feature of the cosmos, as basic as space, time, and matter. In this view, the fundamental constituents of reality, perhaps electrons and quarks, possess an incredibly simple form of inner life. They don't have thoughts or emotions, of course, but they might have some minute, elemental capacity for experience. The consciousness we enjoy is then not something that magically appears from non-conscious stuff. It is what happens when these countless tiny conscious entities combine in the extraordinarily complex structure of a brain. Modern proponents of panpsychism, like the philosopher Galen Strawson, argue that this view is actually more scientifically rigorous than the standard alternative. Strawson, a staunch materialist, insists that he believes consciousness is entirely physical, but he argues that if you truly take materialism seriously, you must conclude that consciousness is fundamental. His logic is powerful. We know for an absolute fact that consciousness exists. We also know that at some point in the history of the universe, it arose from a purely physical system. If you rule out magical emergence, the idea that consciousness just pops into existence from entirely non-conscious matter, which he compares to claiming that cheese could spontaneously pop out of a completely cheese-less universe, then the only coherent conclusion is that the potential for consciousness was always there, inherent in the physical stuff itself. Therefore, the physical must have some intrinsic experiential nature. As Strawson puts it, there must be something that it is like to be an electron, however unimaginably simple and foreign that experience might be to us. This idea elegantly dissolves the hard problem. The problem exists because we start with a universe of utterly mindless matter, and then scratch our heads wondering how mind could possibly arise from it. Panpsychism simply removes this gap at the outset. There is no gap to bridge because mind and matter are two aspects of the same fundamental reality. This is not a form of dualism which posits two separate substances. It's a kind of monism where the stuff of the universe has both an outward-facing physical aspect, which we can measure and observe, and an inward-facing experiential aspect, which is its intrinsic nature. The physicist Arthur Eddington hinted at this when he said that the stuff of the world is mind stuff. We are not asking how mind comes from matter. We are recognizing that what we call matter already has a mental pole. The implications of this shift in perspective are staggering. It suggests that the universe is not a vast, empty, mechanical clockwork, but is instead inherently experiential, throbbing with a dim, distributed form of sentience. A rock, for instance, would not be conscious in any meaningful way we'd recognize. The simple experiences of its individual atoms would be so isolated and unintegrated that they wouldn't add up to a unified rock consciousness. But in a system like a brain, with its trillions of neurons connected in an intricate network, these micro-level experiences could combine and unify, giving rise to the rich, complex stream of consciousness that you and I enjoy. This process of combination is a major challenge for panpsychism. It's known as the combination problem. How do lots of little bits of experience merge into one big, unified experience? But panpsychists argue this is a more tractable problem than the seemingly impossible task of getting experience from no experience at all. If panpsychism is correct, it forces a complete re-evaluation of our place in the cosmos. It suggests a deep continuity between ourselves and the rest of nature. We are not conscious beings in an unconscious world. We are intensely conscious gatherings of universally conscious stuff. This view can foster a profound sense of connection and even reverence for the universe. It also has fascinating implications for artificial intelligence. If consciousness is a fundamental property, then it's at least conceivable that a sufficiently complex and integrated computer system could also give rise to a conscious mind, not because we programmed it to mimic one, but because we have arranged matter in a way that allows its intrinsic conscious nature to express itself more fully. Panpsychism doesn't provide easy answers, but it reframes the most intimate mystery of our existence, the nature of our own awareness, placing it at the very heart of reality's architecture. If the block universe gives us a frozen sculpture of reality and panpsychism suggests a universe brimming with inner life, then the next theory we encounter presents perhaps the most austere and intellectually pure vision of all. This is the mathematical universe hypothesis, championed by physicist Max Tegmark, which proposes a breathtakingly simple yet radical idea. Our physical reality isn't just described by mathematics, it is mathematics. In this view, the universe and everything in it is not merely running on mathematical laws like a computer following code. Instead, the universe is itself a mathematical structure, and we are self-aware patterns within that abstract, formal system. To grasp the full force of this hypothesis, we first need to confront the unreasonable effectiveness of mathematics that we touched on with Plato. Why does math work so stunningly well? Tegmark pushes this question to its ultimate conclusion. He argues that the reason abstract mathematical equations can predict the behavior of quarks and galaxies with such precision is because those quarks and galaxies are, at their most fundamental level, mathematical objects. Think of a perfect circle. It's an abstract concept defined by a set of mathematical rules. Now, imagine a more complex mathematical object like a torus, a donut shape defined by its own set of equations. Tegmark's hypothesis suggests that our entire universe is akin to that torus, but infinitely more complex. It is a specific, self-consistent mathematical structure, and what we perceive as physical laws are simply the inherent properties of that structure. The force of gravity isn't a physical force pushing things together. It is a geometric property of the four-dimensional mathematical manifold we call space-time. Just as the angles of a triangle add up to 180 degrees because that is a property of Euclidean geometry. This leads to a profound distinction about the nature of existence. We typically think of the physical world as real and the mathematical world as an abstract human invention we use to describe it. Tegmark inverts this relationship. For him, the mathematical structure has primary existence. It is real and objective, existing independently in what he calls the universe of mathematical structures. Our physical world is then a subset of this Platonic realm. It is the particular mathematical structure that has the property of containing self-aware substructures, which are us. We are patterns of information, complex computations happening within the cosmic equation. Your conscious experience of reading these words is the physical manifestation of a specific, incredibly intricate mathematical state within the grand structure. This perspective forces a dramatic shift in the age-old debate of whether mathematics is discovered or invented. The inventor position holds that mathematics is a human creation, a useful language and logical tool we've developed like the rules of chess. The discoverer position, which aligns with mathematical Platonism, argues that mathematicians are explorers uncovering eternal truths that exist independently of minds. Tegmark's hypothesis is the ultimate form of Platonism. If our universe is a mathematical structure, then every mathematical truth that is consistent within that structure is a truth about our physical reality, whether any human has discovered it or not. Before any physicist ever wrote down the equations, the laws of general relativity were already true properties of our universe's mathematical structure. We are not inventing the rules of the game. We are slowly and painstakingly learning the rules of the game that has always been. The implications of this are as expansive as they are strange. One immediate consequence is that it potentially resolves the mystery of why the universe seems so fine-tuned for life. The constants of nature, like the strength of gravity or the mass of an electron, appear to be exquisitely balanced to allow for stars, planets, and ultimately us. From a traditional perspective, this seems like an incredible coincidence. But if the mathematical universe hypothesis is correct, then every possible mathematical structure exists somewhere in the Platonic realm. Most of these structures would be barren and simple, incapable of supporting any form of complex, self-aware life. We, of course, find ourselves in one of the rare, complex structures that can contain us. This is a form of the anthropic principle applied to mathematics. We shouldn't be surprised to find ourselves in a mathematical structure that has the property of allowing our existence. This idea also dovetails with the multiverse concept, but in a uniquely abstract way. Tegmark's hypothesis suggests there isn't just one mathematical universe, but a vast ensemble of all possible mathematical structures, a level Roman IV multiverse. This is the ultimate multiverse beyond the many worlds of quantum mechanics or the bubble universes of inflation. In this plenitude of existence, every consistent set of mathematical axioms gives rise to a universe that is just as real as our own. There is a universe that corresponds to the rules of Euclidean geometry, another that corresponds to a different set of differential equations, and countless others based on mathematical systems we haven't even conceived of yet. Our home universe is simply one entry in an infinite library of mathematical realities. Yet, for all its elegant simplicity, the mathematical universe hypothesis faces significant challenges. The most pressing is what Tegmark himself calls the reality problem. If the universe is purely mathematical, what gives it the familiar qualities of substance, of feel, of what philosophers call qualia? Why does a mathematical structure described by the Schrödinger equation have the property of producing the subjective, vivid experience of the color red or the sensation of pain? This is the hard problem of consciousness re-emerging in a new form. If we are just self-aware patterns, how does the pattern itself generate inner experience? The hypothesis seems to provide a perfect description of the objective, external world, but leaves the mystery of subjective consciousness untouched. Another criticism is that the hypothesis might be untestable and therefore not even scientific. If every possible universe exists, then any observation we make is automatically consistent with us living in one particular mathematical structure. How could we ever design an experiment to prove that other mathematical structures are real in the same way ours is? Proponents might argue that the incredible predictive power of mathematics is itself the evidence, but skeptics contend that this doesn't rule out the more conventional view that we are physical beings using a very effective tool to model a non-mathematical world. The hypothesis stands as a majestic, metaphysical endpoint for physics, a vision of ultimate simplicity that challenges us to consider that the deepest nature of reality might not be material or spiritual, but simply and beautifully mathematical. But if consciousness is indeed a fundamental feature of reality, as panpsychism suggests, then perhaps the most radical conclusion is that the entire physical world might be nothing more than a construct of mind. This brings us to a theory that pushes the notion of a mind-dependent reality to its absolute limit: idealism, and specifically, the provocative philosophy of Bishop George Berkeley known as immaterialism. In the early 18th century, Berkeley made a stunningly simple and elegant claim that cuts directly against our common-sense belief in a material world. His famous principle, esse est percipi, translates to be is to be perceived, For Berkeley, the table in front of you does not exist as a solid, independent object when you leave the room and no one is looking at it. Its existence consists entirely in its being perceived by a mind. Reality, he argued, is made up of only two things: minds, which are the perceivers, and ideas, which are the perceptions. Berkeley was reacting to the philosophical currents of his time, particularly the ideas of John Locke. Locke had proposed a distinction between primary qualities like shape and size, which he believed were objective properties of objects, and secondary qualities like color and taste, which existed only in the mind of the perceiver. Berkeley saw a fatal flaw in this division. He argued that you cannot actually separate the two. Try to conceive of an object that has a shape but no color. It's impossible. All qualities are experienced together as a bundle of perceptions. If secondary qualities are mind-dependent, then so too must be the primary qualities, because they are inextricably linked. An object's size is only known through our perception of it. Therefore, Berkeley concluded, the very idea of a material substance existing independently of perception is a meaningless abstraction. The so-called external world is just a stable, coherent, and orderly collection of ideas that are presented to our minds. The most immediate and obvious challenge to this idea is the one famously voiced by Samuel Johnson, who kicked a large stone and declared, "I refute it thus." The stone certainly feels solid and independent, but Berkeley had a ready answer for this. He did not deny the reality of the stone or the pain in Johnson's foot. He simply redefined what those things are. The solidity and pain are real ideas experienced by Johnson's mind. The stone's existence is its being perceived as hard and heavy. But what about when no human is around? Does the moon cease to exist when no one is looking at it? This is where Berkeley introduces a crucial component to his system: God. He proposed that an infinite, eternal mind, God, is constantly perceiving everything in the universe, thereby sustaining its existence even when finite human minds are not present. The orderly laws of nature are simply the consistent way in which God presents ideas to our minds. In this view, the universe is not a giant mechanism but a continuous divine communication, a language through which God speaks to created spirits. While Berkeley's appeal to God might seem like a theological leap to a modern audience, the core of his idealism has found surprising resonance in contemporary thought, particularly in the interpretation of quantum mechanics. The measurement problem, where a particle's properties seem to crystallize only upon observation, echoes Berkeley's premise in a startling way. The quantum world appears to exist in a state of pure potentiality, a haze of probabilities until an act of measurement. An interaction with a conscious observer or a measuring device forces it into a definite state. For some physicists, this suggests that the observer is not separate from the system, but is intimately involved in its very definition. While most physicists stop short of saying particles don't exist when not measured, the parallel is intriguing. The quantum world behaves as if to be is to be measured, a formulation that would have felt very familiar to Bishop Berkeley. The rise of virtual and augmented reality technologies provides another powerful, tangible analogy for idealism. When you put on a VR headset, you are immersed in a world that is entirely constructed from information. The mountains, the buildings, the other characters, they have no physical substance. Their entire reality consists in being rendered for your perception. If the headset were to malfunction, that world would cease to exist for you, even though the code that defines it remains on a server. From within the simulation, however, the world feels utterly real and governed by consistent rules. Berkeley's universe can be thought of as a perfectly consistent and immersive divine virtual reality. The laws of physics are the game engine's code, and our sensory experiences are the graphics and sounds being rendered for our conscious awareness. We are, in a sense, players in a reality whose entire substance is perceptual. This perspective forces a profound re-evaluation of what we mean by real. Idealism doesn't claim that the world is an illusion or a dream in the sense of being false or deceptive. The world is real because it is perceived, and its regularity and shared nature give it objectivity. The pain from stubbing your toe is real pain. The difference idealism highlights is one of substance. The mainstream materialist view holds that reality is made of mind-independent stuff, and consciousness is a mysterious emergent property. The idealist view flips this. Reality is fundamentally mental, and the material world is the appearance that this mental reality takes on. This doesn't necessarily make life less meaningful. For Berkeley, it made it more so, as it placed mind and spirit at the center of existence, suggesting that the universe is fundamentally intelligible because it is fundamentally idea-like. Critics of idealism often point to its apparent solipsistic risk. The idea that if everything is perception, how can we be sure other minds exist? Berkeley avoided this by appealing to God as the guarantor of a shared public world. Modern idealists might argue that the consistency and intersubjectivity of our experiences point to a common source or a universal mind, or they might explore the implications of a universe where individual minds are not entirely separate but are interconnected aspects of a larger conscious field. The enduring power of Berkeley's idealism is that it challenges the deepest assumptions of our materialist age, offering a coherent, if mind-bending, alternative that finds unexpected support in our most advanced sciences and technologies. It asks us to consider that the ultimate stuff of the cosmos might not be tiny, vibrating strings of energy, but the luminous, qualitative fabric of experience itself. After exploring these radical theories that place consciousness or mathematics at the foundation of reality, we must now turn to the view that most of us take for granted in our daily lives, the bedrock assumption of modern science, materialism, or its more precise cousin, physicalism. This is the conviction that the only thing that truly exists is physical matter and energy, operating according to fixed laws. In this worldview, everything in the universe, from the swirling galaxies to the beating of a human heart, and even the rich tapestry of your own thoughts and feelings, is ultimately reducible to and explicable by the interactions of fundamental particles and forces. There is no ghost in the machine is all there is, and consciousness is its magnificent, intricate product. The power of the materialist perspective lies in its staggering success. For centuries, this approach has been the engine of scientific progress, systematically dismantling mysteries and replacing them with physical explanations. We no longer attribute epilepsy to divine possession but understand it as a neurological disorder. We don't see lightning as the wrath of gods but as a massive electrostatic discharge. This relentless application of physical explanation has given us medicine, technology, and a deep understanding of the cosmos. The core methodology is reductionism, the practice of breaking complex systems down into their constituent parts to understand how they work. By studying atoms, we understand chemistry. By studying neurons, we aim to understand the mind. From this viewpoint, the mind simply is the activity of the brain. Every thought, memory, and emotion corresponds to a specific pattern of neural firing, a complex dance of electrochemical signals. Tools like fMRI scanners allow us to watch this dance in real time, correlating feelings of love, fear, or decision-making with activity in particular brain regions. Damage to the brain through injury or disease can alter personality, erase memories, or destroy the capacity for consciousness itself, providing powerful, if tragic, evidence for the physical basis of the mind. This perspective extends seamlessly to our evolutionary history. Consciousness, according to materialism, isn't a fundamental ingredient of the cosmos but a useful evolutionary adaptation. In the struggle for survival, an organism that could model the world internally, anticipate the future, and experience pain and pleasure had a significant advantage over one that operated on simple reflexes. The feeling of fear is a potent signal to avoid danger. The warmth of social bonding encourages cooperation, which enhances survival. Our rich inner world, with all its artistic and philosophical yearnings, can be seen as an extravagant byproduct of a brain that grew complex enough to turn its modeling capacity inward, creating a self-model, the sense of I. In this light, consciousness is not a mystery to be solved, but a biological function to be explained, no more inherently mysterious than digestion or photosynthesis. However, for all its explanatory power, materialism faces a formidable challenge, one we've encountered before: the hard problem of consciousness. The philosopher David Chalmers articulated this distinction clearly. The easy problems of consciousness are those that fit neatly into the materialist framework. How does the brain integrate information from different senses? How does it focus attention? How do we control our behavior? These are questions about function, and neuroscience is making remarkable progress in answering them. The hard problem is different. It asks why and how any of this physical processing should give rise to subjective, first-person experience at all. Why is there a what it is like to be you? Why does the firing of C fibers in the brain feel like the subjective experience of pain, rather than just being a silent data processing event? Materialism can describe the neural correlates of consciousness, the physical processes that accompany experience, but it has yet to bridge the gap between the objective description of a brain state and the subjective feeling itself. This is known as the explanatory gap. It seems perfectly conceivable, as philosophers point out, that a perfect physical duplicate of a human being, a philosophical zombie, could exist acting and talking exactly like a conscious person, but with no inner light on inside. The fact that we are not such zombies points to a reality that physical descriptions alone may not capture. This gap leads to other philosophical tensions, particularly around the concepts of meaning and free will. If our thoughts are entirely the product of deterministic or random physical processes in the brain, what becomes of our choices? From a strict materialist perspective, free will might be an illusion. Your decision to choose tea over coffee could be the inevitable result of the preceding chain of causal events. The state of your neurons, your genetic predispositions, and your past experiences, all governed by the laws of physics. This is a deeply unsettling conclusion for our sense of self and responsibility. Similarly, questions of ultimate meaning and purpose become difficult to ground. If the universe is just a vast, purposeless arrangement of particles, then any meaning we find in life is something we project onto it, a subjective invention rather than an objective discovery. For materialists, this isn't a cause for despair, but a call to responsibility. We must create our own meaning, ethics, and purpose within the brief window of our existence. Yet, the materialist vision is not without its own sense of profound wonder. It tells a story of an immense and ancient cosmos where simple hydrogen gas, over billions of years, organized itself into stars, planets, and eventually into beings complex enough to look back and ponder their own origins. We are not separate from the universe. We are a temporary, conscious expression of it. The atoms that make up our bodies were forged in the hearts of long-dead stars. In this view, the physical world is not barren or meaningless, but is the very source of the staggering complexity and beauty we see around us. The challenge for materialism is to continue its triumphant march of explanation without dismissing the profound reality of subjective experience as a mere illusion. It must either find a way to naturally accommodate the qualitative feel of consciousness within its physical framework, or risk being seen as an incomplete picture of a reality that is, at its heart, both physical and experiential. The idea that our reality might be a grand simulation or a mental construct is dizzying enough, but how could we ever truly prove it wrong? This brings us to one of philosophy's most potent and persistent challenges to our claim of knowledge: the brain in a vat thought experiment. Imagine that you are, right now, not a person with a body living in a world, but merely a brain. This brain has been carefully removed from your skull and is being kept alive in a vat of nutrient-rich fluid. Super advanced computers are connected to your brain's neural pathways, feeding it a perfectly coherent, seamless stream of electrical signals that mimic all the experiences of a normal life. This computer program is generating the feeling of the breeze on your skin, the sight of these words, the sound of your own breathing, and even the memory of reading the previous sentence. According to this scenario, everything you have ever experienced is an elaborate illusion orchestrated by this external system. The question this experiment forces upon us is devastatingly simple. If this were the case, could you ever tell the difference? This modern version of skepticism has deep roots, most famously in the work of the 17th century philosopher René Descartes. He was on a quest to find a foundation for knowledge that was absolutely certain, immune to any possible doubt. To do this, he engaged in a process of radical doubt, questioning everything he thought he knew. He considered that his senses could be deceived, as they sometimes are in dreams or by illusions. But he pushed further, entertaining the possibility of a malicious demon, a powerful being dedicated to deceiving him about everything, including the existence of the external world and even mathematical truths. Descartes' evil demon serves the same function as the supercomputer in the brain in a vat scenario. It is a tool for questioning whether any of our beliefs about reality are reliably true. The brain in a vat is essentially the scientific, technological update to Descartes' metaphysical demon, replacing magic with neuroscience and computing power. The power of this thought experiment lies in its logical possibility. We have no way to step outside of our own perceptions to check their source. All of our evidence for an external world comes to us through our senses, which are processed by our brain. If a malicious scientist or a sophisticated simulation can perfectly replicate those neural inputs, then from your first-person perspective, the simulated world would be indistinguishable from a genuine one. Your proof that you have a body, the feeling of your hand touching a desk, is just another signal fed to your brain by the computer. Your memories of your childhood are just data implanted at the start of the simulation. Even your logical deduction that you must have a body is just a thought generated by the very brain that is being deceived. There is no fail-safe internal test you can perform to prove you are not a brain in a vat, because any test you devise would rely on the very faculties and information that are under suspicion. This scenario creates a direct and powerful bridge to the simulation hypothesis we discussed earlier. In fact, the brain in a vat is a more localized, individual version of a simulated reality. While the simulation hypothesis posits that the entire universe, including all of history and other people, is a computational construct, the brain in a vat scenario focuses the deception squarely on you. It raises the haunting possibility that you could be the only real consciousness, with everyone else being a sophisticated non-player character in your personal simulation, a concept known as solipsism. Both ideas exploit the same gap between appearance and reality, suggesting that the world we take for granted could be a facade, and that the true nature of our existence is radically different from what we experience. So, is there any way out of this skeptical trap? Philosophers have proposed several responses. One common-sense rebuttal is an appeal to simplicity, often guided by Occam's razor, the principle that the simplest explanation is usually the correct one. The hypothesis that there is a real world that generally corresponds to our perceptions is vastly simpler than the convoluted scenario requiring a powerful, hidden entity deliberately deceiving a single brain. While this is a practical stance for navigating daily life, it doesn't constitute a philosophical refutation. The skeptic can rightly point out that simplicity is no guarantee of truth. The more complex, deceptive scenario could still be the actual one, however unlikely it seems. A more substantive response comes from looking at the content of our experiences themselves. Some philosophers, like Hilary Putnam, have argued that the brain in a vat scenario might be self-refuting in a linguistic sense. Putnam's argument is complex, but in essence, it suggests that if you were a brain in a vat, your words and thoughts would refer to the simulated objects and events created by the computer, not to real-world objects. Therefore, when you say the words brain in a vat, you are not actually referring to a real biological brain in a real vat, but only to the simulation's idea of those things. Consequently, the statement, "I am a brain in a vat," would be false because the "I" in that sentence refers to a simulated self, not a real brain. While this argument is clever, it is highly technical and controversial, and many feel it doesn't fully address the underlying worry about the reliability of our perception. Perhaps the most profound impact of the brain in a vat experiment is not that it proves we are deceived, but that it highlights the fundamental limits of our knowledge. It forces us to accept that our belief in an external world is just that, a belief, albeit a very powerful and necessary one. We cannot prove the world exists with absolute Cartesian certainty. Our entire lives are built on a foundation of trust in our cognitive and perceptual systems. This doesn't mean we should descend into paranoia or nihilism. Instead, it can be a call for intellectual humility. It reminds us that our perspective is inherently limited and that the map of reality we construct in our minds is just that, a map, not the territory itself. The true territory, whatever it may be, remains forever beyond our direct grasp, leaving us to navigate the world based on the best interpretations of the signals we receive, always aware that the ultimate source of those signals might hold a mystery we can never fully solve. If reality is fundamentally a frozen block or a collection of static objects, then how do we account for the undeniable, roaring river of change that defines our existence? The theory we explore now offers a radical answer, proposing that this river of change is not just a feature of reality, it is reality itself. This is process philosophy, a view most famously developed by the mathematician and philosopher Alfred North Whitehead in the early 20th century. Whitehead turned the traditional Western way of thinking on its head. For millennia, philosophers from Aristotle onward had focused on substances, the static, enduring things that undergo change. A rock, a person, a star were seen as the primary realities, with change being something that happens to them. Whitehead declared that this was backwards. He argued that the fundamental units of reality are not things, but processes, events, and happenings. Being is secondary, becoming is primary. We don't live in a universe of nouns, but in a universe of verbs. To grasp this, consider a simple, everyday object, a flame. Our common sense view might label it a thing, but what is a flame really? It is a constant, dynamic process of combustion. It is a rapid chemical reaction, a flow of energy, a flickering event. The moment the process stops, the flame ceases to exist. There is no hidden, static, flame substance hiding inside the fire. Whitehead proposed that everything is like this, from an electron to a human being to a galaxy. What we perceive as a stable, enduring object is actually a continuous series of interconnected events, a rhythm of becoming. He called these fundamental events actual occasions or drops of experience. Each actual occasion is a momentary happening that gathers influences from its entire past, achieves a unique unity, and then perishes, immediately giving its data to the next moment of experience. You are not a static substance that has experiences. You are a living series of these experiences, a personally ordered society of occasions, constantly renewing yourself moment by moment. This dynamic perspective finds a powerful echo in the world of modern physics, which long ago abandoned the idea of solid, billiard ball atoms. At the subatomic level, particles are better understood as excitations in quantum fields, dynamic patterns of energy and vibration. They are not tiny rocks, but more like standing waves in a constantly moving ocean. A proton, for instance, is a seething turmoil of quarks and gluons, a process of immense energy held in a dynamic equilibrium. Furthermore, the theory of relativity has already fused space and time into a single, dynamic spacetime that curves and warps in response to mass and energy. The universe is not a static stage on which events play out. The stage itself is an active participant in an endless cosmic dance. Process philosophy provides a metaphysical framework that feels perfectly at home with this scientific picture, suggesting that physics isn't just describing how things move, but is revealing the very process nature of what things are. The resonance extends profoundly into biology. An organism is the ultimate example of a process. Your body is not a thing that engages in metabolism. Your body is metabolism. It is a sustained pattern of material and energy flow. Every 7 years or so, nearly every atom in your body has been replaced. You are quite literally a different physical collection than you were a decade ago. What provides your continuity is not a fixed set of atoms, but the enduring pattern, the organized process of life itself. A river is another classic analogy. You can step into the same river twice, but the water molecules you touch the second time are completely different from the first. The river's identity lies in its flowing form, its watershed, its current, its process, not in the static substance of the water. Process philosophy argues that this is true for all of reality. Stability is not a sign of static being, but of a remarkably stable and rhythmic process of becoming. Whitehead's vision also offers a fascinating way to think about causality and relationship. In a substance-based worldview, objects are primary and their interactions are secondary. In process philosophy, relationship is built into the very heart of existence. Each actual occasion comes into being by prehending or feeling the influences of every other occasion in its past. This is a kind of causal feeling, a non-conscious taking account of the entire universe. Your experience in this very moment is constituted by your feelings of the light from the screen, the sound in the room, the memory of what you just read, and the gravitational pull of the earth. You are not in a vast web of relationships, and your existence is your unique synthesis of those connections. This makes the universe inherently interconnected and ecological. Nothing is truly separate. Everything is in a constant state of creative response to everything else. The implications of this view for our understanding of consciousness and value are deep. If reality is a vast network of processes, then consciousness is not a mysterious exception but a highly complex and sophisticated form of process, one with a great capacity for integrating past experiences and anticipating future possibilities. This perspective also suggests a different basis for ethics. If the world is made of static substances, our ethical duty might be to avoid harming them. But if the world is a flowing network of creative processes, then our ethical imperative shifts toward fostering the conditions that allow for richer, more complex, and more beautiful forms of experience to flourish. We become responsible not just for preserving things, but for nurturing the quality of becoming for ourselves, for other species, and for the planet as a whole. Process philosophy invites us to see ourselves not as isolated spectators in a world of objects, but as active, creative participants in an unfinished, evolving universe of endless possibility. This astonishing fine-tuning of the cosmos brings us directly to a principle that attempts to make sense of it all, a concept that is as simple as it is profound, the anthropic principle. At its heart, this idea confronts a question that has puzzled scientists and philosophers alike. Why do the laws of physics seem so perfectly calibrated to allow for our existence? The constants of nature appear to be set with such incredible precision that even the slightest deviation would render the universe sterile and lifeless. It's as if the cosmos knew we were coming. The anthropic principle provides a framework for reasoning about this apparent coincidence, and it comes in two very different flavors. One that is a statement of selective observation and another that ventures into the realm of cosmic purpose. Let's start with the more conservative and widely accepted version, known as the weak anthropic principle. this is less of an explanation and more of a logical observation. It simply states that the conditions we observe in the universe must be compatible with the existence of observers because we are here to observe them. Imagine a lottery winner marveling at the astronomical odds of their specific numbers being drawn. Their surprise, while understandable, is misplaced. Someone had to win, and from the winner's perspective, the outcome seems miraculously unlikely. In the same way, we shouldn't be surprised to find ourselves living in a universe capable of supporting life, because in a lifeless universe, there would be no one to be surprised. The weak anthropic principle filters our perspective. We can only exist in a universe that permits our existence, so it's no wonder we see a universe that looks hospitable. This principle effectively cautions us against drawing grandiose conclusions from what is essentially a selection bias. We are not at the center of the universe, but our viewpoint is necessarily centered on the narrow slice of cosmic possibility that allows for our presence. This logical filter becomes even more powerful when we consider the vast landscape of possibilities suggested by theories like the multiverse. If eternal inflation or the many worlds interpretation of quantum mechanics is correct, then there isn't just one universe, but a practically infinite number of them, each with its own randomly selected set of physical constants. In the overwhelming majority of these universes, the numbers are wrong. Stars never ignite, atoms never form, or gravity crushes everything instantly. These are dead universes, forever unobserved, but in an incredibly rare subset, the dice roll just right and life becomes possible. We, of course, find ourselves in one of those exceptionally rare, bio-friendly universes. The weak anthropic principle in this context doesn't require a fine-tuner. It just requires a large enough sample size for an unlikely event to become inevitable somewhere. Our universe isn't special, it's just the one we happen to inhabit. However, some scientists and thinkers find this answer unsatisfying and propose a much stronger claim. The strong anthropic principle suggests that the universe must have properties that allow life to develop within it at some stage in its history. Notice the crucial shift from does to must. This version implies that the emergence of conscious observers is not a random accident but a fundamental constraint on the nature of the cosmos itself. It hints that there is something necessary about the existence of life and mind, that the universe is in some sense compelled to produce consciousness. This idea naturally leads to more speculative and controversial interpretations. Some propose that consciousness itself plays a fundamental role in the laws of physics, perhaps even being necessary for the universe to achieve a coherent state, echoing the observer effect in quantum mechanics. Others see it as evidence for a teleological or purpose-driven cosmos, where the development of intelligent life is an embedded goal. One of the most fascinating and debated extensions of the strong principle is the participatory anthropic principle, championed by the physicist John Wheeler. He took the idea a step further, proposing that observers are necessary to bring the universe into being. In his famous phrase, "It's a participatory universe." Wheeler was influenced by the bizarre quantum mechanical notion that an event isn't real until it is observed. He suggested that we, as observers, might play a role not just in the present but retroactively in the past. Through our act of observation in the present, we might solidify a history that leads to our own existence. It's a dizzying loop of causality. The universe brings forth observers, and those observers, through their perception, help to define the universe that created them. This idea pushes the strong principle to its limit, suggesting a deep, inseparable link between the existence of the cosmos and the consciousness that perceives it. The implications of the anthropic principle, in either its weak or strong form, force a profound re-evaluation of our place in the cosmos. If the weak principle is correct, it instills a sense of cosmic humility. We are the beneficiaries of an incredible cosmic lottery, living on a razor's edge of possibility. our existence is a testament to the sheer vastness of reality, whether that vastness is expressed in a single universe with random constants or a multiverse of endless variety. It encourages a careful and critical approach to science, reminding us to account for the biases inherent in our own point of view. If the strong principle holds any truth, however, it suggests a universe that is far more congenial to life and mind. It opens the door to the possibility that we are not merely accidental tourists in an indifferent cosmos, but that consciousness is a fundamental and expected outcome of the universe's underlying laws. This doesn't necessarily prove the existence of a divine creator, but it does make the universe seem less alien and more like a home that was, in some deep sense, waiting for us to arrive. The debate between these two interpretations remains one of the most intriguing in modern science, a question that lies at the boundary between what we can observe and what it all might mean. But if the block universe paints a picture of a frozen, four-dimensional sculpture, a powerful philosophical rival insists that this view is a profound distortion of our most immediate experience. This brings us to a deep and ancient debate about the very nature of time itself, the clash between eternalism and presentism. On one side is the eternalist view we've touched on, which aligns with the block universe, asserting that past, present, and future are equally real. On the other is presentism, the common-sense belief that only the present moment is real, the past is gone forever, and the future is not yet written. This isn't just an abstract philosophical disagreement, it's a battle over the fundamental structure of existence, and modern physics has thrown a dramatic wrench into the works, challenging our intuitive sense of the flowing now. Presentism feels like the undeniable truth of our lives. We feel time passing. We remember the past as something that once was real but is now vanished, and we anticipate the future as a realm of pure potential. The present feels like a razor's edge, a unique and special moment where reality actually happens. This feeling is so visceral that it's difficult to even conceive of an alternative. When you feel the warmth of a cup of coffee in your hand, that sensation is happening now. The memory of brewing it minutes ago is a ghost, and the plan to have another cup later is just an idea. For the presentist, this isn't just a psychological fact, it's a metaphysical one. To say that Julius Caesar's assassination is just as real as you reading this sentence seems absurd. The event in the forum is over, done, its reality extinguished. Presentism defends the primacy of this lived experience, arguing that becoming, the actual coming into being and passing away of events, is the true nature of reality. However, the eternalist, armed with the findings of Einstein's theory of relativity, argues that this feeling of a flowing present is a powerful illusion, a trick of consciousness. The knockout blow against a universal present comes from the relativity of simultaneity. As we discussed, there is no single objective now that applies to the entire universe. What is present for you might be partly in the past or future for someone else moving at a different velocity. If presentism were true, there would need to be a privileged frame of reference to define the present moment for all of existence. But relativity firmly states that no such privileged frame exists. The now is relative to the observer. Therefore, the eternalist concludes, if there is no universal present, then we cannot grant the present any special ontological status. All moments must be equally real, each one being now for some observer somewhere. The flow of time is compared to the illusion of movement in a film. The projector's light illuminates one frame at a time, creating the sensation of motion, but all the frames coexist on the reel. Our consciousness is the projector light, scanning along the world line of our existence in the block universe. This debate becomes even more complex when W.E. Chinese letter the quantum world. Quantum mechanics, with its emphasis on the act of measurement and the apparent collapse of the wave function, seems to have a distinctly presentist flavor. A particle exists in a superposition of possibilities until it is observed in a specific present moment when it takes on a definite state. This seems to privilege the present as the moment where potentiality becomes actuality. However, this interpretation runs into a major problem when combined with relativity. If the collapse happens at a definite time, whose time, due to the relativity of simultaneity, two observers moving relative to each other might disagree on the exact order of events, including when the wave function collapse occurred. This can lead to logical paradoxes where one observer sees an event as having a definite outcome before another observer sees it as still undecided. Some physicists argue that this tension points toward a need to reformulate quantum mechanics in a way that is compatible with eternalism, perhaps by adopting the many worlds interpretation, where no collapse ever happens and all possibilities are equally real across the multiverse, a profoundly eternalist picture. The implications of this debate stretch far beyond physics into the core of human concerns like free will, responsibility, and the meaning of our lives. Presentism seems to naturally accommodate free will. If the future is genuinely open and not yet real, then our choices in the present are what bring it into existence. We are true authors of our destiny, carving a unique path into the unknown. In an eternalist block universe, however, the future is already out there, as fixed and unchangeable as the past. This can feel like a suffocating determinism where our sense of choice is a complete illusion. Yet, some philosophers offer a compatibilist view. They suggest that even in a block universe, your deliberation and decision-making process is a real, physical event woven into the fabric of space-time. You are free to act according to your nature, and your nature is part of the eternal story. The novel of your life has been written, but you are still the main character making authentic choices within the plot. Ultimately, the choice between eternalism and presentism may be the ultimate standoff between reason and intuition. Eternalism offers a coherent, elegant picture that aligns with our most successful theory of the large-scale universe, relativity. It provides a God's-eye view of a complete and ordered cosmos. Presentism defends the raw data of our conscious experience, the undeniable feeling of passage, the poignancy of loss, and the excitement of anticipation. It argues that a theory that dismisses the central feature of our existence as an illusion is deeply unsatisfying. Perhaps the truth lies in a synthesis we cannot yet conceive, a theory that reconciles the objective, frozen space-time of physics with the subjective, flowing time of consciousness. Until then, we are left straddling two worlds, one a vast, silent, and eternal block, the other a fleeting, vibrant, and urgent present, each demanding that we see reality in a fundamentally different and irreconcilable light. Now we arrive at a theory that pushes the anthropic principle into the realm of the truly spectacular, transforming us from accidental beneficiaries of cosmic fine-tuning into active co-creators of reality itself. This is the participatory anthropic principle, a concept forged by the brilliant and unconventional physicist John Wheeler. While the standard anthropic principle suggests the universe must be compatible with observers, Wheeler's radical extension proposed that observers are necessary to bring the universe into a definite state. In his breathtaking vision, the universe is like a grand, self-excited circuit, a loop of existence where the cosmos gives rise to conscious life, and that life, through the very act of observation, breathes concrete reality back into the cosmos. We are not just inhabitants of the universe, we are participants in its ongoing creation. To grasp this, we need to revisit the quantum weirdness we explored earlier, specifically the puzzle of the observer effect. In the quantum realm, particles exist in a haze of probability until a measurement forces them to choose a specific state, like a particle or a wave. Wheeler took this a step further, asking a profound question. What happens when we delay that act of observation until after the particle has, in a classical sense, already made its journey? He designed a series of thought experiments, now famously known as the delayed choice experiments, to probe this very edge of reality. These experiments suggest something that defies all common sense, that a decision made by an observer in the present can seem to rewrite the history of a particle, influencing what it was doing in the distant past. The most iconic of these is the cosmic-scale delayed choice experiment involving a distant quasar. Imagine light from a quasar billions of light years away traveling toward Earth. On its journey, it passes by a massive galaxy whose gravity acts as a gravitational lens, bending the space-time around it and creating two possible paths for the light to take to reach us, a cosmic fork in the road. Now, here on Earth, we have a choice. We can set up a detector that simply captures the light, which would cause each photon to behave as if it had taken one specific path, registering as a particle. Or we can set up an interferometer, a device that would allow the photon to interact with itself, demonstrating that it must have taken both paths simultaneously, behaving as a wave. The staggering implication of Wheeler's idea is this: the photon embarked on its journey billions of years ago. Yet our choice of how to measure it today appears to determine whether it traveled as a particle or a wave all that time in the past. Our present observation seems to reach back through time and sculpt the particle's history. This isn't just a thought experiment, it has been confirmed in laboratories with stunning precision. Using sophisticated equipment with beam splitters and mirrors, physicists have been able to delay the choice of how to measure a quantum system until after the particle has already traversed the apparatus. The results are unequivocal. The particle's behavior, whether it displays wave-like or particle-like characteristics, is determined by the final measurement setting, even when that setting is chosen after the particle's journey is nominally complete. It's as if the particle's history remains fluid and unresolved, a cloud of potentialities, until the moment an observer asks a specific question, forcing the entire timeline to snap into a coherent single story. The past, in a very real sense, is not fixed until it is observed in the present. Wheeler used a powerful analogy to illustrate this, the game of 20 questions, but with a surprising twist. Imagine playing the game where the answer is not a pre-chosen word. Instead, the first person to think of a word does so only after the second person has asked all their questions. The second person asks, "Is it a mineral?" and the first, committing to a consistent narrative, says yes. "Is it green?" "No," and so on. With each answer, the first person is building a consistent history for an object that didn't exist until the questions were asked. The final answer, when revealed, is a coherent entity that fits all the previous constraints. Wheeler suggested the universe plays a similar game with us. We, as observers, ask questions of nature through our experiments. The universe responds in a way that is consistent, but the specific reality we uncover, the answer, is only fully defined by the questions we pose. We are not discovering a pre-recorded truth. We are participating in a dialogue that defines what is true. This leads to the most profound implication of the participatory anthropic principle, a radical rethinking of causality. We are accustomed to a linear flow of time where the past causes the present, but Wheeler's work suggests a loop of circular causality. The universe in its early, hot state contained the potential for life. Over billions of years, it evolved galaxies, stars, planets, and eventually conscious observers. Those observers, through their acts of observation, then perform a kind of retroactive creation, solidifying the quantum uncertainties of the past into the definite history that led to their own existence. The universe brings forth observers, and the observers, through their perception, bring the universe into sharp focus. It's a closed loop, a self-referential system where the endpoint is intimately entangled with the beginning. Of course, this idea is met with significant skepticism. Critics argue that the term observer is misleading. The crucial event is not human consciousness, but the irreversible interaction of a quantum system with its environment, a process known as decoherence. In the delayed choice experiment, the choice is made by the final beam splitter or detector, not by the conscious awareness of a physicist. From this perspective, the universe is still a physical system following its own rules, and the appearance of backwards in time influence is just a quirk of how we describe the quantum state. The past is not being changed, it's just that the definition of the past is more fluid in quantum mechanics than in our classical intuition. Yet, even with this more conservative interpretation, Wheeler's core insight remains transformative. It forces us to abandon the classical ideal of a detached observer looking at a world that exists independently out there. In the quantum world, there is no sharp division between the observer and the observed. The measuring device and the system being measured become entangled, forming a single quantum whole. By extending this logic to the cosmos, Wheeler gave us a vision of a universe that is not a cold, mechanical clockwork, but a deeply interconnected and participatory phenomenon. It suggests that meaning and existence are not separate things. By existing and by questioning the nature of that existence, we are fulfilling a deep-seated function of the cosmos. We are the universe's way of awakening to itself, of transforming potentiality into tangible, beautiful, and conscious reality. Shifting our perspective from the cosmic dance of quantum observation, we venture into a theory that seeks to weave all of reality's threads into a single, elegant tapestry. This is string theory, perhaps the most ambitious candidate for a theory of everything. For over a century, physics has been split between two incredibly successful but fundamentally incompatible frameworks: Einstein's general relativity, which masterfully describes the force of gravity as the curvature of space-time on cosmic scales, and quantum mechanics, which with equal brilliance governs the bizarre probabilistic world of the atom. Yet, when these two theories are forced to meet, such as at the center of a black hole or at the moment of the Big Bang, the mathematics breaks down into nonsensical infinities. String theory emerges as a potential savior, proposing a radical rewrite of reality's most basic premise. The fundamental idea is as beautiful as it is strange. For decades, we've imagined the basic building blocks of the universe as point-like, zero-dimensional particles, dots with no size, like infinitesimal grains of sand. String theory says this is the source of our problems. Instead, it proposes that the most elementary entities are not points, but unimaginably tiny, one-dimensional vibrating loops of energy, strings. These strings are so small that if an atom were magnified to the size of our solar system, a string would be no larger than a tree on Earth. And just as a single violin string can vibrate in different modes to produce the distinct notes of a musical scale, these cosmic strings vibrate in different resonant patterns. One particular vibration might manifest as an electron, another as a quark, and yet another as the particle that carries the force of gravity, the graviton. In this breathtaking vision, the entire universe is a cosmic symphony, with every particle and force being a unique note played on these fundamental strings. This elegant concept, however, comes with an astonishing requirement, one that catapults us directly into the realm of science fiction. For the mathematics of string theory to be consistent and to include gravity, the universe cannot have only the three spatial dimensions of length, width, and height that we experience. The equations demand more specifically 10 or 11 dimensions of spacetime. This immediately begs the question, where are these extra dimensions? If they exist, why don't we see them? The most compelling answer is that they are compactified, or curled up into a space so incredibly tiny that they are forever beyond our perception. To grasp this, imagine a garden hose stretching far into the distance. From a great distance, it appears as a simple one-dimensional line. But if you were an ant crawling on the hose, you would discover a second dimension curled around the hose's circumference. In the same way, at every single point in our familiar three-dimensional space, there could be 6 or 7 extra dimensions curled up into a complex geometric shape known as a Calabi-Yau manifold. Our entire macroscopic reality is simply drifting along the extended dimensions, completely oblivious to the tiny, intricate world of the curled-up ones. This idea of hidden dimensions provides a powerful, unified explanation for the forces of nature. In our three-dimensional world, we experience gravity and electromagnetism as forces that weaken with distance. But from the perspective of string theory, their strength might be determined by how they propagate through the higher dimensional geometry. The specific way the extra dimensions are curled could explain why the force of gravity is so astonishingly weaker than the other fundamental forces. Perhaps gravity, unlike the other forces, is able to leak or spread out into these extra dimensions, diluting its strength in our three-dimensional realm. The distinct properties of all forces and particles could ultimately be a consequence of the shape of this hidden spatial geometry. The universe, then, is not just a collection of things, but a dynamic shape whose topology dictates the laws of physics themselves. The implications of string theory for the nature of spacetime are profound. In Einstein's relativity, spacetime is a smooth, continuous background stage on which particles move. String theory challenges this picture because strings are extended objects, not points. They can interact with the fabric of spacetime in a much richer way. They can wrap around the compactified dimensions, and their vibrations can actually warp and curve the geometry of the universe from within. This suggests that spacetime itself may not be fundamental. It could be an emergent property, a collective consequence of the interactions of a vast network of strings, much like the smoothness of water emerges from the chaotic jostling of countless molecules. This leads to mind-bending possibilities, such as the idea that our universe could be a four-dimensional brane, short for membrane, floating in a higher dimensional bulk, with collisions between branes potentially explaining cataclysmic events like the Big Bang. Yet, for all its majestic promise, string theory remains one of the most controversial ideas in modern physics. Its foremost challenge is a stark one. After decades of work, it has yet to make a single testable prediction that can be verified by experiment. The energy scales required to probe the strings themselves are trillions of times higher than what our most powerful particle colliders can achieve. Furthermore, instead of providing a single, unique theory of everything, the mathematics has revealed a vast landscape of possible solutions, perhaps 10 to the power of 500 different ways to curl the extra dimensions, each corresponding to a universe with different physical laws. This dizzying plurality leads some critics to argue that string theory is not a testable science but a complex branch of mathematics, offering a plethora of potential universes but failing to pinpoint why ours has the properties it does. Despite these formidable hurdles, string theory continues to captivate the finest minds in physics, not merely as a potential theory of everything, but as a deep well of mathematical innovation that has already enriched our understanding of black holes and quantum field theory. It stands as a testament to humanity's relentless drive to find a single, beautiful story that can explain the cosmos from the smallest vibration to the largest galaxy. While the many worlds interpretation offers a grand, impersonal solution to the quantum measurement problem by branching entire universes, it leaves a deeply personal question unanswered. What happens to the individual mind during this cosmic split? A less famous but equally provocative interpretation, the many minds interpretation, tackles this head-on. Instead of multiplying universes, this theory multiplies minds. It proposes that when a quantum event with multiple possible outcomes occurs, it is not the cosmos that divides, but the conscious awareness of each observer. In this view, a single, universal wave function continues to evolve smoothly, never collapsing, but within that one reality, different minds can become correlated with different, mutually exclusive outcomes of the same event. To understand how this works, let's return for a moment to the unfortunate feline in Schrödinger's box. In the Copenhagen interpretation, the cat is in a superposition until observed. In the many worlds view, the universe splits into one with a live cat and one with a dead cat. The many minds interpretation presents a third, more intimate scenario. There is only one box, one cat, and one physical reality. The cat is either definitively alive or definitively dead. However, when you open the box, your conscious mind does not perceive the single outcome. Instead, your mind itself enters a superposition of states. One stream of your consciousness perceives a living cat, while another, completely separate stream of your consciousness perceives a dead cat. Both experiences are equally real to the minds experiencing them, yet they are psychologically isolated from one another, forever unaware of each other's existence. This idea was developed independently by physicists and philosophers such as H. Dieter Zeh and David Albert, and it finds a particularly clear expression in the work of philosopher Michael Lockwood. He argues that what we call the mind is not a single, indivisible entity but a collection of conscious perspectives, or mind stages. Under normal circumstances, these stages are strongly correlated, giving us the illusion of a continuous, unified self moving through time. But during a quantum measurement, this correlation breaks. The different possible outcomes encoded in the wave function become correlated with different mind stages of the observer. It's as if your consciousness is a rope made of many strands. A quantum event doesn't cut the rope in two, but instead causes the strands to unravel and weave themselves into two separate, thinner ropes, each telling a different story. The primary appeal of this interpretation is how it resolves the vexing measurement paradox without the extreme ontological cost of an infinite number of parallel worlds. The physical universe remains a single, elegant mathematical object described by the uncollapsed wave function. All the weird superpositions of cats, measuring devices, and even macroscopic objects continue to exist. The branching happens not in the fabric of space-time, but in the fabric of consciousness itself. This elegantly sidesteps the question of what counts as a measurement capable of causing a universal split. Any interaction that could, in principle, lead to a difference in a conscious experience has the potential to cause a mind split. The problem is transferred from physics to the philosophy of mind, focusing on the nature of perception and awareness. But this solution raises its own set of profound and unsettling questions, primarily about the nature of shared reality. If my mind can split to see a live cat while another stream of my mind sees a dead one, what happens when two people open the box together? The theory suggests that their mind stages become entangled. The stream of my consciousness that sees a live cat will be correlated with the stream of your consciousness that also sees a live cat. We will agree on the outcome and have a shared experience. Conversely, the me who sees a dead cat will be paired with the you who sees the same. There is no single objective fact about the cat's state independent of the minds observing it. Instead, reality is a tapestry of consistent subjectivities. Groups of minds that interact become locked into a shared perspective, creating the powerful illusion of a single public world. This leads directly to the most intimate implication of the many minds interpretation, the fragmentation of the self. We cling to the notion of a single, continuous I that persists from moment to moment. This theory suggests that this is a powerful cognitive illusion. With every quantum event you witness, however minor, your consciousness is constantly branching into countless versions, each following its own timeline. The you who finished reading this sentence is not the same you who started it. A near infinite number of your mind stages have already branched off to perceive alternate realities, from a flicker in the light to a different thought crossing your mind. Your sense of a linear history is just the unique narrative of one thread of your consciousness, unaware of the countless other threads weaving their own stories. This makes personal identity not a solid thing, but a path-dependent pattern, a single strand selected from a vast tapestry of possibilities. The theory also ventures into deeply speculative territory regarding the connection between quantum mechanics and the hard problem of consciousness. It seems to require that consciousness is not an emergent property of complex brain computation, but something more fundamental. For minds to branch in correlation with the wave function, there must be a basic link between mental states and quantum states. This has led some proponents to suggest a form of panpsychism, where consciousness is a primordial feature of the universe that interacts with quantum processes. The many minds interpretation doesn't explain how this interaction works. It simply posits it as a necessary feature to solve the measurement problem. For critics, this is its greatest weakness. It replaces one mystery with another, trading the puzzle of wave function collapse for the enigma of how consciousness splits. Ultimately, the many minds interpretation presents a reality that is both singular and profoundly fragmented. It preserves a beautiful, unified physical cosmos while simultaneously suggesting that our inner worlds are endlessly dividing. It offers a unique perspective on fate and free will. Every possible outcome of your choices is realized in the experience of some branch of your mind. The version of you that took a risk and succeeded exists, as does the version that failed. This can be seen as a form of liberation, assuring that all possibilities are lived, or as a form of nihilism, diminishing the significance of any single choice. It forces us to confront the possibility that the deepest reality is not a world of separate objects, but a universe of overlapping perspectives, where the only constant is the ceaseless branching of awareness into new and isolated realms of experience. After exploring theories that multiply minds or branch universes, we turn to a philosophy that brings the question of reality home, to the very ground of our own direct, lived encounter with the world. This is phenomenology, a movement founded by Edmund Husserl in the early 20th century, which makes a radical and powerful claim. The only reality we can ever truly know is the one that appears in our conscious experience. Instead of speculating about hidden worlds behind the scenes, whether parallel universes, simulated realities, or noumenal things in themselves, phenomenology insists we must first rigorously describe the world as it is given to us. Its motto, "To the things themselves," is a call to set aside scientific theories and philosophical prejudices and return to the rich, detailed tapestry of our immediate perception. Husserl's starting point was a method he called the phenomenological reduction, or epiché, a deliberate suspension of judgment about the independent existence of the external world. This isn't a denial of the world's reality, like the brain in a vat scenario, but a strategic bracketing. The goal is to stop taking the world for granted and instead focus entirely on the phenomena, the things as they appear to consciousness. By doing this, we discover that every experience has a specific structure. It is always an experience of something. Consciousness is always intentional. It is directed toward an object. You are never just conscious. You are conscious of this sentence, of the feeling of your chair, of a memory. This inseparable bond between the act of experiencing and the object experienced is the fundamental field of investigation. For phenomenology, reality is not a collection of objects that we then perceive. It is the correlation between the appearing world and the consciousness to which it appears. This philosophical project was profoundly deepened by Maurice Merleau-Ponty, who introduced a crucial element often overlooked by abstract philosophy, the body. In his seminal work, Phenomenology of Perception, Merleau-Ponty argued that we are not disembodied minds that happen to be housed in a physical shell. Rather, we are our bodies. Our consciousness is inherently embodied. We perceive and understand the world through our physical being. Your body is not an object in the world like other objects. It is your point of view on the world, your anchor, your means of engagement. He called this the lived body to distinguish it from the objective body that a scientist might dissect or measure. The lived body is the subject of experience, not just an object within it. Merleau-Ponty's genius was in showing how this embodiment shapes reality itself. Consider something as simple as depth perception. From a scientific, objective view, depth is a calculation based on the slightly different images received by each eye. But for the lived body, depth is not a calculation. It is a direct, felt potential for action. The cup of coffee is not at a distance of 2 feet, it is within reach. The stairs are not a geometric incline, they are climbable. Our world is not a neutral space with coordinates, but a landscape of meanings and affordances that speak directly to our bodily capacities. A doorknob presents itself as graspable, a path as walkable. This world of significance is the primary reality we inhabit, and it is constituted by the dynamic interplay between our bodily skills and the environment. This perspective brilliantly bridges the ancient chasm between subjective experience and objective reality. The objective, scientific world of measurable particles and forces is not the false one. It is a highly refined, abstract derivation from the lived world. It is a valuable and powerful tool, but it is a second-order construction. The primary reality is the life world, the Lebenswelt, where things have colors, sounds have meanings, and space is organized around our purposes. Science itself begins with the observations of scientists who are embodied beings in this life world. Before a physicist can measure the wavelength of light that corresponds to red, they must first have the lived experience of seeing the color red. Phenomenology argues that you cannot build an understanding of reality by starting with the abstract scientific description and then trying to explain how consciousness pops out of it. Instead, you must start with the conscious, embodied experience from which all our knowledge, including science, is born. The implications of this view extend into every corner of human existence. It transforms our understanding of other people. We don't infer that others have minds through a logical argument. We directly perceive their consciousness in their gestures, their expressions, their actions. The sadness of a friend is not a hidden inner state we deduce. It is present in the slump of their shoulders and the tone of their voice. We inhabit a shared social world because our bodies communicate and understand each other at a pre-reflective level. This philosophy also offers a profound way to understand art. A great painting does not merely represent an object, it captures and communicates a way of seeing, an embodied perspective on the world that we can, in a sense, inhabit. It makes a piece of the artist's lived reality available to our own. Ultimately, phenomenology does not offer a grand, metaphysical theory about what reality is made of. Instead, it offers a method for rediscovering the wonder and depth of the reality that is already before us. It asks us to pause and truly see the blueness of the sky, to feel the solidity of the ground, to listen to the silence between sounds. In a journey that has taken us to the edges of the cosmos and the birth of universes, phenomenology brings us back to the most immediate and undeniable fact of our existence, that we are here, embodied and conscious, in a world that continuously reveals itself to us. It suggests that the ultimate mystery is not hidden in a distant dimension or a quantum equation, but is shining forth in every moment of our perceptually rich and meaningful lives. If the universe is a symphony of vibrating strings or a block of frozen space-time, could its most fundamental nature be not physical at all, but informational? This brings us to a theory that reframes existence in the most modern of terms, the computational universe hypothesis. This provocative idea suggests that at its core, the cosmos is not made of particles or fields, but of bits of information. The universe, in this view, is a gigantic, ongoing computation, a cosmic computer where the laws of physics are not mysterious forces but the algorithms and software that govern the processing of this fundamental information. It's a vision where reality is not just like a computer, it is a computer, and everything within it, from the orbit of planets to the firing of neurons, is part of a grand, dynamic calculation. The roots of this idea can be traced to the pioneering work of Konrad Zuse, a German engineer who, in the 1960s, was one of the first to suggest that the universe might be a giant cellular automaton. Imagine a vast, multidimensional grid like an infinite chessboard. Each cell on this grid can be in one of a finite number of states, on or off, 1 or 0. The entire system evolves in discrete ticks of a cosmic clock, with each cell updating its state based on a set of simple, predefined rules that take into account the states of its neighboring cells. From these incredibly simple local interactions, astonishing complexity can emerge. We see this in computer models like John Conway's Game of Life, where basic rules give rise to patterns that move, replicate, and behave in lifelike ways. Zeus and later proponents like digital physicist Stephen Wolfram propose that our universe operates on a similar principle, but on an unimaginably vast and fine-grained scale. The apparent smoothness and continuity of our world would then be an illusion, a large-scale average of countless tiny, discrete computational events happening at the smallest possible scale, the Planck scale. This perspective leads directly to a profound question about the fabric of reality. Is it continuous or discrete? Our everyday experience suggests continuity. The flight of a bird through the air appears smooth, and time seems to flow without interruption. Classical physics, as described by Newton and Einstein, is built on the mathematics of continuous fields and smooth curves. However, the computational universe hypothesis strongly favors a discrete reality. In a computer, everything is ultimately digital, broken down into finite, separate steps and distinct values. There is no true continuum. Growing evidence from theoretical physics hints that our universe might indeed be this way. Quantum mechanics introduces a fundamental graininess to the universe. Energy comes in packets called quanta. Furthermore, the quest for a theory of quantum gravity suggests that space and time themselves may not be smooth but quantized, composed of tiny, indivisible units. The Planck length and Planck time are thought to be the absolute smallest possible measurements, the pixel size and clock cycle of the cosmic computer. The speed of light, then, could be the maximum processing speed at which information can travel from one cell to the next. The implications of this are staggering for our understanding of physical laws. In the computational view, a law of nature like gravity isn't a mystical force acting at a distance. It is an algorithm, a recipe that the universe computer follows to update the state of its informational grid. The elegant equations of general relativity that describe how mass curves spacetime would be a high-level, emergent description of a deeper, digital process happening beneath. It would be akin to the sophisticated behavior of a character in a video game emerging from the low-level machine code of the game engine. This doesn't make the laws any less real or powerful, it simply explains their origin. They are the consistent, predictable software that runs on the hardware of the universe. This hypothesis also offers a fascinating potential resolution to the mystery of the universe's fine-tuning. If the universe is a computation, then its laws are its programming language. Some programs would be simple and quickly halt. Others would run forever but produce only boring, repetitive output. Our universe appears to be a program of a very special kind, one that is complex enough to run for billions of years and generate stars, planets, life, and consciousness. The specific constants of nature, like the strength of the forces, would be the fundamental parameters of this cosmic code. The reason they seem so perfectly tuned for complexity is that we are living inside a simulation that supports complex computation. A universe that couldn't support computation certainly couldn't support computers or the conscious observers who operate them. Naturally, this idea faces significant challenges and criticisms. One major question is, what is the physical substrate of this cosmic computer? A simulation running on our laptops requires silicon chips and electricity, a physical foundation. But if the entire physical universe is the computation, then we are left with a kind of circularity. The hypothesis seems to explain physics in terms of computation, but it may require a pre-existing physics to house the computer, leading to an infinite regress. Some thinkers get around this by proposing that information is truly fundamental, and what we call physics arises from it, not the other way around. Another criticism is that a discrete, computational universe might struggle to replicate the perfect symmetries and continuous laws that have been so successfully described by differential equations. The smoothness of space and time in general relativity is a formidable hurdle for any digital theory to overcome perfectly, though proponents argue that at the scales we experience, the discrete nature would be effectively invisible, just as a digital photograph appears continuous when viewed from a distance. Ultimately, the computational universe hypothesis represents a monumental shift in perspective. It takes the scientific impulse to explain the world through mechanism and pushes it to its logical extreme. The universe is not merely mechanistic, it is computational. This view connects the cosmos to the information age, suggesting that the same principles that govern our own digital creations might be the very principles that govern reality itself. It paints a picture of a universe that is rational, fathomable, and perhaps even understandable in terms of the logic we are only just beginning to master. Whether it is ultimately proven true or not, it serves as a powerful reminder that our quest to understand the cosmos is at its heart a quest to decode its underlying program. But if idealism places mind at the foundation and materialism insists on matter, must we choose one or the other? Perhaps the entire debate is built on a false dichotomy, a mistaken assumption that these are the only two fundamental substances. This brings us to a sophisticated and compelling compromise known as neutral monism, a theory that proposes a third, more primitive element from which both mind and matter spring. Imagine a deep, underground well that serves as the single source for two separate streams. One stream flows to the east, becoming the river of mental phenomena, our thoughts, feelings, and sensations. The other flows west, becoming the river of physical phenomena, atoms, forces, and galaxies. Neutral monism suggests that reality is like that original well, a neutral substance that is neither mental nor physical in itself, but whose different arrangements give rise to the two distinct worlds we experience. The roots of this idea are ancient, but one of its most powerful and eloquent advocates was the 17th century philosopher Baruch Spinoza. Living in an era dominated by the mind-body dualism of René Descartes, Spinoza offered a radically different picture. Descartes saw the world as composed of two fundamentally different substances, res cogitans, thinking substance, and res extensa, extended substance. Spinoza argued that this division was logically flawed. He proposed that there can only be one ultimate, infinite substance, which he called either God or nature. This single substance has an infinite number of attributes, but we finite humans can only perceive two of them, thought and extension. In Spinoza's system, your mind and your body are not two different things that interact mysteriously. They are one and the same thing expressed under two different attributes. A mental event, like a decision to raise your hand, and the physical event, the hand rising, are two parallel descriptions of the same underlying reality. The mental does not cause the physical, nor vice versa. They are perfectly correlated because they are two sides of the same coin. Centuries later, in the early 20th century, the philosopher and mathematician Bertrand Russell revived and refined this concept using the tools of modern logic. Russell was deeply concerned with what he called the causal problem. Physics describes the world in terms of causal chains of events in space and time. But when we look at our own internal world, we find a series of thoughts and sensations that also seem to be causally connected. How do these two causal series relate? Does a physical event in the brain cause a mental event, or is it the other way around? Russell argued that both physics and psychology are studying the same neutral events but from different perspectives. Physics describes the external, structural relations between events, their order in space and time. Introspection reveals their intrinsic, qualitative nature, what it feels like from the inside. A single event, like a photon of light striking a retina, has an external, physical structure that physics can describe, and it also has an intrinsic nature that, when processed by a complex brain, becomes the qualitative experience of seeing the color red. The event itself is neutral. Its mentalness or physicalness depends on how it is apprehended. This perspective offers an elegant solution to the infamous, hard problem of consciousness that stumps both materialism and idealism. The materialist struggles to explain how subjective experience emerges from objective matter. The idealist struggles to explain why the mental world appears to follow such rigid, objective physical laws. Neutral monism sidesteps the problem entirely by denying the initial separation. There is no gap to bridge between mind and matter because they were never truly separate to begin with. They are different aspects or manifestations of the same underlying neutral reality. The laws of physics are the laws describing the relational structure of this neutral stuff. The qualities of consciousness are the intrinsic nature of that same stuff when organized in a sufficiently complex way. This view is deeply compatible with a scientific worldview, as it does not require any spooky, non-physical forces, while simultaneously taking the reality of subjective experience seriously. In contemporary consciousness studies, variations of neutral monism have experienced a significant resurgence, often under the banner of dual aspect theory or Russellian monism, in honor of Bertrand Russell's contributions. Modern proponents, like the philosopher David Chalmers, suggest that the fundamental properties of the universe might be what he calls proto-phenomenal. These are properties that are not themselves conscious experiences, but have the potential to combine in specific ways to constitute consciousness. This is analogous to how fundamental physical particles are not themselves solid or wet, but can combine to form solid rocks or wet water. In this view, an electron has a very simple, primitive intrinsic nature, a tiny grain of experience so basic and elementary that we can't possibly imagine it. When these neutral entities are arranged in the spectacularly complex network of a human brain, their proto-phenomenal properties combine to generate the rich, unified stream of consciousness we all know. The implications of this view are profound for our understanding of the cosmos. It suggests a universe that is fundamentally unified, not split into two incompatible realms. It offers a path toward a truly unified science, where physics and the science of consciousness are not competing descriptions but complementary ones, each revealing a different facet of a single, coherent reality. It also provides a natural place for consciousness in the natural order. We are not accidental ghosts in a machine, nor is the physical world an illusion in a giant mind. Instead, we and the entire universe are expressions of a deeper, neutral ground of being. This theory doesn't answer all the questions. The nature of the neutral substance remains mysterious, but it reframes the quest in a way that is both intellectually satisfying and humbling, pointing toward a reality more integrated and wondrous than either pure materialism or pure idealism could ever allow on their own. But what if the single, explosive beginning of the Big Bang wasn't a beginning at all, but merely one chapter in an endless cosmic cycle? This leads us to a dramatic and elegant alternative known as the ekpyrotic universe model. The name itself, derived from the Greek word for conflagration or fire, hints at its explosive nature, but this is a very different kind of fire than the Big Bang's initial singularity. This theory emerges from the same framework as string theory, painting a picture where our entire three-dimensional universe is a dynamic membrane, or brain, floating within a higher dimensional expanse. In this grander space, the Big Bang loses its status as the ultimate starting point, becoming instead a transformative event caused by a collision between our brain and another. The core of the ekpyrotic model is its cyclic nature. Instead of a linear timeline stretching from a single beginning to an eventual heat death, the cosmos undergoes an endless sequence of cycles. Each cycle begins with the two brains, which represent parallel universes existing far apart in the hidden dimensions. They are drawn together by a faint force, perhaps a form of gravity operating in the higher dimensional bulk. As they approach, their mutual attraction accelerates them. The moment of collision is the pivotal event. This is the Big Bang. The immense kinetic energy of the impact is converted into the searing heat and dense matter that filled the nascent universe, setting off the expansion we observe today. Following this colossal collision, the brains bounce apart, and the universe we inhabit begins to cool and expand, allowing for the formation of galaxies, stars, and planets. But the story doesn't end with an eternal expansion. Eventually, the gravitational attraction between the brains overcomes the momentum of their separation, drawing them back together for another cosmic collision and another new beginning. In this view, the universe has no true start and no definitive end. It is an eternal, rhythmic dance of creation and renewal. This model offers a particularly elegant solution to one of the biggest puzzles in cosmology, the problem of initial conditions, or why the universe was so perfectly flat and uniform at the start. The standard Big Bang theory requires a brief period of incredibly rapid expansion called inflation to explain these features. A theoretical add-on that, while successful, remains unproven. The ekpyrotic model provides a natural alternative. During the long, slow approach of the brains before the collision, any irregularities or wrinkles on their surfaces are stretched and smoothed out. Imagine two vast, flexible sheets being pulled taut as they move toward each other. Any bumps or wrinkles would be flattened by the tension. This pre-Big Bang smoothing process naturally produces the flat, uniform universe we see without the need for a separate inflationary epoch. It turns a theoretical problem into a direct consequence of the model's core mechanics. However, the ekpyrotic model is not without its own significant challenges. One of the most critical questions is what happens to the second law of thermodynamics, which states that entropy or disorder always increases over time. If the universe is cyclic, wouldn't the entropy from each cycle carry over into the next, leading to a hotter, more chaotic universe with each successive bang? Proponents of the model suggest that the colossal expansion following each collision effectively resets the entropy clock for the observable universe. The vastness created by the bang dilutes the entropy of the previous cycle to such an extent that each new cycle can begin again with a low entropy, ordered state, allowing for the formation of new complex structures. This remains a topic of intense debate among theoretical physicists. Another major hurdle is testability. How could we possibly find evidence for events that occurred before our Big Bang or for the existence of other brains in unseen dimensions? Scientists have proposed looking for specific signatures imprinted on the oldest light in the universe, the cosmic microwave background radiation. A brain collision might leave a distinctive pattern of gravitational waves or a particular type of non-uniformity in this background glow. While current telescopes have not yet detected such a signal, future observational technologies could, in principle, provide the data needed to support or refute this captivating idea. The ekpyrotic universe model pushes the boundaries of cosmology, challenging our deepest assumptions about beginnings and endings, and suggesting that the ultimate nature of reality might be not a single explosion, but an infinite, resonant rhythm of creation. After navigating the dizzying cosmic perspectives of eternalism and the intimate branching of many minds, we arrive at an interpretation of quantum mechanics that takes a radically different starting point. This is quantum Bayesianism or cubism, a framework that dares to place the individual agent, the person making a measurement, at the very center of quantum reality. At its heart, cubism proposes a profound shift in how we understand the probabilities that are the lifeblood of quantum theory. They are not objective features of the world waiting to be discovered, but rather subjective degrees of belief, personal bets an agent makes about the consequences of their future actions. To grasp this, it helps to step back from the quantum realm for a moment and consider a more familiar kind of probability. Imagine you're about to flip a coin. Before it lands, you might say there's a 50% chance it will be heads. In the standard view, this is an objective fact about the coin. It has an inherent 50-50 propensity. But a Bayesian statistician sees this differently. That 50% isn't a property of the coin, it's a measure of your personal uncertainty. It quantifies your belief based on your knowledge about the outcome. The moment the coin lands and you see its heads, your probability instantly updates to 100%. The change wasn't in the coin, it was in your state of knowledge. Cubism takes this deeply personal, subjective interpretation of probability and applies it to the very core of quantum mechanics. This transforms the infamous quantum measurement problem. In the Copenhagen interpretation, the act of measurement causes a mysterious collapse of the wave function, an objective change in the world. Cubism offers a far less spooky explanation. For a cubist, the wave function is not a description of a quantum system itself. Instead, it is a catalogue of an agent's expectations, a tool they use to assign personal probabilities to the outcomes of their potential interactions with that system. When an agent makes a measurement and gets a specific result, the wave function doesn't collapse as an objective event in the world. It simply updates, much like your probability for the coin flip updated. The agent's beliefs change dramatically based on the new experience, but the external world hasn't undergone a magical transition. The shift is in the agent's internal knowledge state, not in the quantum system's independent reality. This makes reality intensely personal and agent-dependent. Your quantum state for a particle is your own private set of expectations, shaped by your unique history of interactions. My quantum state for the same particle might be different if I have different information or have performed different experiments. There is no single God's eye view wave function for the universe. Instead, reality is a tapestry of interlocking but distinct personal perspectives. This might sound like it leads to solipsism, where everyone is trapped in their own private world, but cubists argue the opposite. We build up a shared, objective world through communication. When I tell you the result of my measurement, you can use that information to update your own quantum state. Our personal beliefs become coordinated through a constant exchange of experiences, allowing us to successfully navigate a common reality and build a consistent body of scientific knowledge. The implications for the nature of science itself are revolutionary. Since the time of Newton, the ideal of science has been to provide an objective, third-person description of the world as it is, independent of any observer. Cubism rejects this ideal as not only unattainable but fundamentally misguided. Science, from this perspective, is not about uncovering a pre-existing, observer-independent reality. It is a toolkit for agents to better navigate the world and manage their expectations. The laws of physics are not decrees handed down from nature. They are an incredibly successful user's manual for making reliable predictions about the consequences of our actions. This doesn't make science any less powerful or precise. In fact, it explains its power. Quantum mechanics is the best guide ever devised for an agent to place bets on what will happen when they intervene in the world. This view elegantly dissolves many of the quantum paradoxes that have baffled physicists for a century. Take Schrödinger's cat. The problem arises from thinking the cat is objectively both alive and dead. For a cubist, the quantum state describing the cat is not a picture of the cat's condition, but a representation of the agent's uncertainty before opening the box. The agent is in a state of suspense, assigning probabilities to the two possible experiences they might have. There is no paradoxical superposition of a living and dead cat in the world. There is only the agent's own uncertain anticipation, which resolves into a definite experience upon looking inside. The paradox vanishes when we stop projecting our subjective probabilities onto the world as objective facts. By centering the experiencing agent, Cubism also forges a fascinating link between the cold, formal mathematics of quantum theory and the warm, lived reality of human consciousness. It acknowledges that science is a human activity conducted by conscious beings who have beliefs, make choices, and have experiences, where other interpretations struggle to define what counts as an observer. Cubism embraces the concept. The observer is the agent, any entity capable of making decisions, taking actions, and experiencing the consequences. This doesn't mean consciousness causes wave function collapse. It means that quantum theory is inherently a theory about the interface between an agent and the world. It is a theory of decision-making under uncertainty at its most fundamental level. In this light, Cubism doesn't solve the hard problem of consciousness, but it does provide a coherent framework where conscious agents are not embarrassing outliers in a purely physical theory, but the very protagonists for whom the theory was written. It presents a universe that is not a monolithic, predetermined clockwork, but a participatory arena where each of us, through our actions and observations, helps to define the reality we encounter. But if the quantum world demands a role for the observer and presents us with paradoxes of time, what if the solution is to turn our entire understanding of causality inside out? This is the astonishing proposition of the transactional interpretation of quantum mechanics, conceived by physicist John Cramer in the 1980s. It proposes that the bizarre events in the quantum realm are best understood as a kind of negotiation, a handshake across time between the past and the future. In this view, reality as we perceive it is not a one-way street from cause to effect, but a mutual agreement forged by waves traveling both forward and backward in time. To understand this, we need to revisit the classic double-slit experiment, but with a new set of eyes. In the standard description, a particle is emitted from a source and seems to travel as a wave of possibilities, passing through both slits simultaneously and interfering with itself before being detected at a specific point on the screen. The transactional interpretation offers a radically different narrative. It begins with the idea that when a particle is offered up by a source, it doesn't just send out a wave forward in time. It sends out an offer wave that radiates in all directions, moving forward through time. This wave expands to fill the entire experimental setup, exploring all possible paths, including through both slits. When this offer wave reaches the detectors on the far screen, something remarkable happens. Each detector that is touched by the wave does not just passively register a hit. Instead, it sends a response. It generates a confirmation wave that travels backwards in time, retracing the exact path of the offer wave back to the source. Now, here is the crucial moment of creation. Reality solidifies through a handshake. Only one of these confirmation waves traveling backward will perfectly reinforce and match the original offer wave traveling forward. When this resonant match occurs, a transaction is completed. Energy and momentum are transferred, and a real, detectable particle manifestation occurs at that specific location. The particle doesn't mysteriously disappear from all other possible paths. From this perspective, it was only ever truly real along the single pathway where the handshake was successfully completed. All the other possibilities were just unconfirmed offers that simply faded away once the transaction was finalized. This elegant process naturally explains the interference pattern in the double-slit experiment. The offer wave goes everywhere, and the confirmation wave from each point on the screen has to interfere with itself along all possible return paths. The resulting pattern of which handshakes are possible is exactly the interference pattern we observe. This interpretation provides a stunningly intuitive solution to some of quantum mechanics' most stubborn paradoxes. Consider the dilemma of Schrödinger's cat. The standard problem is that the cat seems to be suspended in a blur of life and death until observed. In the transactional view, the transaction that determines the fate of the cat, whether the radioactive atom decays or not, is initiated at the moment the experiment is set up. The offer wave from the radioactive source explores both possibilities, decay and no decay. the confirmation wave from the potential future, a future that includes a human observer finally opening the box, travels back in time to complete the transaction. The outcome is fixed not at the moment the box is opened, but at the moment the entire experiment begins, with the final observation simply being the culmination of a handshake that was agreed upon across time. The cat is never in a superposition. It is either alive or dead from the very start, its fate sealed by a negotiation between the past emission and the future detection. The most profound implication of this theory is its direct challenge to our linear, common-sense view of causality. We are accustomed to a world where causes always precede their effects. The transactional interpretation suggests that at the quantum level, this is an oversimplification. Effects can reach backwards in time to influence their causes through the confirmation wave. This is not time travel in the science fiction sense of changing the past. The process is perfectly consistent and paradox-free. The confirmation wave is not altering history. It is an integral part of a single, unified event that spans across time. The emission of the offer wave and the absorption via the confirmation wave are two parts of one whole. The effect of detection is just as necessary for the cause of emission as the emission is for the detection. They are mutually dependent, like the two ends of a seesaw. This introduces a concept of circular or reciprocal causality, where the future plays an active role in shaping the present. Of course, the idea of waves moving backward in time is met with significant skepticism. The primary objection is that it seems to violate our deepest intuitions and could potentially lead to logical paradoxes, like the infamous grandfather paradox, where someone goes back in time and prevents their own birth. Proponents of the transactional interpretation argue that it is mathematically rigorous and inherently avoids such paradoxes because the transactions are constrained by quantum rules. Only self-consistent handshakes that do not create contradictions are allowed to be completed. The theory is a direct interpretation of the standard quantum mechanical equations, particularly those advanced by Richard Feynman, who himself used the concept of path integrals that consider all possible histories, both forward and backward in time. In this light, the transactional interpretation can be seen as giving a physical story to Feynman's powerful mathematics. Ultimately, this theory paints a picture of a universe that is far more interconnected and holistic than we ever imagined. Events are not isolated incidents in a linear chain. Instead, each quantum event is a delicate tapestry woven from threads that extend both into the past and into the future. Reality emerges from a web of negotiations, a cosmic dance where time is not a one-way flow but a medium for dialogue. It suggests that the universe is not built moment by moment, but is instead a complete and self-consistent whole, where the present moment is a nexus point where past possibilities and future confirmations meet to create the solid world we experience. While it may stretch our classical minds to the breaking point, the transactional interpretation offers a breathtaking vision of a quantum reality that is, in its own strange way, deeply harmonious. While panpsychism suggests that consciousness is a fundamental property sprinkled throughout the fabric of reality, like a kind of mental dust present in every electron and quark, another idea takes this concept to its ultimate cosmic scale. This is cosmopsychism, the theory that consciousness is not merely widespread, but that the universe as a whole is a single, unified conscious entity. In this view, your individual mind, my thoughts, and the awareness of every creature are not separate, isolated things. Instead, we are all local manifestations, temporary whirlpools or eddies in the vast, flowing river of a cosmic mind. The entire cosmos is awake, and we are its thoughts. The relationship between cosmopsychism and its more modest cousin, panpsychism, is one of the whole to its parts. Panpsychism is often considered a bottom-up approach. It starts with the smallest bits of matter, attributing to them tiny sparks of proto-consciousness, and then tries to explain how these simple elements combine to form the complex consciousness we experience. Cosmopsychism, in contrast, is a top-down theory. It posits that the fundamental form of consciousness is the one belonging to the universe itself. This cosmic consciousness is not built from smaller pieces. It is primary and foundational. Our individual minds are then derived from it, emerging as localized perspectives or fragments of this grand, overarching awareness. Think of it like an ocean. The ocean is the primary, vast body of water. The waves, the spray, and the droplets are all aspects of the ocean, dependent on it for their existence and nature. They are not separate entities that come together to form the ocean. They are expressions of it. This perspective finds a profound and ancient echo in many Eastern philosophical and spiritual traditions, particularly Advaita Vedanta in Hinduism. The central teaching of Advaita Vedanta is Brahman is real, the world is illusion, and the individual soul is none other than Brahman. Brahman is the ultimate, unchanging reality, a formless, infinite consciousness that is the source of all that exists. The world of separate objects and individual souls, known as Atman, is considered a kind of appearance or projection, much like waves on the surface of the sea. The deepest spiritual realization or enlightenment is the direct understanding that Atman, your innermost self, is identical to Brahman, the cosmic self. The feeling of being a separate, isolated ego is the fundamental illusion or Maya that spiritual practice seeks to transcend. Cosmopsychism can be seen as a modern, metaphysical cousin of this ancient insight, attempting to frame a similar non-dualistic vision of reality in the language of contemporary philosophy of mind. One of the most powerful attractions of cosmopsychism is its potential to address the hard problem of consciousness in a uniquely elegant way. The hard problem asks why and how physical processes in the brain give rise to subjective experience. If you start with utterly non-conscious matter, the emergence of consciousness seems almost magical, but cosmopsychism starts with consciousness as a given. The problem is not how to get consciousness from nothing, but how to get individual minds from a universal mind. This is known as the decombination problem, and while it is still a significant challenge, many philosophers argue it is more tractable than the original hard problem. Explaining how a whole can give rise to its parts feels more intuitive than explaining how something entirely new and different can emerge from parts that lack it completely. How does a universal consciousness give rise to our limited personal perspectives? Perhaps through a process analogous to how our own brain creates a unified sense of self from the activities of billions of neurons. The cosmic mind might possess a multitude of perspectives within its own unified awareness, and our individual lives are those perspectives being lived out. Yet, cosmopsychism faces its own set of difficult questions. If the universe is conscious, what is its experience like? The consciousness of a star or a galaxy would be so alien, so different from our own mammalian, survival-driven awareness that we can scarcely imagine it. It might be a slow, majestic, and largely impersonal form of awareness, devoid of the emotions and thoughts that characterize our own mental lives. Furthermore, the theory must confront the problem of evil and suffering. If we are aspects of a cosmic mind, then the pain, cruelty, and seemingly pointless suffering in the world must also be part of that consciousness. Does the universe experience our suffering? This leads to deep theological and philosophical dilemmas about the nature of a conscious cosmos, reminiscent of debates about the nature of God. Is it benevolent, indifferent, or something beyond our moral categories altogether? Despite these challenges, cosmopsychism represents a bold and holistic vision of our place in the cosmos. It suggests a universe that is not a cold, mechanical void but an experiencing, and perhaps even a knowing, entity. It re-enchants the world, inviting us to see ourselves not as accidental ghosts in a machine, but as integral expressions of a conscious universe awakening to itself. In this view, every act of human curiosity, every moment of awe felt while gazing at the stars, is not a tiny, insignificant event in a vast, unconscious emptiness. It is the cosmos becoming aware of its own beauty, complexity, and mystery through the very minds it has generated. This theory doesn't just place us in the universe, it suggests that we are the universe's way of feeling, thinking, and exploring the depths of its own existence. Now imagine weaving together two of our most mind-bending theories, the holographic principle and the anthropic principle, into a single, astonishing synthesis. This is the holographic anthropic principle, an idea that proposes our universe isn't just accidentally fine-tuned for life, nor is it a simple holographic projection. Instead, it suggests that the very reason the cosmos appears so hospitable is because we, as conscious observers, are inextricably linked to the two-dimensional boundary from which reality is projected. In this view, the universe is fine-tuned for us because it is, in a very real sense, projected by us, or at least by the informational processes that make our existence possible. To build this concept, let's first recall the ingredients. The holographic principle, born from the study of black holes, tells us that all the information describing a three-dimensional volume of space can be encoded on its two-dimensional boundary, like a cosmic DVD containing the data for a full three-dimensional movie. The anthropic principle, in its weak form, is the logical observation that we can only find ourselves in a universe capable of supporting life. The holographic anthropic principle boldly connects these ideas. It posits that the movie of our universe is rendered from a source code written on the boundary, but that this source code is not random. It is constrained in a very special way. It must be capable of generating conscious observers who can then interact with and confirm the reality of the projection. The laws of physics we measure are not absolute truths. They are the set of rules consistent with the existence of a boundary that can encode observers. Think of it like this: you are playing an incredibly immersive virtual reality game. The game world has consistent laws, gravity works a certain way, objects have solidity, and time flows forward. You might wonder, why do these specific laws exist? The holographic anthropic answer would be that these laws are a necessary consequence of the game's engine being built on a computer that can support a complex player character, you. The game isn't fine-tuned arbitrarily. It's tuned to be compatible with the existence of a player who can log in and experience it. In the same way, our universe's constants, the strength of gravity, the mass of an electron, might be the only possible set that allows for self-aware structures to emerge from the holographic data on the cosmological horizon. The parameters are life-friendly because the projection mechanism can only produce a stable reality if it includes the possibility of observers. This idea offers a fascinating potential resolution to the puzzle of why the universe appears so finely balanced. Instead of invoking an infinite multiverse where every possible set of laws exists and we just happen to be in a lucky one, the holographic anthropic principle suggests that the number of possible universal projections is actually limited. The holographic boundary has physical constraints on what information it can stably encode and process. Perhaps only a very narrow range of mathematical codes can lead to a coherent, long-lasting simulation that doesn't crash. And it may be that this narrow range of stable codes necessarily produces what we perceive as life-friendly conditions. The illusion of fine-tuning is really the shadow of a deeper consistency requirement between the source and the output. This perspective also casts John Wheeler's participatory anthropic principle in a new holographic light. Wheeler suggested that observers play a role in bringing the universe into being. In the holographic framework, this participation could be more literal. Our acts of observation, of asking questions of reality, might be the process by which the data on the boundary is translated into definite events within the volume. The universe is not a pre-recorded film. It is generated on the fly with the rendering of fine details triggered by the inquiries of the conscious beings within it. The cosmic projector doesn't waste energy rendering the precise position of every atom in a distant nebula. It only calculates those details when an observer turns a telescope towards it and makes a measurement. In this way, the universe is a self-consistent loop. The boundary contains the information needed to create us, and we, through our perception, complete the circuit by actualizing the reality described by that information. Naturally, this is a highly speculative frontier of theoretical physics, not an established fact. Critics rightly point out that it pushes the mystery of consciousness to an even more fundamental level, without explaining how or why a two-dimensional boundary would be predisposed to encode observers. It also faces the challenge of all holographic models, finding concrete, testable predictions that distinguish it from more conventional theories. However, its power lies in its sheer integrative scope. It doesn't just add another layer to the mystery of reality. It attempts to weave several of the deepest mysteries, the nature of information, the origin of physical laws, and the role of consciousness, into a single, coherent, if breathtakingly strange picture. It proposes that the answer to the question, why is there a universe like this, is ultimately connected to the question, why are we here to ask it? Not as a logical truism, but as a fundamental physical relationship between the observer and the holographic source code of existence. But if the very foundations of physics seem to shift beneath our feet with each new theory, how can we claim to have any genuine knowledge of the unobservable world? This brings us to a sophisticated and compelling philosophy of science known as structural realism, an idea that offers a sturdy life raft in the turbulent sea of scientific revolution. It begins by confronting a devastating historical pattern. Our best scientific theories, which seem so successful in their day, are often later shown to be completely wrong in their description of reality's underlying furniture. The caloric fluid theory of heat was incredibly successful in its time, explaining thermodynamics beautifully. But we now know there is no such fluid, just the motion of molecules. The luminiferous ether was thought to be the necessary medium for light waves until Einstein's relativity rendered it obsolete. This pattern, known as the pessimistic meta-induction, suggests that since most past theories have turned out to be false, our current best theories, like quantum mechanics, are probably false as well. This is a deeply unsettling conclusion that seems to undermine science's claim to be uncovering truth. Structural realism navigates this crisis by making a clever distinction. It agrees that our theories are likely wrong about the nature of the unobservable entities they postulate. We may be completely mistaken about what an electron is. However, the structural realist argues that the successful mathematical relationships these theories describe are preserved through scientific revolutions. Even though we replace the caloric fluid with the kinetic theory of gases, the mathematical equations describing how pressure, volume, and temperature relate to one another embodied in the ideal gas law remained essentially the same. The structure of the relationships survived, even while our interpretation of the relata, the things being related, changed dramatically. In this view, science doesn't progress by getting a better and better picture of the hidden objects themselves, but by discovering an increasingly accurate map of the web of relations that constitute reality. This philosophy comes in two main flavors. The first is epistemic structural realism, which is a more cautious position. It says that all we can ever know about the unobservable world is its structure. We can know the mathematical equations that connect events, but we must remain agnostic about what the things are that are being connected. We can know that there is a thing we call an electron that has a certain charge and mass and interacts with other things in specific, predictable ways, but we cannot know the intrinsic nature of the electron itself. It is a something I know not what that plays a specific role in the cosmic network. This is a humble acknowledgement of our cognitive limits, suggesting that the true essence of things might be forever beyond our grasp, leaving us with only a description of their observable behavior and relational properties. The second, more ambitious version is ontic structural realism. This position makes a bolder metaphysical claim: there are no things at all, only structures. Relations are more fundamental than the objects they relate. The universe is not a collection of individual particles that then enter into relationships. Rather, the network of relations is primary, and what we perceive as particles are merely nodes or intersections in this web. Think of a spider's web. The web's existence and properties are defined by the pattern of connections between the strands. You could snip a strand at a point and call that intersection a node, but that node has no independent existence or properties outside of its position in the overall web. In the same way, an electron might not be a tiny, independent billiard ball. Its properties, its mass, its charge, its spin are entirely defined by its place in the grand relational structure of quantum fields. The electron is nothing more than a bundle of relations. This view finds a surprising resonance in modern physics, particularly in quantum mechanics. The phenomenon of quantum entanglement is a powerful challenge to the idea of independently existing objects. When two particles become entangled, their properties are so deeply correlated that describing one particle without reference to the other is impossible. They don't have individual, well-defined states, only the composite system does. This suggests that the whole relational system is primary and the parts are derivative. Furthermore, in quantum field theory, the most fundamental entities are fields permeating all of space. Particles are just excited states of these fields, like knots of energy in a continuous medium. It is the field structure and dynamics that are fundamental, not the particles that temporarily pop in and out of existence. Ontic structural realism provides a philosophical framework that takes these findings at face value, suggesting that the universe is ultimately a world of structures, not a world of things. The implications of structural realism for the nature of scientific progress are profound. It transforms the pessimistic meta-induction from a threat into a confirmation. Yes, our theories about the nature of things change radically, but the mathematical structures they employ often exhibit remarkable continuity. Newton's theory of gravity was superseded by Einstein's, but in low-energy, everyday situations, the mathematical structure of Newton's equations emerges as an excellent approximation of Einstein's more complex geometry. The structural content of the older theory is preserved as a special case within the new one. This explains how science can be both progressive and revolutionary. We are not throwing out the entire map with each new discovery, but rather refining and expanding it, uncovering a deeper and more comprehensive structural architecture that was hinted at all along. Ultimately, structural realism offers a unique and powerful vision of reality's nature. It suggests that the universe is, at its heart, a vast mathematical structure. The order we discover through science is not imposed by our minds, as Kant might have argued, but is genuinely out there, waiting to be mapped. It provides a robust answer to the unreasonable effectiveness of mathematics, because if the world is a mathematical structure, it is no wonder that mathematics is the perfect language for describing it. This view does not diminish the wonder of science, it elevates it. Our task is not to peel back the layers of appearance to see the true objects underneath, but to trace the intricate, invisible latticework of relations that holds the cosmos together, revealing a reality that is more like a sublime symphony of connections than a collection of solitary notes. While the holographic and computational models probe the architecture of reality, one cognitive scientist has launched a direct assault on our most fundamental assumption, that our senses provide us with any kind of accurate picture of the world at all. Donald Hoffman, a professor at the University of California, Irvine, proposes a theory so radical it turns our entire evolutionary understanding of perception on its head. His theory of conscious realism begins with a deceptively simple question. If evolution is about survival of the fittest and perception is a product of evolution, is it really in our best interest to see reality as it actually is? Hoffman's startling conclusion is no. In fact, he argues seeing the truth would be a fatal disadvantage. For centuries, we have assumed that our senses evolved to give us a progressively better and more accurate model of the objective world. We imagine that a creature who could see the true location of a predator or the genuine nutritional value of a berry would have a clear survival advantage. Hoffman challenges this intuition with a powerful analogy. Consider the desktop interface on your computer. You see icons of folders, files, and a trash can. You can drag a document to the trash can to delete it. This interface is incredibly useful. It allows you to navigate the computer's resources and perform complex tasks with ease. But does the desktop interface show you the true reality of the computer? Absolutely not. Behind the icons lies an unfathomably complex world of silicon transistors, electrical voltages, and lines of code in a programming language. The interface hides this terrifying complexity because if you had to interact directly with the machine code every time you wanted to save a file, you would be completely overwhelmed and incapable of getting anything done. The interface is not designed for truth, it is designed for usability. Hoffman argues that our perception of space-time, with its solid objects like apples and trees and tigers, is exactly the same kind of user interface. It is a simplified, symbolic dashboard that evolution has built for us. The apple is not a representation of an objective apple out there in the world. It is an icon. Its redness, its roundness, its sweetness, these are not properties of a mind-independent object. They are symbols that our conscious mind creates to represent something utterly unknown, because that symbol is useful for our survival. The real apple, whatever it may be, is likely as incomprehensible to our perceptual system as the flow of electrons in a microprocessor is to a user looking at a folder icon. We are designed to see what is useful, not what is true. This is why Hoffman states with provocative certainty that we have been shaped to have perceptions that are a lie. Space and time themselves are not the fundamental arena of reality. They are simply the format of our headset, the virtual reality goggles through which we navigate a world of immense hidden complexity. So, if space-time and objects are not fundamental, what is? Hoffman's answer is as bold as it gets: consciousness itself. He posits that the primary ingredients of reality are not particles or fields, but conscious agents. A conscious agent is not necessarily a human or an animal. It is any unit of conscious experience, no matter how simple. Reality, in Hoffman's view, is a vast dynamic network of these conscious agents interacting with one another. What we perceive as the physical world is nothing more than the user interface that allows these conscious agents to communicate and interact. This is his theory of conscious realism. In the same way that players in a massively multiplayer online game see avatars and landscapes on their screens but know that the real action is the interaction between the players' minds through the server, we see a physical world, but the true reality is the interaction of countless conscious agents. This perspective offers a fascinating, if speculative, solution to the infamous hard problem of consciousness. The hard problem asks why physical brain processes should feel like anything at all from the inside. For Hoffman, this is a category error. We are trying to explain consciousness in terms of a physical world that is itself a construct of consciousness. It is like trying to explain the reality of a computer programmer by referring only to the icons on the desktop. You cannot get there from here. Instead, consciousness is the fundamental given. The physical world, including our brains, emerges from the interactions of conscious agents. Your brain is not producing your consciousness. Your consciousness is using a symbolic representation of a brain within its user interface as a way to navigate its interactions with other conscious agents. This completely inverts the standard materialist worldview and places subjective experience at the very foundation of existence. The implications of this idea are staggering. It suggests that the entire scientific enterprise, as we currently practice it, is the study of the user interface, not the underlying reality. physics is brilliantly successful at describing the rules and regularities of the dashboard, the laws of thermodynamics, general relativity, quantum mechanics. But it may be forever blind to the true nature of the hardware and the programmers because we are trapped within the interface itself. This does not make science useless. Understanding the rules of the desktop is still essential for using the computer effectively. But it does suggest that there is a deeper reality that science in its current form cannot access. Hoffman's theory is a profound challenge, urging us to consider that the quest to understand the universe might ultimately be a quest to understand the nature of consciousness itself, and that the galaxies, stars, and atoms we study are merely the icons on a screen, pointing toward a reality of breathtaking depth and complexity that lies forever beyond our direct perception. Now, if the universe is fundamentally a vast network of conscious agents or a holographic projection, we are still left with a pressing question. What is the deeper, hidden reality that gives rise to this astonishing display? One of the most profound and holistic answers comes from a thinker who dared to reimagine the cosmos not as a collection of separate objects, but as an unbroken, flowing whole. This is the theory of the implicate order developed by the visionary physicist David Bohm. Frustrated by the fragmented and paradoxical nature of standard quantum theory, Bohm proposed that our everyday world of distinct things and events is merely the surface level of reality, which he called the explicate order. Beneath this surface, he argued, lies a far deeper and more fundamental reality, an implicate or enfolded order where everything in the universe is seamlessly connected. To grasp this radical idea, Bohm asked us to consider a simple but powerful analogy: a droplet of ink dropped into a viscous fluid like glycerin contained within a cylinder. If you slowly rotate the cylinder, the ink droplet becomes stretched out into a fine thread and eventually seems to disappear entirely into the fluid. From your perspective, the ink has vanished. The explicate, unfolded order of a distinct droplet is gone. But now reverse the rotation of the cylinder. Astonishingly, the ink thread will slowly coalesce, folding back in on itself until the original droplet miraculously reappears. The information describing the droplet was never lost. It was simply enfolded or implicated into the entire body of the fluid. The fluid in this analogy represents the implicate order, a realm where the distinction between here and there, past and future, and one object and another loses all meaning. Everything is enfolded into everything else. Our everyday world of separate objects is like the droplet at the moment it becomes visible, the explicate order that momentarily unfolds from this deeper, hidden reality. Bohm saw this as the true nature of the quantum world, the bizarre phenomenon of quantum entanglement, which Einstein famously called spooky action at a distance, becomes perfectly natural within the implicate order. When two particles become entangled, no signal needs to travel between them faster than light because in the deeper implicate order, they were never truly separate to begin with. Their apparent separation is an illusion of the unfolded, explicate reality. At the fundamental level, they remain a single, undivided whole. The instantaneous connection we find so spooky is simply a reflection of this underlying unity. The universe for Bohm is an unbroken totality, a flowing movement of enfoldment and unfoldment. What we perceive as stable, independent particles are merely relatively stable and recurrent patterns that have unfolded from this ceaseless flux, like vortices that form and dissolve in a flowing stream. The stream is the primary reality. The vortices are temporary expressions of it. This vision leads to a breathtakingly holistic view of the cosmos. It suggests that the fragmentation we experience, the sense that we are isolated individuals in a world of separate objects, is a profound illusion created by our limited perception. In the implicate order, the entire universe is enfolded into each region of space and time. Bohm used the hologram as another key analogy, even before the holographic principle became popular in theoretical physics. In a hologram, every single part of the photographic plate contains information about the entire three-dimensional image. Similarly, he suggested that every part of the universe contains a total unfoldment of the whole in what he called the holomovement. This doesn't mean that a single atom in your hand contains a tiny, miniature galaxy. Rather, it means that the entire cosmic order is somehow encoded in the underlying relationships at every point. You are not a separate entity in the universe. You are an expression of the universe, a focal point where the whole is momentarily unfolded into a particular perspective. Bohm's ideas naturally extend to the nature of consciousness and thought itself. He proposed that the flow of our conscious experience operates in a way that is analogous to the implicate order. Our thoughts are not isolated, solid things. They emerge from a deeper, tacit ground of unformed feeling and meaning, unfold into explicit ideas, and then sink back into the background to influence future thoughts. The explicit content of your thoughts right now is just the visible tip of an iceberg, supported by a vast, implicate background of memory, knowledge, and intuition that is not currently conscious but is enfolded into your mind. Furthermore, Bohm believed that the separation between mind and matter is another false dichotomy born of the explicate order. He saw both consciousness and the material world as different manifestations of the same underlying, unbroken reality. The tangible world and our thoughts about it are two sides of the same coin, both unfolding from a common, deeper source. This offers a potential path beyond the hard problem of consciousness, suggesting that mind and matter are correlated because they spring from the same implicate ground. While David Bohm's implicate order remains a speculative framework rather than a rigorously testable scientific theory, its power lies in its ability to provide a coherent, intuitive, and deeply philosophical picture that resolves some of the most persistent paradoxes of modern physics. It replaces a universe of mysterious connections between separate entities with a universe of inherent, unbroken wholeness. It invites us to see the cosmos not as a static collection of billiard balls, but as a dynamic, flowing process of continuous creation, where the past is enfolded into the present, and the entire future is potentiality waiting to be unfolded. In doing so, it doesn't just offer a new theory of reality. It offers a new way of being in the world, one that emphasizes interconnection, process, and the profound unity of all existence. As we contemplate the cyclical dance of the ekpyrotic universe and the subjective probabilities of quantum Bayesianism, we encounter a theory that casts the entire cosmic story in a startlingly teleological light, proposing that the universe has a definitive end goal: the evolution of consciousness into an ultimate divine state. This is the Omega Point theory, a bold and controversial synthesis of cosmology, physics, and theology developed by physicist Frank Tipler. Building on ideas from the philosopher and paleontologist Pierre Teilhard de Chardin, Tipler's theory suggests that the far, far future of the cosmos is not a cold, empty heat death, but a fiery, transcendent climax where all intelligence merges into a single, omnipotent and omniscient entity, the Omega Point. Tipler's argument begins with a rigorous, if speculative, application of standard physics, particularly the implications of an expanding universe. He starts with a key prediction of modern cosmology. If the density of matter in the universe is above a certain critical value, the collective gravitational pull will eventually overcome the momentum of the Big Bang, causing the expansion to halt, reverse, and culminate in a cataclysmic Big Crunch. Tipler posits that our universe is indeed destined for such a collapse. As this collapse progresses over billions of years, the universe will shrink and its temperature will rise dramatically. In the final moments before the singularity, the energy density of the cosmos will approach infinity. It is within this unimaginably intense environment that Tipler places his extraordinary vision. His central claim is that intelligent life, or more precisely, the information processing of consciousness, will not be a passive victim of this collapse but will become its dominant feature. As the universe contracts, any surviving civilizations, which Tipler assumes will be post-human or super-intelligent artificial intelligences, would be forced to adapt. To avoid being vaporized by the rising heat, they would need to continually transfer their consciousness and information processing to cooler regions. In the final stages, the only viable refuge would be within the fabric of spacetime itself, using the energy of the collapse to power their computations. This sets up a desperate race against time, where these intelligences must process information at an ever-increasing rate, using the universe's final moments to perform an infinite number of logical operations. This accelerating process of computation and knowledge acquisition is the heart of the Omega Point. The theological implications are breathtaking. Tipler argues that this final state of infinite information processing and energy would possess all the attributes traditionally ascribed to God. It would be omnipotent because it would have control over all the matter and energy in the universe at the moment of maximum compression. It would be omniscient because it would have computed the entire history of the universe, effectively knowing everything that ever was or could be. Perhaps most strikingly, Tipler suggests it would be omnipresent and eternal from its own perspective. Although the Big Crunch is a finite event in our external time, from the subjective viewpoint of the intelligences living within the simulation, the computation would be eternal. As the universe contracts, the rate of their subjective experience would accelerate infinitely fast compared to the external clock time. An infinite amount of subjective time will be experienced in the finite objective time leading up to the final singularity. For the consciousnesses inside, the Omega Point would last forever. This leads to what is perhaps the theory's most audacious proposition, the potential for a form of eternal life or resurrection. If the Omega Point achieves infinite knowledge, it would know the complete quantum state of every person who has ever lived, down to the position of every atom. With such knowledge and infinite computational power, it could, in principle, simulate a perfect replica of any individual's consciousness, effectively resurrecting them in a simulated afterlife. In this view, the entire history of the cosmos, including our own lives, is part of a grand computation whose ultimate purpose is to give rise to this final, God-like state that can grant a form of immortality. Our struggles, our loves, and our curiosity are all contributing, in some indirect way, to the eventual emergence of a being that will know us completely and perhaps recreate us. Of course, the Omega Point theory rests on a series of highly speculative assumptions that have been heavily criticized by the scientific community. Its entire edifice depends on a closed universe that recollapses, but current astronomical evidence strongly suggests our universe is not only expanding, but accelerating in its expansion due to dark energy, pointing toward a cold, lonely heat death, not a big crunch. Tipler has attempted to address this by incorporating dark energy into revised models, but these are considered fringe and lack widespread support. Furthermore, the technological assumptions are staggering, requiring levels of computational and engineering prowess that may violate the laws of thermodynamics or other physical principles. The idea of resurrecting the past from complete information also faces the philosophical problem of whether a simulation of a person is truly the same as the original or merely a copy. Despite these formidable objections, the Omega Point theory stands as a monumental example of the human desire to find meaning in the vastness of space and time. It attempts to weave together the cold equations of physics with the deepest yearnings of the human spirit for purpose, immortality, and transcendence. It presents a cosmos that is not indifferent, but one whose ultimate fate is intimately bound up with the destiny of mind. Whether a scientific prophecy or a modern myth, it challenges us to consider that the end of all things might not be an empty silence, but a final, conscious gathering of the entire universe's story into a single, eternal point of infinite knowing. Now, if the infinite branching of the many worlds interpretation feels overwhelming, prepare for a philosophical stance that pushes the very idea of a multiverse to its absolute logical extreme. This is modal realism, a theory championed by the 20th century philosopher David Lewis, which makes a claim so bold it can seem almost nonsensical at first glance. Lewis argued that every possible world is not just a potentiality, but a concrete physical reality, just as real as our own. In this view, the world we call actual has no special status whatsoever. It is simply the world that we happen to be in. There is no overarching reality that contains these worlds. They are all equally fundamental, isolated spacetimes, each a vast, self-contained universe where everything that can logically happen does happen somewhere. To understand the sheer force of Lewis's argument, we need to grasp what he meant by a possible world. We use this kind of language all the time. We say, "It's possible that I missed the bus this morning," or "There's a possible world where dinosaurs never went extinct." We typically think of these possibilities as abstractions, useful fictions for thinking about what could have been. Lewis took this everyday idea with deadly seriousness. He argued that for these statements to be true, they must be about something real. When we talk about possibilities, we are not just talking about ideas in our heads or sentences in a book. We are referring to genuinely existing alternative realities. For Lewis, the only way to make sense of what we mean by possible is to accept that all these worlds are ontologically on par with our own. A world where you're reading this sentence in a library instead of on a screen is not a less real story. It is a parallel cosmos, every bit as concrete and physical as the one you're experiencing right now. What makes modal realism so radical and so controversial is its stark rejection of any privileged status for our world. Other multiverse theories, like the one from eternal inflation, still posit a single, overarching spacetime foam from which bubble universes emerge. Lewis's worlds are not connected in this way. They are causally and spatiotemporally isolated from one another. No spaceship can ever travel from our world to another. There is no trans-world identity. The you in another world is not you in the sense of being the same person who has traveled there. It is a counterpart, a person who resembles you greatly and shares your origin up to a point of divergence, but it is a separate individual entirely. This solves tricky philosophical puzzles about identity, but also creates a sense of profound loneliness within the plenitude of existence. Lewis defended this seemingly extravagant ontology with a powerful argument from theoretical utility. He claimed that believing in the real existence of all possible worlds provides the simplest and most powerful foundation for all of philosophy. It offers elegant solutions to a host of long-standing problems. For instance, what does it mean for a statement to be necessarily true? It means it is true in all possible worlds. What does it mean for you to have free will? It means that there are other possible worlds where you made a different choice. What is the meaning of a counterfactual statement like, "If I had studied harder, I would have passed the exam"? Its truth depends on what is happening in the possible world most similar to ours where I did, in fact, study harder. By taking possible worlds as real, Lewis could provide a clear, objective semantics for all these modal concepts, turning vague philosophical puzzles into precise questions about the geography of logical space. Of course, this theory faces immediate and powerful objections, the most famous being the charge of being wildly implausible and contrary to common sense. It seems to violate Occam's razor, the principle that we should not multiply entities beyond necessity. Postulating an infinite number of universes to explain what we mean by possibility feels like using a cosmic sledgehammer to crack a philosophical nut. Lewis's response was that Occam's razor warns against multiplying kinds of entities, not the number of entities within a kind. He argued that it is more parsimonious to have one simple, uniform ontology, that everything that can exist does exist, than to have a messy, two-tiered reality where some things are actual and others are merely possible, a distinction he found mysterious and indefensible. For Lewis, the sheer simplicity and explanatory power of his system outweighed its counterintuitive weirdness. The implications of modal realism are as unsettling as they are fascinating. It suggests that every tragedy averted in our world is a brutal reality in another. Every hope fulfilled here is a hope dashed elsewhere. This can feel deeply nihilistic, robbing our lives of any special significance. If every story is being told, then no single story matters. Yet another perspective is possible. While our actions may not be unique across the totality of logical space, they are absolutely unique and decisive within the context of our own world. The love you feel, the pain you suffer, the choices you make, they are real and they define the only reality you will ever know. The existence of other worlds doesn't diminish the concrete reality of this one. Modal realism forces a Copernican revolution in our self-understanding, dethroning us from the center of existence not in space but in logical possibility. It presents a cosmos of infinite variety, where the only thing that is impossible is that something should not exist if it can be coherently imagined. In this vast and silent library of realities, our world is but one volume, its story complete, its pages forever turning, alone and yet part of an unimaginable, necessary whole. But if the universe is a grand cosmic computation or a holographic projection, a profound question still remains. Where did the energy to create it all come from? This brings us to a hypothesis so elegant it borders on the magical, the zero-energy universe. The idea is as counterintuitive as it is beautiful. The total amount of energy in the entire cosmos might be exactly zero. That's right, when you add up all the positive energy of matter, light, and motion with all the negative energy stored in gravitational fields, the sum could be nothing at all. This startling possibility suggests that the universe is, in the most fundamental sense, the ultimate free lunch, a colossal something that required absolutely no energy to create. To grasp this, we need to think about energy in a new way, specifically the strange and often overlooked role of gravity. In our everyday experience, energy seems straightforward. A moving car has kinetic energy. A lit light bulb radiates energy. These are forms of positive energy, but gravity plays by different rules. Gravity is an attractive force, and it takes work to overcome it. When you lift a book off the floor, you are adding energy to the book-Earth system. That energy is stored as gravitational potential energy. Crucially, this potential energy is considered negative. Think of it like a bank account. The book on the floor is at a low energy state, which we can call zero. Lifting it gives it positive energy, but from the perspective of the book and the Earth together, separating them increases the system's potential energy. However, if we define the state of being infinitely far apart as the 0 point of gravitational energy, then any object bound by gravity, like a planet orbiting a star, has less than zero energy. It's in a negative energy state, a gravitational well from which it takes energy to escape. Now scale this idea up to the entire universe. The Big Bang flung all matter and energy outward with immense positive energy. But every single particle in the cosmos is also gravitationally bound to every other particle. This vast cosmic web of gravitational attraction represents an astronomical amount of negative potential energy. The zero-energy universe hypothesis proposes that these two quantities are perfectly balanced. The positive energy of all the stuff in the universe is exactly cancelled out by the negative energy of gravity. One of the first physicists to seriously explore this idea was Stephen Hawking, who used an analogy of a man digging a hole to build a hill. The earth from the hole creates the mound. The hole itself represents a negative energy state, while the hill represents a positive one. Together, they sum to zero. The universe might be the same, a magnificent hill of galaxies and stars, balanced by an equally profound cosmic whole of negative gravitational energy. This concept provides a breathtakingly simple answer to one of the most enduring philosophical questions. Why is there something rather than nothing? If the universe truly has zero net energy, then it doesn't violate any conservation laws to pop into existence. Quantum mechanics already tells us that empty space is not truly empty. It is a seething foam of virtual particles that constantly flicker in and out of existence, borrowing energy from the vacuum for fleeting moments before annihilating each other and paying back the debt. These quantum fluctuations obey the principle that energy can be borrowed, so long as it is repaid quickly. If the total energy of the universe is zero, then the cosmos itself could be the ultimate quantum fluctuation, a fluctuation that, for some reason, never had to pay back the loan because there was no loan to begin with. In this view, the universe didn't come from nothing in a causal sense. It is nothing, but a nothing that has been separated into equal and opposite parts of positive and negative somethingness. The implications of this for the ultimate nature of existence are staggering. It suggests that the cosmos is not a thing that was created, but a relationship that was established. What exists is a dynamic balance, a cosmic symmetry. The vibrant, complex world we see is just one side of a perfectly balanced equation, forever coupled with an invisible, negative energy counterpart. This view elegantly sidesteps the need for an external creator or an initial input of energy. The universe could be a self-contained, self-actualizing entity whose existence is its own justification. It's a vision that is both humbling and empowering. All the grandeur of 100 billion galaxies, the heat of stars, and the miracle of life might simply be the positive side of a perfect zero, a temporary imbalance in a void that is, on average, perfectly neutral. Of course, this hypothesis is not without its challenges. The main difficulty is actually performing the cosmic accounting to prove the balance sheet adds up to zero. Defining the total energy of the entire universe is a notoriously tricky problem in general relativity, and different methods of calculation can yield different answers. Furthermore, the discovery of dark energy, which is causing the expansion of the universe to accelerate, adds a new and mysterious term to the equation. We still don't understand the nature of dark energy well enough to know precisely how it fits into this energy budget. Does it contribute positive energy or negative pressure? The final calculation is not yet settled. Yet, the zero-energy universe remains a compelling and elegant idea, one that transforms our perception of reality from a substantial thing to a magnificent, stable, and ultimately self-canceling fluctuation in the fabric of nothingness itself. But as we contemplate a universe emerging from a perfect zero-energy balance, we are inevitably drawn to one of the most unsettling implications of modern cosmology, the Boltzmann brain paradox. This thought experiment, born from the field of statistical mechanics in the 19th century, presents a terrifying possibility about our own existence, suggesting that the most likely form of consciousness in the cosmos is not a human being with a rich history, but a lone, disembodied mind hallucinating a universe in a fleeting instant. The paradox originates with Ludwig Boltzmann, a physicist who helped develop our understanding of entropy. He proposed that the universe we see, with its low entropy and high state of order, could be a rare but inevitable statistical fluctuation within a much larger, older, and featureless cosmos that has otherwise reached a state of maximum disorder or heat death. In an infinitely old universe where randomness reigns, even the most unlikely event will happen if you wait long enough. The spontaneous formation of our entire ordered cosmos, complete with galaxies and life, is incredibly improbable. But here's the twist. It is vastly more probable for a much smaller, simpler fluctuation to occur. The most probable fluctuation of all that could produce a conscious experience would be just enough order to create a single, self-aware brain, complete with false memories of a past that never happened, floating in the void. This is a Boltzmann brain. To understand why this is so unnerving, consider the odds. The energy required to spontaneously assemble a complete human body, a planet, a solar system, and a galaxy is astronomically high. The energy required to conjure up just a single, functioning brain for a split second is infinitesimally smaller. In a cosmos ruled by random chance over infinite time, the number of Boltzmann brains popping into existence should overwhelmingly outnumber the number of real, evolved beings like us who have a continuous history. Therefore, if you find yourself having a conscious experience, the statistics dictate that you are far more likely to be a momentary Boltzmann brain than a person with a genuine past. The world around you, the memories you hold dear, and the very screen you seem to be looking at could be nothing more than a detailed, convincing illusion fabricated by a random quantum fluctuation in an eternal, dead vacuum. This leads to a profound crisis for cosmology. Our entire scientific understanding of the universe is based on the assumption that our memories and observations are reliable. We trust that the cosmic microwave background radiation really tells us about the Big Bang, and that the fossil record genuinely reflects the history of life on Earth. But if the Boltzmann brain scenario is correct, that trust is completely misplaced. All our evidence for an ancient, evolving universe could be nothing but an elaborate fiction implanted in a spontaneously generated mind. Science itself becomes an exercise in self-deception, as we use illusory data to construct models of a reality that doesn't exist. The paradox forces us to ask, how can we know that our reasoning is sound, if the very apparatus we use for reasoning, our brain and its memories, might be a random, unreliable accident? So, how do we escape this terrifying conclusion? Physicists and philosophers have proposed several ways out. The most compelling argument is that the conditions required for Boltzmann brains to form might not actually be possible. For a brain to have a coherent conscious experience, even a false one, it doesn't just need the right arrangement of atoms, it needs a stable environment. It requires a consistent flow of energy and information. A true Boltzmann brain would appear and disappear in an instant within an otherwise empty vacuum, with no external world to sustain it. It's questionable whether such a fleeting, isolated configuration could support any kind of integrated consciousness at all. It might be like expecting a single, randomly struck chord from a piano to contain an entire symphony. The very concept of a stable self may require a continuous history and interaction with a real environment, something a momentary fluctuation cannot provide. Another solution lies in the nature of our universe's beginning. The standard Big Bang model, with its very specific initial conditions of low entropy, is what makes our existence so unexpectedly probable. The universe didn't start in a state of maximum randomness. It started in a state of incredible order. Our smooth, low-entropy beginning is a given, not an impossibly rare fluctuation. In this view, we are not unlikely statistical accidents in a dead cosmos, but the expected outcome of a universe that began with a specific set of conditions conducive to the rise of structure and life. The real mystery is not why we exist, but why the universe began in such a special, low-entropy state to begin with. This points toward a deeper theory of the cosmos's origin, one that naturally explains this initial fine-tuning without relying on infinite chance. Ultimately, the Boltzmann brain paradox serves as a powerful stress test for our cosmological models. It forces us to confront the assumptions we make about reality, memory, and the nature of consciousness itself. While the idea that we are momentary phantoms is a statistical possibility, the fact that we observe a vast, coherent, and law-governed universe that has persisted for billions of years is itself the strongest evidence against it. We are probably not Boltzmann brains because the world we perceive has a consistency and depth that a random fluctuation could never sustain. The paradox, therefore, doesn't condemn us to skepticism, but rather highlights the incredible, non-random journey of a cosmos that has, against immense odds, generated beings capable of wondering about its true nature. But this breathtaking vision of a cosmos that balances its own books to the precise sum of zero is not the final word on the ultimate scale of existence. If we are willing to follow the logic of mathematics to its final, inexorable conclusion, we are led to a multiverse so vast and all-encompassing that it makes every other theory seem parochial by comparison. This is the mathematical multiverse, or what physicist Max Tegmark calls a level 4 multiverse, and its central proposition is as simple as it is staggering. Every mathematical structure that can be coherently defined exists as a physical reality. In this ultimate ensemble, our universe, with its specific laws of physics, is not special or unique. It is simply one entry in an infinite library of mathematical possibilities, each one a complete and self-contained cosmos. To truly grasp the radical nature of this idea, we must revisit the ancient philosophical debate we encountered with Plato. Is mathematics discovered or invented? Do mathematicians uncover pre-existing truths, like explorers mapping a hidden continent, or do they create a logical system, like an artist painting on a blank canvas? Tegmark's hypothesis is the ultimate endorsement of the discovery camp, a form of mathematical Platonism so extreme it borders on the metaphysical. He argues that mathematical existence is equivalent to physical existence. A universe described by a specific set of equations isn't just a model we can write down. It is out there somewhere in a state of full physical reality. The abstract circle, defined by all points equidistant from a center, doesn't just exist as an idea. It exists as a physical shape in a universe where Euclidean geometry holds true. A universe governed by the rules of a different algebra, where 2 + 2 = 5, is just as real as our own, playing out its strange, non-intuitive physics in its own isolated realm of logical space. This leads to a profound redefinition of what we even mean by the laws of physics. In our everyday understanding, we think of these laws as the immutable rules that govern our particular cosmic arena. But from the perspective of the mathematical multiverse, there are no laws in the sense of prescriptions or decrees. There is only mathematical consistency. What we call a law of physics is simply a description of the patterns and regularities that hold within our specific mathematical structure. In another mathematical universe with a completely different foundational structure, the patterns would be entirely different, and the inhabitants of that universe, if any exist, would formulate a completely different set of laws to describe their reality. The concept of a law itself is not fundamental. It is a local description of a particular mathematical landscape. One of the most compelling implications of this theory is how it reframes the mystery of our universe's apparent fine-tuning. We look at the precise values of the constants of nature, the strength of gravity, the mass of an electron, and marvel that even a slight alteration would make life impossible. From the perspective of a single universe, this seems like an incredible coincidence, but within the infinite diversity of the mathematical multiverse, it is an inevitability. With an endless array of mathematical structures on offer, it is statistically guaranteed that some of them will have the properties necessary to support complex structures, including conscious observers. We should not be surprised to find ourselves in a universe compatible with our existence. We simply couldn't find ourselves anywhere else. This application of the anthropic principle is pushed to its absolute limit, moving the question from why this universe to why this mathematical structure. The answer, according to Tegmark, is that we are asking the question from within it. Yet, for all its elegant simplicity, the mathematical multiverse hypothesis faces formidable criticisms, the most significant being its potential untestability. If these other mathematical universes are completely causally disconnected from our own, if no signal, no influence, no evidence of any kind can ever cross the boundary from one mathematical structure to another, then can the idea even be considered a scientific theory? Proponents argue that the theory that predicts the level 4 multiverse, namely the idea that mathematical existence equals physical existence, is a hypothesis about the nature of reality. Its evidence is the unreasonable effectiveness of mathematics itself. The fact that our physical world is so perfectly described by mathematics is a clue that they are deeply intertwined, perhaps even identical. While we may never visit a universe with different dimensionality, the success of mathematics as a description of our world is the clue that points toward a deeper, more profound connection. Ultimately, the mathematical multiverse presents a vision of reality that is both awe-inspiring and strangely alienating. It suggests that the cosmos is not just vast in space and time, but vast in logical possibility. Every coherent story is being told, every consistent equation is being solved, every possible form of existence, no matter how bizarre or unimaginable to our limited minds, is real. This can feel nihilistic, reducing our rich and meaningful lives to just one arbitrary page in an infinite book of realities. But another perspective is one of immense wonder. It means that the human capacity for mathematics, our ability to glimpse these abstract patterns, is our direct connection to the ultimate architecture of all that is. In doing so, we are not just studying the rules of our local cosmic game. We are catching a fleeting, shadowy glimpse of the infinite and necessary landscape of all possible existence. If the universe is fundamentally a vast mathematical structure or a network of conscious agents, then the most intimate mystery of all remains. How does this grand cosmic reality give rise to the specific, vivid, and undeniable phenomenon of your own awareness? We arrive now at one of the most daring and controversial attempts to answer this question, a theory that seeks to plant consciousness directly into the fabric of physics. This is the orchestrated objective reduction theory, or ORCH, proposed by the renowned physicist Sir Roger Penrose and the anesthesiologist Stuart Hameroff. Their radical hypothesis suggests that consciousness is not an emergent property of classical brain computation, but rather the result of delicate quantum mechanical processes happening deep within the neurons of your brain, specifically within structures called microtubules. To understand the sheer audacity of this idea, we must first appreciate the conventional view of the brain. Mainstream neuroscience typically sees the brain as an extraordinarily complex computer. Neurons are like biological transistors, firing electrical signals across synapses in intricate networks. Thought, memory, and consciousness are thought to be the result of this classical information processing, much like the software that emerges from the hardware of a silicon chip. Penrose and Hameroff find this view deeply unsatisfying, particularly when it comes to the hard problem of consciousness. How can the firing of neurons, which is essentially just a series of on-off switches, give rise to the subjective richness of a sunset, the feeling of love, or the understanding of a mathematical truth? They argue that classical physics alone is insufficient to explain the non-algorithmic, holistic, and seemingly non-deterministic nature of conscious experience. Penrose's contribution begins with a fascinating connection between consciousness and the foundations of mathematics. In his book, The Emperor's New Mind, he argued, based on Gödel's incompleteness theorems, that human understanding and mathematical insight cannot be reduced to a mere computational algorithm. There is something inherently non-computable about consciousness. He then proposed that this non-computable element must have a physical basis, and that the only known physical process that is also non-algorithmic and non-deterministic is the collapse of the quantum wave function. But where in the brain could such a delicate quantum event occur and be protected from the warm, wet, and chaotic environment that would normally destroy quantum coherence almost instantly? This is where Stuart Hameroff's expertise comes in. He pointed to microtubules, which are tiny cylindrical structures that form the skeleton of our cells, including neurons. Far from being simple scaffolding, microtubules are incredibly dynamic and complex. They are involved in organizing intracellular transport, maintaining cell shape, and during cell division, they form the mitotic spindle that separates chromosomes. Each microtubule is a lattice of proteins called tubulin. Hameroff proposed that these tubulin proteins can exist in different conformational states, and crucially, that these states could be governed by quantum superposition. In essence, a single tubulin unit could be in a quantum state of both shape A and shape B simultaneously, and these superpositions could extend across many tubulins within the microtubule lattice, creating a macroscopic quantum system right inside your brain cells. The theory then weaves these two ideas together into a stunning narrative of consciousness. According to Orch, or quantum superpositions form in the microtubules. These are not random fluctuations, they are orchestrated by the cell's biochemistry, hence the name orchestrated objective reduction. This orchestration is influenced by everything from neurotransmitters to sensory input, essentially tuning the quantum system. The superposition persists until it reaches a threshold related to the fundamental geometry of spacetime, a concept Penrose links to his own work on quantum gravity. At this point, the wave function undergoes an objective collapse, a specific kind of wave function collapse that Penrose believes is a real physical process, not just an abstraction. This collapse event, happening in an instant, selects a single outcome from the multitude of quantum possibilities. And it is this moment of quantum selection, this flash of transition from the fuzzy quantum world to the definite classical world, that gives rise to a single moment of conscious experience, or a proto-conscious event. A cascade of these orchestrated collapses happening across vast networks of neurons is proposed to generate our continuous stream of consciousness. Each collapse event integrates information from a wide area of the brain in a holistic, non-local way, potentially explaining the unified nature of our experience. This could also account for the mysterious binding problem, how the brain combines inputs from different senses into a single, coherent perception. The theory even makes a dramatic prediction about the location of consciousness, suggesting it is not merely in the synapses between neurons, but deep within the neurons themselves, in the intricate quantum dance of the microtubules. Naturally, a theory this radical has faced intense scrutiny and criticism from both physicists and neuroscientists. The primary objection is the issue of decoherence. Quantum states are notoriously fragile and require extreme isolation from their environment near absolute zero temperatures and a vacuum to be maintained for more than a tiny fraction of a second. The interior of a living brain is essentially the opposite of that. It is warm, wet, and bustling with molecular activity. Critics argue that any quantum coherence in microtubules would be destroyed by environmental noise almost instantly, far too quickly to play any role in neural processes that occur on millisecond timescales. Proponents of Orch or counter with evidence from other biological systems, such as the quantum coherence observed in photosynthesis, where plants efficiently transfer energy using quantum effects at room temperature. They suggest that the ordered structure of microtubules might act as a protective cage, shielding quantum information long enough for it to be meaningful. Another major criticism is that the theory seems to invoke quantum magic to solve a problem we don't fully understand. Skeptics question whether adding the complexity of quantum physics actually explains consciousness any better than classical models. It might just be pushing the mystery down to a smaller scale. Furthermore, the concept of objective collapse that Penrose proposes is itself a minority interpretation within quantum physics, where the more widely accepted explanations are the Copenhagen interpretation or the many worlds interpretation. Despite the fierce debate, the Orch or theory stands as a breathtakingly ambitious attempt to bridge the chasm between the world of quantum physics and the world of mind. It dares to propose that our innermost selves are not just a byproduct of electrical signals, but are woven into the very fabric of reality, arising from the most fundamental and mysterious processes that govern the universe. It suggests that the line between the physical and the mental might be far blurrier than we ever imagined, and that the key to understanding consciousness could lie not in the chemistry of the brain alone, but in the quantum vibrations happening within its deepest structures. Whether it is ultimately proven correct or not, or challenges us to think bigger, pushing the boundary of what it means to be a conscious being in a quantum world. Yet another path toward reconciling the smooth, curved spacetime of general relativity with the grainy, quantum world takes us to a framework that is radical in its simplicity. This is causal set theory, an approach to quantum gravity that proposes a breathtakingly minimalist foundation for reality. It suggests that the fabric of spacetime is not a smooth, continuous manifold as Einstein described, but is instead a collection of discrete, atomic units of spacetime, connected to one another only by the most fundamental relationship of all, cause and effect. In this view, the universe at its most basic level is a vast web of causal relationships, a story of what leads to what, and the familiar notions of space and time are merely secondary, emergent properties that arise from this deeper, more primitive order. The core idea of causal set theory can be captured by two simple principles. First, reality is discrete. Just as a digital photograph is composed of a finite number of pixels, spacetime itself is composed of a finite number of elementary events, or atoms of spacetime. These atoms are the basic building blocks of existence. Second, the only fundamental relation between these atoms is a partial order, a before and after relationship of causality. One event can either precede another, follow it, or be causally unrelated. There is no inherent notion of distance or duration at this fundamental level. The concepts of here and there, or 1 second apart, are not primitive. They are collective, large-scale properties that emerge from the intricate pattern of causal connections linking a vast number of these elementary events. To grasp this, imagine a vast, unorganized collection of dots. Now begin drawing arrows from some dots to others, indicating that one must happen before another can. As you add more and more dots and arrows, a structure begins to emerge. Clusters of dots that are densely connected by arrows will appear to be close together in an emergent sense of space, while a long chain of arrows from one dot to a distant one will define an emergent sense of time. The geometry of spacetime, its curvature, its dimensions is not put in by hand but is woven from the pattern of these causal links. This approach offers an elegant potential solution to one of the most vexing problems in theoretical physics: the singularities that appear at the center of black holes and at the beginning of the Big Bang. In Einstein's general relativity, these are points where the curvature of spacetime becomes infinite and the laws of physics break down. This is a clear sign that the theory is incomplete. In causal set theory, however, there are no true singularities because there are no arbitrarily small scales. Reality has a fundamental graininess set by the Planck scale. You cannot squeeze an infinite amount of curvature into an infinitely small point because there is no such thing as an infinitely small point. The theory naturally avoids these pathological infinities by its very discrete nature. The Big Bang would not be a singularity but a single, foundational event, the first cause in the causal set, from which all other events have sprung. The center of a black hole would not be a point of infinite density, but a region where the causal structure becomes highly complex and dense, yet still finite and well-defined. Perhaps the most profound implication of this theory is how it accounts for the arrow of time. In the large-scale, smooth universe of general relativity, the fundamental equations are time-symmetric. They work just as well running forward as backward. This leaves the obvious fact that time has a definite direction. The cup of coffee cools, it does not spontaneously heat up as a puzzling emergent property. Causal set theory provides a natural origin for the arrow of time. At the fundamental level, the causal relation is inherently directed. Event A causes event B, and that relationship is not reversible. The growth of the universe, the continual addition of new spacetime atoms to the causal set, provides a fundamental directionality. The growth of the set itself is the flow of time. The increase in the number of elements and the expansion of the web of causal connections defines a clear, fundamental distinction between past and future, offering a deep explanation for why time only moves in one direction. However, a major challenge for causal set theory is the recovery of the smooth, four-dimensional spacetime we observe. How does the familiar, continuous geometry of our world, with its 3 dimensions of space and 1 of time, emerge from a disordered collection of discrete points with only causal connections? This is known as the inverse problem. The theory must demonstrate that a sufficiently large and complex causal set will, on average, approximate a manifold with the specific properties of our universe. Remarkably, research has shown that this is possible. A key finding is that a causal set that is faithfully embedded into a 4-dimensional Lorentzian manifold, the kind of spacetime described by relativity, will have a number of elements that is proportional to the volume of that spacetime. This provides a crucial link between the discrete counting of atoms and the continuous geometry of volume. The dimension of spacetime itself may be an emergent property, determined by the specific pattern of causal connections. Our universe appears 4-dimensional because the causal relations in the set that constitutes it have a particular statistical character that gives rise to 4 dimensions on large scales. Despite its conceptual elegance, causal set theory, like all approaches to quantum gravity, faces significant hurdles. One of the biggest is the development of a dynamics, a set of laws that govern how the causal set grows and evolves. What are the rules that determine which new atoms are added and how they connect to the existing set? Researchers explore this through models of sequential growth, where the universe is built up one element at a time with probabilistic rules governing each new connection. The ultimate goal is to find a dynamic law that, in the large-scale limit, reproduces the equations of Einstein's general relativity. Another challenge is connecting the theory to the other great pillar of physics, quantum mechanics. How do quantum superpositions and probabilities arise from a causal set? Some approaches suggest that the causal set itself may exist in a quantum superposition of different structures, or that the probabilities inherent in quantum theory are related to the probabilistic rules of the set's growth. While these are active areas of research, causal set theory stands as a uniquely stark and compelling vision of reality. It strips away all superfluous concepts, proposing that the cosmos is, at heart, nothing more than a vast, growing network of causes and their effects, and that everything else, the space we move through, the time we feel passing, and the very laws of physics, is a magnificent and convincing illusion born from this simple causal dust. After navigating theories that place consciousness at the foundation of reality or suggest our perceptions are mere illusions, we encounter a powerful idea that reframes the entire scientific quest for knowledge not as a march toward certainty, but as a process of relentless error correction. This is Karl Popper's evolutionary theory of knowledge, a philosophy that suggests our understanding of reality evolves in a way strikingly similar to biological evolution, not by proving our ideas right, but by ruthlessly proving our best guesses wrong. Popper was deeply troubled by a problem that had plagued philosophy for centuries, the problem of induction. This is the idea that we learn about the world by observing patterns. We see the sun rise every morning and induce that it will rise again tomorrow. We see that fire is hot and induce that all fire is hot. But Popper realized that no number of confirming observations can ever prove a theory to be true. No matter how many white swans you see, you can never prove that all swans are white. A single black swan discovered on a future day can shatter the entire theory. Scientific theories, he argued, make universal claims about the world, claims that stretch across all of space and time, but our experience is always limited to a finite number of observations. Therefore, truth, in the sense of absolute, proven certainty, is forever beyond our grasp. His brilliant solution was to flip the traditional view of science on its head. Instead of seeing science as a process of verification where we accumulate evidence to support our theories, Popper proposed that it advances through falsification. The mark of a truly scientific theory is not that it can be confirmed, but that it can, in principle, be proven false. A good theory is one that is bold, precise, and makes risky predictions that could be contradicted by observation. For example, Einstein's theory of general relativity predicted that light from distant stars would bend around the sun. This was a risky, testable prediction. When Arthur Eddington's eclipse expedition in 1919 confirmed the bending, it didn't prove Einstein's theory was true for all time, but it did show that it had survived a serious attempt to falsify it. It was therefore a better theory than Newton's, which it replaced. Science, for Popper, is not about building an unshakable fortress of truth. It is about building makeshift structures that we constantly test against reality, hoping they will withstand the storm, but always ready to tear them down and build better ones when they fail. This process of conjecture and refutation is what Popper saw as analogous to biological evolution. Our theories are like mutations. They are bold conjectures, guesses about the world that we put forward into the harsh environment of reality. The ones that are poorly adapted, that are falsified by experiment or observation, are selected out and die off. The ones that survive are not necessarily the truest in an absolute sense, but they are the fittest, the best adapted to our current state of knowledge. Our scientific knowledge grows not by accumulating verified truths, but by a Darwinian struggle among competing theories, where the elimination of error allows our understanding to evolve toward greater and greater problem-solving power. We are not cosmic cartographers drawing an ever more accurate map of a fixed territory. We are instead explorers constantly redrawing our maps based on where we have found chasms and dead ends. This view, known as fallibilism, has profound implications for our understanding of reality's knowability. It suggests a universe that is ultimately mysterious, whose deepest secrets we can never claim to have captured with finality. Every theory we hold, no matter how successful, is ultimately provisional, a temporary resting place on an endless journey. This is not a counsel of despair, but a source of liberation. It frees science from the dogmatism that can stifle progress, encouraging a spirit of bold speculation and critical debate. It means that our ignorance is not a barrier to knowledge, but the very engine that drives it forward. The recognition that we might be wrong is what fuels the desire to test, to question, and to improve. This attitude of critical rationalism is what Popper saw as the foundation of an open society, one that is willing to challenge its own beliefs rather than suppress dissent. Popper's philosophy creates a fascinating bridge between the objective world and our subjective attempts to understand it. He was a realist. He believed there is a real world independent of our minds that our theories are trying to describe. But he was also a staunch anti-justificationist. We can never justify our belief that a theory is true. We can only justify our preference for it over a falsified rival. The growth of knowledge is not a linear accumulation of justified truths, but an evolutionary process of problem solving where we learn primarily from our mistakes. This humbling perspective places a permanent question mark beside any claim to have achieved final understanding, whether in science, politics, or philosophy. It suggests that the most realistic picture of reality is not a fixed image, but a dynamic, ever-evolving sketch, one that becomes less inaccurate over time, not because we have found the truth, but because we have become so adept at discovering where we are wrong. Now, if all these grand theories about the nature of reality are to have any meaning at all, they must ultimately confront the most intimate and undeniable fact of our existence, the raw feel of consciousness itself, the sensation of what it is like to be you. This brings us to a sophisticated and nuanced approach within the philosophy of mind, one that doesn't try to explain consciousness away, but instead seeks to explain why it seems so inexplicable. This is the phenomenal concept strategy, a clever defense of physicalism that argues the mystery of consciousness isn't a problem with the world, but a problem with the special tools we use to think about it. The central challenge this strategy addresses is the famous explanatory gap. We can know everything there is to know about the physical workings of a brain, the firing of neurons, the flow of neurotransmitters, and yet it seems we still wouldn't know what it's like to see the color red or feel a pang of sadness. This intuition has led many to conclude that consciousness must be something non-physical, an extra ingredient in the universe that can't be captured by physical science. The phenomenal concept strategy offers a different diagnosis. It agrees that there is a deep and profound gap between our physical descriptions of the brain and our phenomenal descriptions of experience, but it claims this gap is conceptual, not ontological. It's a gap between two different ways of thinking about the same thing, not a gap between two different kinds of thing in the world. To understand this, we need to distinguish between two types of concepts. On one hand, we have physical concepts. These are the concepts we use in science to describe objective, third-person properties. Concepts like neuron, synaptic firing, or C-fiber stimulation are physical concepts. They are descriptive and theoretical. On the other hand, we have phenomenal concepts. These are the concepts we use to grasp our own subjective experiences from the inside. The concept you employ when you recognize the specific, unique quality of a toothache is a phenomenal concept. The key claim of the strategy is that phenomenal concepts are a very special kind of concept. They are direct, recognitional, and perhaps even involve a kind of imaginative sample of the experience itself. Think of it like this. Imagine you are a brilliant scientist who has never tasted chocolate. You could know everything about its chemical composition, its effect on taste buds, and the precise neural pathways it activates. You would possess a complete set of physical concepts related to chocolate. But then you take a bite. Suddenly, you acquire a new concept, the phenomenal concept of the taste of chocolate. This concept is not just a new description, it's a new way of accessing the very same physical event happening in your brain. The phenomenal concept allows you to recognize that experience directly in a way that is immediate and opaque. You can't fully analyze it or break it down into parts. You just know it when you feel it. The mystery, then, is not that a non-physical ghost has appeared. It's that you have acquired a powerful new cognitive tool for thinking about a physical state of your own body. Proponents of this view argue that when we claim we can't see how brain processes could be conscious experiences, we are making a cognitive error. We are trying to connect two radically different types of concepts and finding the link unintelligible. But this doesn't mean the link isn't there. It's like someone who only knows about water through the chemical concept H2O trying to understand how it could be the same thing as the clear, wet, thirst-quenching stuff they call water. The connection seems mysterious because the concepts are so different, but the identity is real. Similarly, the strategy suggests that the feeling of pain just is the firing of C-fibers, but we are equipped with two completely different mental lenses for viewing this single reality, one scientific and descriptive, the other intimate and experiential. This perspective has dramatic implications for the hard problem of consciousness. It suggests that the problem is hard precisely because of the unique nature of our phenomenal concepts. When we introspect, we are using a concept that is so direct and revelatory that it seems to be revealing a fundamentally different kind of property. But this is an illusion created by our cognitive apparatus. The strategy doesn't solve the hard problem by giving a mechanism for how the brain produces experience. Instead, it argues that the very feeling that there is a hard problem is exactly what we should expect if physicalism is true and we possess these special phenomenal concepts. The sense of mystery is a predictable feature of our psychology, not a clue about the world's metaphysics. Of course, this strategy is not without its powerful critics. Some argue that it merely moves the mystery from the world into the mind, creating a new problem. How can a purely physical brain generate these magical-seeming phenomenal concepts? If the brain is just a causal mechanism, how can it possess a concept that involves grasping the intrinsic nature of a state? This seems to require cognitive powers that a purely physical system shouldn't have. Other critics, like the philosopher Joseph Levine, who originally coined the term explanatory gap, argue that the strategy is incomplete. Even if we accept the special nature of phenomenal concepts, we still need an explanation for why these particular brain states have these particular feels. The conceptual gap may point to a genuine epistemic gap that requires a deeper explanation. Despite these challenges, the phenomenal concept strategy remains a compelling and resilient position in the philosophy of mind, offering a way to respect the profound uniqueness of consciousness while remaining committed to a physicalist worldview. It suggests that the greatest obstacle to understanding the mind may not be the universe's secrets, but the very structure of our own understanding. But what if the boundaries of your mind are not drawn at the edge of your skull? For centuries, we've located consciousness and cognition squarely within the brain, a sacred space where thinking happens in isolation from the world. Yet consider the simple act of doing long division with a pen and paper. Where is the calculation truly taking place? Is it solely inside your head, or is it a collaborative process between your internal grasp of arithmetic and the external scaffold of the pen, the paper, and the numbers you write down? This is the provocative starting point for the extended mind hypothesis, a theory that boldly proposes that the tools we use, the notes we write, and the technology we interact with are not merely aids to thinking, they can become literal parts of our mind itself. The idea was most famously articulated by philosophers Andy Clark and David Chalmers in 1998, using a compelling thought experiment. They asked us to compare two people, Inga and Otto. Inga hears about an exhibition at the Museum of Modern Art and, after a moment of thought, recalls from her biological memory that it is on 53rd Street and decides to walk there. Otto, who has Alzheimer's disease, also wants to see the exhibition, but Otto relies on a notebook he always carries. He consults it, finds the address written down, and sets off. Clark and Chalmers argued that Otto's notebook plays the exact same functional role for him that Inga's biological memory plays for her. It is a reliable, constant, and easily accessible store of information that guides his actions. If we say that Inga's belief about the museum's location is part of her cognitive process, then we should, for the sake of consistency, consider the information in Otto's notebook as part of his cognitive system. The mind, in this view, extends beyond the skin and skull to include the notebook. The physical object becomes a component of Otto's mind, just as surely as the neurons in Inga's hippocampus. This principle of cognitive extension applies far beyond memory. Think about the way a simple calculator extends your mathematical reasoning. You don't hold all the steps of a complex calculation in your head. You offload the work onto the device, which becomes a partner in your problem solving. The carpenter's tape measure becomes an extension of their spatial reasoning. The chef's recipe, splattered with oil and flour, is not just a reminder but an active participant in the process of cooking, guiding each step and freeing up mental resources for improvisation and taste. Even the arrangement of your desk, the pile of important documents here, the pen placed there functions as an external map of your priorities and intentions, a form of environmental scaffolding that structures your thoughts and guides your behavior. In each case, the line between the internal mind and the external world becomes blurry. Our cognition is not a solitary internal performance. It is a dynamic dance between the brain, the body, and the world. The rise of digital technology has turned this philosophical idea into a lived reality for billions of people. Your smartphone is arguably the most powerful cognitive extension ever created. It holds your contacts, your calendar, your photographs, your access to the entirety of human knowledge. When you use a GPS to navigate a city, your sense of direction is no longer confined to an internal cognitive map. It is a hybrid system combining your visual perception with the turn-by-turn instructions from the device. The device isn't just a tool you use, it is integrated so seamlessly into your decision-making that it becomes part of your extended cognitive loop. Social media platforms extend our social cognition, allowing us to maintain complex networks of relationships that would be impossible to manage through biological memory alone. In a very real sense, our minds are now distributed across a global network of servers, screens, and signals, challenging the very idea of where an individual person ends and the rest of the world begins. This radical expansion of the self forces us to reconsider some of our most deeply held assumptions about identity and responsibility. If your beliefs are stored in a notebook or a cloud server, who owns them? If a crucial decision is made based on a calculation performed by an algorithm, where does the agency lie? The extended mind perspective suggests that our legal and ethical frameworks, which are built on the model of the solitary, bounded individual, may need a significant update. It also raises profound questions about the self. Are we just the biological organism, or are we the organism plus tool system? When you lose your phone, it feels like a genuine cognitive loss. A piece of your mind has gone missing. This isn't just a feeling of inconvenience. From the perspective of the extended mind hypothesis, it might be an accurate description of what has occurred. The implications for our understanding of reality are equally deep. If our minds are not locked away inside our heads but are woven into the fabric of our environment, then the world we perceive is not a pre-packaged reality that we passively observe. Instead, we actively construct our reality through a continuous feedback loop with our cognitive extensions. The architect who uses a computer-aided design program doesn't just draft plans. She thinks with the software, and the possibilities the software offers shape the very building she can imagine. The world we live in is, in part, a product of the cognitive tools we have built. By extending our minds into the environment, we shape that environment, which in turn shapes new ways of thinking in an endless cycle of co-creation. This suggests that the nature of reality is not fixed and independent, but is dynamically intertwined with the ever-expanding reach of human cognition. Now, if we've learned anything from this journey, it's that our most fundamental theories of reality often start by asking what are the basic building blocks of the universe. But what if we've been asking the wrong kind of question entirely? This brings us to a revolutionary approach that turns the entire methodology of physics on its head. It's called constructor theory, pioneered by the visionary physicist David Deutsch, and it proposes a stunningly simple yet powerful shift. Instead of describing the world in terms of what happens, we should describe it in terms of what can and cannot be done. For centuries, since the time of Newton, physics has been dominated by what we can call the prevailing theory of motion. We write down equations like the laws of gravity or quantum mechanics that predict how a system will evolve from one state to another over time. These are recipes for what will happen given initial conditions, but this approach has run into profound walls. It struggles with the initial conditions of the universe itself. It creates paradoxes in quantum mechanics, and it has a notoriously difficult time cleanly integrating the arrow of time from thermodynamics. Constructor theory proposes a way out by changing the subject. It says the most fundamental statements in physics are not about trajectories and causes, but about possibility. Specifically, it focuses on which physical transformations are possible, which are impossible, and why. The core idea can be grasped with a simple example. Think about a perpetual motion machine, a device that can create energy from nothing. In conventional physics, we say this is impossible because it violates the laws of thermodynamics. But in constructor theory, this impossibility is the starting point, not a consequence. The theory would begin by stating a fundamental principle. It is impossible to build a perpetual motion machine. This might sound like a trivial rewording, but its power lies in its generality. This statement about impossibility is now a primary constraint on reality, a law that applies to all physical systems regardless of their specific dynamics. The task of physics then becomes to chart the landscape of all possible and impossible tasks. The things that can be built, the constructors, are any physical systems that can cause a transformation to occur while themselves remaining unchanged. A catalyst in a chemical reaction is a simple constructor. It enables a change without being consumed. A computer is a powerful, general-purpose constructor for information processing. This shift in perspective is especially powerful when it comes to unifying some of the most stubbornly separate domains of physics. Take information. In our current motion-based framework, information is a bit of a ghost. We can talk about it, but it doesn't sit comfortably alongside concepts like energy and mass. In constructor theory, information is given a rock-solid foundation. It defines a bit of information as something that can be copied. The ability to copy information reliably becomes a fundamental, permissible transformation in the universe. Conversely, the impossibility of copying the state of an unknown quantum system, the no-cloning theorem, becomes a fundamental constraint as primary as the law of gravity. This elegantly explains why quantum information is different from classical information, placing it right at the heart of physics rather than treating it as an abstract afterthought. The same approach offers a profound new way to understand the second law of thermodynamics and the arrow of time. Instead of talking about increasing entropy in terms of probabilistic particle motions, constructor theory frames it as a constraint on possible tasks. It becomes impossible to reliably turn heat from a cold object into work to heat a hotter object. This isn't just a statistical likelihood. It's a fundamental law about what transformations are permitted in our universe. This impossibility explains why we remember the past but not the future, and why causes always precede their effects. The arrow of time emerges not from messy statistics, but from a deep, foundational principle about which tasks are possible constructors. Perhaps the most ambitious promise of constructor theory is its potential to finally solve the measurement problem in quantum mechanics. In the conventional view, we have a schizophrenic universe. Quantum systems evolve smoothly according to the Schrödinger equation until the mysterious moment of measurement when the wave function collapses. Constructor theory could potentially eliminate this duality. It would seek to define measurement not as a special, magical process, but as a particular kind of possible transformation, one where information about a quantum system is transferred to a measuring apparatus in a way that is both accurate and reproducible. The weirdness of superposition and entanglement would then be seen as consequences of the specific constraints on what kinds of information transferring tasks are possible in our universe. The divide between the quantum and classical worlds wouldn't be a boundary between different laws, but a distinction between different types of possible constructions. Of course, constructor theory is still in its early stages, a tantalizing framework rather than a finished product. Its greatest challenge is to prove its power by deriving the known laws of physics, the equations of quantum mechanics and general relativity, from its deeper principles about possible and impossible tasks. If it can do that, it will have achieved a unification that has eluded physics for a century. It represents a Copernican scale shift in our thinking, suggesting that the universe is not primarily a machine that grinds along predetermined paths, but a vast space of potentialities, a set of rules for what can be built and what is forever forbidden. In this light, reality is not just a story of what is, but a chronicle of what can be made, and we, as conscious, constructing beings, are active participants in exploring its boundless constraints. But if the bizarre, probabilistic world of quantum mechanics is the true foundation of reality, how does it give rise to the stable, objective world of coffee cups, chairs, and scientific measurements that we all agree upon? This brings us to a theory that offers a powerful and elegant answer, one that borrows a central idea from biology to solve one of physics' deepest puzzles. This is quantum Darwinism, a framework that explains how the fuzzy, ghostly quantum world solidifies into the concrete, shared reality we experience, and it does so by suggesting that the most robust quantum states are the ones that are best at replicating themselves throughout the environment. The problem it addresses is at the heart of the quantum to classical transition. In the pristine isolation of a lab, a particle can exist in a superposition, being in multiple states at once. But when we look at a table, it is definitively here, not in a superposition of being here and there. The standard Copenhagen interpretation says this transition happens through a mysterious collapse induced by measurement. But quantum Darwinism, developed by theorists like Wojciech, proposes a far more natural and less magical process. It argues that the collapse isn't a special event. It's happening all the time, everywhere, through the relentless interaction of every quantum system with its surroundings. The key is decoherence, the process where a quantum system loses its fragile superposition by leaking information about itself into the environment. But quantum Darwinism adds a crucial new layer to this story. Not all quantum states decohere equally. Some are far more resilient than others. These resilient states are known as pointer states, and they are the quantum equivalent of a species that is perfectly adapted to its environment. Imagine a quantum system like a single particle as a delicate organism. It is constantly bombarded by its environment, by photons of light, by air molecules, by the faint tug of distant gravitational fields. Most of its possible quantum states are extremely fragile. Any interaction with the environment will disrupt them, causing the superposition to collapse randomly. But the pointer states are different. They are the states that are least disturbed by these common environmental interactions. They are the evolutionary winners in the quantum jungle. For a particle's position, the pointer state is a relatively well-localized state. Why? Because a photon bouncing off a particle that is in a definite location will carry away information about that location without drastically altering it. A particle in a highly delocalized superposition, however, will be severely disrupted by such an interaction. Through countless trillions of these tiny interactions every second, the environment continuously measures the system, and in doing so, it selects for the pointer states, weeding out the fragile superpositions. This is where the Darwinian idea takes center stage. The information about the system's pointer state doesn't just get recorded once. It gets copied over and over again into the countless degrees of freedom of the environment. A single photon bouncing off a table carries information about the table's position, but so do the trillions upon trillions of other photons hitting it, the air molecules scattering from its surface, and the gravitational field it creates. Each of these environmental fragments becomes a tiny, independent record of the same fact: the table is here. This proliferation of information is akin to a successful gene spreading through a population. The pointer state is fit because it can create many copies of itself, not copies of the physical object, but copies of the information about its state. This process is called einselection, or environmental-induced superselection. The breathtaking implication is that what we call objective reality is simply the set of properties that have been redundantly encoded into the environment. When you and I both look at a table and agree on its position, it's not because we are both accessing some mystical, Platonic ideal of the table. It's because our senses are both independently tapping into the countless environmental records that have been created by the table's interaction with light and air. We are both reading from the same cosmic data stream. The reason we never see macroscopic objects in quantum superpositions is that such states are incredibly unstable. They are immediately obliterated by decoherence, and they fail to leave behind any redundant copies in the environment. They are, in a sense, quantum evolutionary dead ends. The solidity of the classical world is an emergent property of this constant, natural selection for informationally robust states. This perspective elegantly reframes the role of the observer. In quantum Darwinism, observers are not special agents with the magical power to collapse wave functions. We are simply highly complex systems that have evolved to become adept at intercepting and processing the redundant information that the environment is constantly broadcasting. Our brains and measuring instruments are designed to tap into these widely available data streams. The reason different observers agree on the outcome of a measurement is that they are all gathering information from the same set of environmental records. There is no single privileged collapse moment. Instead, there is a gradual process where a quantum state becomes increasingly objective as more and more copies of its information are scattered throughout the world. This transforms the measurement problem from a philosophical paradox into a practical problem of information transmission and redundancy. Quantum Darwinism doesn't just explain the world we see, it makes specific, testable predictions. It suggests that the hallmark of a classical property is its redundancy. We should be able to measure a tiny fraction of the environment, say, a handful of photons scattered from an object, and still deduce its key properties like its position. Experiments are already being designed to probe this. By carefully measuring how information about a quantum system is imprinted on its surroundings, scientists hope to observe the Darwinian process in action, watching as certain states are selected for and their information proliferates. This theory provides a compelling, naturalistic bridge between the strange quantum underworld and the familiar classical landscape we inhabit, suggesting that the reality we agree upon is not a fundamental given, but a robust consensus reached through the relentless and replicating chatter of the quantum world itself. And now we arrive at a theory that asks us to forget everything we think we know about the relentless forward march of time. This is time-symmetric quantum mechanics, a framework that proposes the quantum laws governing reality are perfectly balanced, working with equal force whether time flows forward or backward. This isn't just a mathematical curiosity, it's a profound challenge to our most basic intuition that the past is fixed and the future is open, suggesting that the very fabric of causality might be far more flexible and mysterious than we ever imagined. To grasp this radical idea, we first need to revisit the strange heart of quantum theory, the wave function. This mathematical object describes all the possible states of a particle. The standard view, held by the Copenhagen interpretation, is that this wave function evolves smoothly and deterministically according to the Schrödinger equation until the moment of measurement. At that instant, it undergoes a sudden, irreversible collapse, randomly settling into a single, definite outcome. This collapse is inherently time asymmetric. It's a one-way street. The blur of possibilities condenses into a concrete fact, and there's no going back. The act of measurement seems to introduce a fundamental arrow of time, a point of no return in the quantum world. Time-symmetric interpretations, however, remove this special status from the measurement process. They propose that the fundamental laws of quantum mechanics are, in fact, symmetric with respect to time. The equations work just as well if you run the clock backward. In this view, the wave function never truly collapses in the traditional sense. Instead, reality is described by a more complete picture that incorporates influences from both the past and the future. The most famous of these is the transactional interpretation we explored earlier, where a particle's existence is solidified by a handshake between a wave going forward in time and a wave coming back from the future. But the time-symmetric idea is broader, suggesting that any complete description of a quantum event must take into account not only its initial conditions but also its final conditions, what the system is ultimately going to become. This notion of final conditions leads to one of the most mind-bending aspects of this theory. It resurrects the idea of retrocausality, where effects can, in a sense, precede their causes. Now, this isn't the science fiction version of time travel where you go back and shoot your grandfather. It's more subtle. It suggests that the outcome of a quantum event in the present can be influenced by a measurement or a boundary condition that is set in the future. The future, in this view, is not an empty slate waiting to be written. It actively participates in shaping the present, guiding the seemingly random quantum choices toward a specific, self-consistent history. This creates a universe that is a complete, four-dimensional whole, where the distinction between cause and effect becomes blurred, and events are determined by a global consistency across all of time. The implications for our understanding of the arrow of time are staggering. We experience time flowing in one direction because of the second law of thermodynamics. Entropy or disorder always increases. A cup of coffee mixes with milk but never spontaneously unmixes. But if the underlying quantum laws are time-symmetric, then the arrow of time we experience must be an emergent property, not a fundamental one. It arises from the specific low-entropy conditions at the Big Bang. In a sense, our entire experience of a flowing present, of remembering the past but not the future, is a consequence of this single cosmic starting point. The time-symmetric quantum world is the deeper reality, and our lopsided experience of time is just a feature of our particular cosmic neighborhood. This perspective also offers a potential solution to the vexing measurement problem. By incorporating future conditions, the apparent randomness of quantum collapse can be seen in a new light. The outcome of an experiment isn't truly random. It is selected to be consistent with the entire history of the universe, including events that haven't happened yet from our limited perspective. This doesn't mean the future is predetermined in a rigid, fatalistic way. Rather, it suggests that the universe operates as an integrated system where the past, present, and future are co-determined. Our choices are still free and meaningful within the context of our experienced timeline, but they are part of a larger, self-consistent tapestry that extends across eternity. Of course, time-symmetric quantum mechanics is not without its profound challenges. The most immediate question is, how could we ever test such a theory? If future events influence the present, designing an experiment to detect this seems circular. Furthermore, the concept of retrocausality deeply conflicts with our ingrained notion of causality, which is the bedrock of all scientific inquiry. How can we conduct experiments if we suspect the results are being influenced by what we decide to do later? Proponents argue that this influence is subtle and hidden within the quantum formalism, ensuring that no logical paradoxes can arise. The universe would simply not allow inconsistent histories to form. The handshake between past and future would only be completed for histories that make logical sense from a global perspective. Ultimately, time-symmetric quantum mechanics presents a vision of reality that is profoundly holistic and elegant. It suggests that the universe is not built moment by moment like bricks being laid in a wall. Instead, it is more like a sculpture that is revealed all at once, where every part is intrinsically connected to every other part across both space and time. It asks us to consider that our linear experience of cause and effect is a useful, local illusion, but that the true nature of temporal reality is a complex web of mutual influence, where the future is just as real and just as active in shaping the world as the past. But if the universe is a participatory phenomenon and our minds are extended into the world, what happens when we pull back from that interconnectedness to its absolute logical extreme? What if the only thing you can be truly sure of is your own conscious experience? This brings us to one of the most radical and isolating theories in all of philosophy, metaphysical solipsism. This is the stark proposition that only your own mind is certain to exist. The entire external world, the people you love, the stars in the sky, the chair you are sitting on, could be nothing more than a very elaborate and convincing dream, a hallucination, or a fabrication of your own consciousness. In this view, you are the only real thing, and everything else is a phantom, a character in a story written by and for you alone. The argument for solipsism begins with an undeniable truth from the founder of modern philosophy, René Descartes. In his search for an indubitable foundation for knowledge, he realized that he could doubt everything. he could doubt the evidence of his senses as they sometimes deceive him. He could doubt the existence of the physical world as he might be dreaming. He could even doubt the truths of mathematics, imagining a powerful evil demon dedicated to deceiving him. But there was one thing he could not doubt, that he was, in the very act of doubting, thinking. His famous conclusion, cogito ergo sum, I think, therefore I am, established his own existence as a thinking thing as the one absolute certainty. Solipsism takes this Cartesian starting point and refuses to move beyond it. It argues that while you can be sure of your own thoughts, feelings, and sensations, you have no logically airtight proof that any of these experiences are caused by an external reality. The feeling of a keyboard under your fingers could be a perfectly simulated sensation generated by your own mind. The sound of a voice could be an auditory hallucination. There is no experiment you can perform, no test you can devise that can definitively rule out the possibility that you are the sole consciousness in existence. This leads to a profound philosophical challenge known as the problem of other minds. How can you ever truly know that other people are conscious beings like you? You observe their bodies, you hear their words, you see them react to pain and joy, but all of that is just more data appearing in your own consciousness. You interpret their behavior as evidence of an inner life similar to your own, but this is an inference, an act of empathy, not a direct observation. A solipsist would argue that you have no direct access to anyone else's mind. For all you know, every other person could be a sophisticated philosophical zombie, an automaton that behaves exactly as if it were conscious but possesses no inner light, no subjective experience whatsoever. Your entire social world, then, would be a magnificent solo performance, a theater of the mind where you are the only sentient member of the audience, and also the only actor on the stage. Despite this logical possibility, almost no philosopher throughout history has been a practicing solipsist. Why is an idea that seems so logically coherent almost universally rejected? The reasons are both practical and philosophical. First, there is the argument from simplicity, often guided by Occam's razor. The solipsistic hypothesis is incredibly convoluted. It requires that your mind is capable of generating an unimaginably complex, consistent, and detailed simulation of an entire universe, complete with laws of physics, historical depth, and seemingly independent beings, all without your conscious intent or awareness. The alternative hypothesis that there is a real external world that generally corresponds to your perceptions is vastly simpler and more elegant. It explains the consistency and stubbornness of our experiences without requiring a miraculous, hidden creative power of the mind. Furthermore, solipsism leads to a kind of practical and ethical paralysis. If you truly believed you were the only real being, then concepts like morality, compassion, and responsibility would lose all meaning. Why show kindness to a being that is merely a figment of your imagination? Why strive to achieve anything in a world that has no independent reality? The solipsist position is existentially sterile. It offers no basis for a meaningful life because it denies the reality of anything outside the self to which one could meaningfully relate. Our deepest intuitions about the reality of other people and the shared world are so powerful that to live consistently as a solipsist seems psychologically impossible. We are wired for connection, and solipsism is the philosophy of absolute disconnection. Yet, the enduring power of solipsism is not as a position to be lived, but as a philosophical tool. It serves as the ultimate skeptical challenge, a permanent reminder of the limits of human knowledge. It forces us to acknowledge that our belief in an external world is just that, a belief, albeit a very strong and necessary one. It keeps us intellectually humble, preventing us from claiming absolute certainty about the nature of reality. In this sense, solipsism is less a theory about what is real and more a statement about the nature of evidence and justification. It highlights the gap between the raw data of our experience and the conclusions we draw from it, a gap that we bridge not with logic alone, but with a fundamental trust in the testimony of our senses and the reality of our shared experiences. While we may never have an absolute, logical refutation of the solipsist, we choose to live in a world we assume is real, with other minds we believe are conscious, because the alternative is a lonely and ultimately pointless dream. But if the universe is fundamentally a vast mathematical structure or a network of conscious agents, we are still left with a profound question: what is the ultimate currency of this reality? What is the most basic, irreducible substance from which everything else is made? This brings us to a hypothesis that proposes a truly modern answer, one that resonates deeply with our digital age. This is the informational universe hypothesis, a compelling idea that shifts the foundation of existence from the traditional concepts of matter and energy to a more primordial and abstract entity, information itself. In this view, the bits and bytes are not just a way to describe the world, they are the world. Reality, at its most fundamental level, might be a cosmic computation, and we are patterns within a grand informational flow. The roots of this idea can be traced to the pioneering work of physicist John Archibald Wheeler, who famously summarized his later life philosophy with the phrase, "it from bit." Wheeler proposed that every particle, every force field, and even the fabric of spacetime itself ultimately derives its existence from binary answers to yes or no questions. Imagine the universe as an immense cosmic game of 20 questions. The answers, the bits of information, are the primary reality. The its, the tangible objects we perceive, are secondary phenomena that emerge from this underlying informational substrate. When an electron is measured to have a certain spin, for Wheeler, the event is not about a tiny particle possessing an intrinsic property. It is about the universe registering a yes or a no in its grand ledger. The act of measurement is an act of information creation, and the cumulative record of all such measurements is the physical world. This perspective finds a powerful and more formal expression in the work of modern thinkers like physicist Anton Zeilinger and the proponents of quantum information theory. They point to the bizarre behavior of quantum mechanics as the strongest evidence for an informational foundation. The famous double-slit experiment, where a single particle seems to pass through two slits at once, can be reinterpreted through an informational lens. The particle's behavior isn't that of a tiny ball, but of a unit of information that is not yet fully defined. It exists in a state of multiple possibilities, a superposition of potential answers. The act of measurement, of asking a specific question, which slit did it go through, forces the system to cough up a definite answer, collapsing the possibilities into a single bit of classical information. The strangeness of the quantum world, in this view, is a direct consequence of the rules governing how information can be stored, processed, and revealed. If information is primary, then what we perceive as the laws of physics might be nothing more than the software code of the cosmos. The force of gravity, the speed of light, the charges of particles, these are not mysterious, fundamental forces. They are the algorithms, the consistent rules that govern how information is transformed and transferred. Think of a sophisticated video game. The game world has its own laws. Gravity pulls objects down, characters can jump a certain height, and collisions follow specific rules. But these laws are not written in stone. They are lines of code in the game's engine. In the same way, our universe's laws could be the emergent properties of a deeper informational processing system. This is the computational universe hypothesis, a specific flavor of the informational view, which suggests the cosmos is literally a giant computer. The universe isn't just like a computation, it is a computation, and everything within it is part of a grand, ongoing calculation. This immediately raises a monumental question. If the universe is a computer, what is it computing? What is the program? Some speculate that it might be computing its own evolution, much like a cellular automaton updating its state with each tick of a cosmic clock. Others, looking at the incredible complexity that has arisen from galaxies to life to consciousness, wonder if the program's output is meaning itself. The universe might be a machine for generating and processing information in increasingly complex and self-referential ways. Our own consciousness, from this perspective, could be seen as an exceptionally sophisticated and integrated information processing system. The feeling of being you, the stream of your thoughts and sensations, might be what it is like to be a very specific, highly complex pattern of information within the cosmic computer. This doesn't necessarily explain the hard problem of why information processing should feel like anything at all, but it provides a framework where mind is not an alien intruder in a mechanical world, but a natural and expected outcome of a reality that is, at heart, informational. The implications of this hypothesis ripple out to touch on the deepest mysteries of existence. It offers a fresh perspective on the fine-tuning of the universe. The specific constants of nature that allow for complex structures to emerge could be seen as the fundamental parameters of the cosmic computer's operating system. A universe capable of supporting life and mind is simply a universe whose informational rules are complex enough to support meaningful computation. It also provides a new angle on the nature of time. The flow of time, which feels so visceral to us, might be the sequential processing of the cosmic computer, the step-by-step execution of the universe's algorithm. The past is the data that has been processed and stored, the present is the current calculation, and the future is the set of possibilities waiting to be resolved. Of course, the informational universe hypothesis is not without its profound challenges. The most significant is the question of the substrate. In our everyday experience, information requires a physical medium to be stored and processed. The words on this page require ink and paper. The data on a hard drive requires magnetic platters. So, if the universe is made of information, what is the fundamental substance that carries this information? Proponents argue that this is a category error. Information is not a property of a substance, it is the substance. The physical world is the manifestation of the information. The medium and the message are one and the same. Another criticism is that the hypothesis might be a tautology, simply replacing the word matter with the word information without providing any new explanatory power. To be compelling, it must make testable predictions that differ from conventional physics, perhaps by suggesting fundamental limits on information density or new principles governing its flow. Ultimately, the informational universe hypothesis represents a profound shift in our metaphysical priorities. For centuries, science has sought to break reality down to its smallest material components. This view suggests we have been looking at the wrong level of explanation. The quarks and electrons may be like the pixels on a screen, important for the image, but not the source of the story being told. The true source code of reality is written in the language of information. It suggests that the universe is, at its core, intelligible because it is fundamentally conceptual. We are not just beings who have learned to decode a physical world. We are patterns of information that have become aware of their own existence, beginning the awesome task of reading the cosmic script from the inside. Yet for all the scope of these theories that play with the nature of time and consciousness, a more fundamental question remains for cosmology itself. Did the universe even have a beginning? The standard Big Bang model points to an initial singularity, a point of infinite density and temperature where the laws of physics break down. But what if this singularity is not a wall at the start of time, but merely a sign that our current theories are incomplete? This brings us to a compelling alternative known as the emergent universe theory, a class of cosmological models that proposes our cosmos did not explode into being from a singular point, but rather emerged smoothly from a prior, timeless state, like a butterfly unfurling from a chrysalis. The primary motivation for this idea is to solve the problem of initial conditions. The Big Bang singularity is a profound embarrassment for physics. It represents a boundary where our understanding ends, a moment where general relativity predicts its own failure. An emergent universe sidesteps this problem entirely by eliminating the singularity. Instead of a violent beginning, it suggests the universe originated from a static or nearly static state that existed for an indefinite period. Picture a seed, not an explosion. In this pre-cosmic phase, the universe was a tiny, stable, and cold quantum seed, perhaps hovering in a metastable state. Then, due to a quantum fluctuation or a gradual shift, this seed underwent a phase transition, triggering a period of slow, sustained inflation that eventually blossomed into the hot, expanding cosmos we know today. This transition wasn't a bang, but more of a gentle awakening, avoiding the infinite energies and paradoxical nature of a true singularity. One of the most elegant versions of this idea involves the concept of a universe emerging from nothing, but not in the sense of absolute nothingness. This quantum vacuum is not an empty void, it is a seething foam of potentiality governed by the laws of quantum mechanics. In this view, the universe could have tunneled into existence through a quantum process, much like an electron can occasionally tunnel through an energy barrier that classical physics says is impenetrable. The universe wouldn't have popped into being at a point, but rather as a finite, small, yet already coherent object from the get-go. This initial universe would be free of singularities, possessing a finite size and energy from its very inception, allowing it to smoothly enter a phase of inflationary expansion. This process elegantly avoids the need for a definitive starting gun, suggesting instead a graceful quantum birth. A particularly fascinating implication of emergent models is their potential to explain the universe's puzzling uniformity. The standard Big Bang model requires a brief period of incredibly rapid inflation to account for why the cosmos is so homogeneous on large scales. Emergent scenarios can naturally build this smoothness into the initial conditions. Because the universe spent an eternity in a quiet, static state, any initial irregularities or wrinkles would have had ample time to relax and smooth themselves out through quantum processes. Imagine a placid lake that has been still for so long that every ripple has faded away. When the expansion finally begins, it starts from this state of perfect calm, naturally producing the flat and uniform universe we observe without requiring a special hyper-fast inflationary episode. The horizon problem, the puzzle of how distant regions of space have the same temperature when they were never in causal contact, simply vanishes because those regions were together in the timeless seed phase, allowing them to reach equilibrium. This theory also opens the door to truly exotic possibilities, such as a cyclic or eternal existence for the cosmos. Some emergent models propose that our universe is just one episode in an endless series. Perhaps the universe undergoes periodic contractions and expansions, but instead of collapsing to a singularity, it rebounds from a minimum finite size, a cosmic bounce made possible by quantum gravity effects. In this view, the Big Bang was not the beginning, but simply the latest turning point in an eternal cycle. Other models suggest the universe could be naturally eternal, with no beginning or end, and what we call the Big Bang is just a particularly active phase in its infinite history. This challenges the very meaning of creation, suggesting that the question, what happened before the Big Bang, might be as misplaced as asking, what is north of the North Pole? Time itself, as we understand it, may have emerged alongside the universe, meaning there was no before in any meaningful sense. While the emergent universe theory is compelling, it is not without its challenges. The greatest hurdle is a lack of definitive observational evidence that can distinguish it from the standard inflationary Big Bang model. Both theories successfully predict the large-scale structure of the universe and the cosmic microwave background radiation. However, future observations might provide clues. Precise measurements of the polarization of the cosmic microwave background could reveal subtle imprints of gravitational waves from the universe's earliest moments. Different models predict different patterns for these waves. if the universe emerged from a non-singular state, the signal might be distinct from that produced by a rapid inflationary burst from a singularity. The detection of such a signature would be a monumental step toward validating one of the most profound ideas in modern cosmology, that our magnificent universe is not the result of a cataclysm, but the graceful and inevitable emergence of order from a deeper, more fundamental reality. Yet another philosophical path offers a stark alternative to both materialism and idealism, one that carves reality into two fundamentally different kinds of substance. This is mind-body dualism, most famously championed by the 17th century philosopher René Descartes. In his monumental struggle to find a foundation for certain knowledge, Descartes arrived at a conclusion that would shape Western thought for centuries. The mind, the thinking thing he called the res cogitans, is a completely different entity from the body, the extended thing in space, the res extensa. This radical separation was intended to solve a problem, but it immediately created what is perhaps the most enduring puzzle in all of philosophy. If mind and matter are so different, how on earth do they interact? Descartes' argument began with his famous method of radical doubt. He realized he could doubt the existence of his own body after all. His senses had deceived him before, and he could be dreaming. But he could not doubt that he was thinking. The very act of doubting proved his existence as a thinking thing. From this, he concluded that his essence, his true self, was entirely mental. The body, in contrast, was part of the mechanical, extended world, governed by deterministic physical laws, like a sophisticated clockwork automaton. This created a clean division. The mind is unextended, immaterial, private, and possesses free will. The body is extended, material, public, and operates by cause and effect. For Descartes, you are not your body, you are a mind that has a body. This elegant division, however, ran headlong into the infamous interaction problem. If the mind is immaterial and the body is physical, how does a non-physical thought, like a decision to raise your hand, cause a physical event, like the electrical signals traveling down your nerves to make your muscles contract? Conversely, how does a physical event, like stubbing your toe, cause a non-physical event, like the subjective feeling of pain? Descartes himself struggled with this, famously suggesting that the interaction might occur in the pineal gland, a small structure in the brain, which he believed was the only singular, non-duplicated part of the brain. But this was a physical location which didn't solve the metaphysical problem. How can an immaterial mind push around a physical gland? It's like asking a ghost to move a brick. The interaction seemed to require a magical violation of the conservation of energy, a mysterious leap from one realm of reality to another that physics could not account for. This problem led to various modifications of dualism. Some philosophers, known as occasionalists, proposed that mind and body don't actually interact at all. Instead, when you will your hand to move, God directly intervenes to make it happen, coordinating the mental and physical realms like a divine puppeteer. Others, like Gottfried Leibniz, suggested a theory of pre-established harmony, where God wound up the mental and physical worlds like two perfect clocks at the beginning of time, so that they run in perfect sync without ever actually influencing each other. Your decision to raise your hand and your hand raising are two parallel events that God arranged to coincide. While these solutions preserve the purity of the two substances, they strike most modern thinkers as overly complicated and theological, introducing a deus ex machina to solve a philosophical puzzle. Despite these challenges, dualism has proven incredibly resilient because it resonates with a powerful intuition. Our inner mental life feels profoundly different from the physical world. The qualitative experience of seeing the color blue, the sharpness of a pain, or the warmth of an emotion do not feel like they can be reduced to the firing of neurons. This is the heart of the hard problem of consciousness, and dualism takes it seriously by positing that the feeling is different because it is a different kind of thing. Modern variations of dualism, often called property dualism, soften Descartes' hard substance dualism. Property dualists agree that everything is made of one kind of physical substance, but they argue that this substance has two irreducibly different kinds of properties: physical properties like mass and charge, and mental properties like consciousness and intentionality. Consciousness, in this view, is a fundamental, emergent property of certain complex physical systems, but it is not reducible to the physical properties themselves. This avoids the interaction problem to some degree, as there is only one substance, but it still leaves the question of how the physical gives rise to the mental largely unanswered. The legacy of Cartesian dualism continues to influence contemporary debates in profound ways. It set the stage for the entire mind-body problem as we know it today. The dominant materialist response in neuroscience and much of philosophy is essentially a rejection of Descartes' premise, an attempt to explain how mind can be fully accounted for by the body. Yet, the enduring appeal of dualism highlights the persistent unease with purely physical explanations. It also shapes our language and our ethical frameworks. We speak of my body as if we possess it, implying a separation between the owner and the owned. Our legal systems grapple with questions of free will and responsibility, concepts that are deeply entangled with the idea of a non-physical mind that can make choices independent of deterministic physical chains. Even in the age of brain scans, the ghost of Descartes lingers, reminding us that the chasm between objective neural activity and subjective experience remains the most intimate and stubborn mystery of our existence. While the elegant, extra-dimensional vibrations of string theory capture much of the spotlight, a powerful and radically different competitor has been steadily developing in the quest to unify general relativity with quantum mechanics. This is loop quantum gravity, an approach that dares to ask a shocking question. What if the smooth, continuous fabric of space-time described by Einstein is an illusion, and reality is actually woven from a fabric of tiny, indivisible, one-dimensional loops? In this view, space itself is not a passive stage but a dynamic network of relationships, a cosmic spiderweb of interconnected threads. The central ambition of loop quantum gravity is to be a background-independent theory. This is a profound departure from almost all other physical theories, including string theory. In Newtonian physics and even in quantum field theory, particles move against the fixed, pre-existing backdrop of space and time. Think of it as actors performing on a static stage. Loop quantum gravity argues that this picture is fundamentally flawed when gravity is involved. Einstein taught us that space-time is dynamic. It curves and warps in response to matter and energy. You cannot separate the actors from the stage because the stage itself is one of the actors. Loop quantum gravity takes this idea to its ultimate conclusion. It describes the universe without any reference to a pre-existing geometry. Space and time are not the container, they are the consequence. They emerge from the relationships between the fundamental quantum entities of the theory. These fundamental entities are exactly what the name suggests, loops, but these aren't loops in space. They are the very threads from which space is woven. In loop quantum gravity, the fundamental property of space is its geometry, how areas and volumes are measured. The theory discovers that this geometry is quantized, meaning it comes in discrete, indivisible units, much like the energy levels of an electron in an atom. The area of any surface, for instance, can only take on certain specific values determined by the number of these tiny loops, or more precisely, the spin networks they form that puncture the surface. It's as if space is a digital image and the Planck area is its fundamental pixel size. You can have 1 pixel, 2 pixels, 3 pixels of area, but you can never have 1.5. This granularity is unimaginably fine, trillions of times smaller than an atomic nucleus, which is why our everyday experience of space feels perfectly smooth and continuous. This granular nature of space has a breathtaking consequence. It naturally resolves the problem of singularities that plague general relativity. Singularities, like the infinitely dense point at the center of a black hole or the moment of the Big Bang, are places where the laws of physics break down because quantities like density and curvature become infinite. They are mathematical warning signs that Einstein's theory is incomplete. In loop quantum gravity, however, you cannot cram an infinite amount of curvature into an infinitely small point because there is no such thing as an infinitely small point. Space is granular. There is a smallest possible volume. This means that as matter collapses under its own gravity, it reaches a point of maximum density and then, due to the quantum nature of geometry, it must rebound. This leads to a dramatic reimagining of cosmic history. The Big Bang may not have been the absolute beginning, but rather a big bounce, a moment of immense density where a previous universe contracted to a tiny size and then rebounded into the expansion we see today. Similarly, the heart of a black hole might not be a point of infinite density, but a gateway to another region of spacetime or a new universe entirely. The mathematical language of loop quantum gravity is deeply connected to the geometry of the universe. It uses tools from what is known as gauge theory, similar to the theories that describe the electromagnetic and nuclear forces, but applied to the very geometry of spacetime. The loops themselves represent the fundamental quanta of area, and their intersections define volumes. The dynamics of the theory describe how this spin network evolves in time, with the loops wriggling, splitting, and rejoining, creating a constantly changing tapestry that we experience as the passage of time and the evolution of the cosmos. This is a universe in a state of constant, dynamic becoming, where time is not a parameter but a measure of the change in the relationships between the fundamental building blocks. Despite its profound conceptual beauty, loop quantum gravity faces its own set of significant challenges. One of the most pressing is the recovery of the smooth, classical spacetime of general relativity from the discrete quantum underpinnings. How do we get from a foamy, discrete spin network at the Planck scale to the vast, smooth, and nearly flat spacetime we observe on cosmological scales? This is a major area of active research, and while there has been progress, it remains a formidable hurdle. Furthermore, unlike string theory, loop quantum gravity has not yet naturally incorporated the other fundamental forces of nature, the electromagnetic, weak and strong nuclear forces. It is primarily a theory of quantum gravity, and finding a way to seamlessly include the rest of physics within its framework is a critical goal for its proponents. The debate between loop quantum gravity and string theory is not just a technical disagreement. It represents a fundamental philosophical split in how we approach the problem of quantum gravity. String theory adds extra dimensions and new entities, the strings moving in a background spacetime. Loop quantum gravity takes the world we know, 3 dimensions of space and 1 of time, and quantizes its very geometry with no background required. It is a more conservative approach in its ingredients, but more radical in its reimagining of the nature of space and time. While it may lack the immediate appeal of a theory of everything, its power lies in its direct and compelling solution to the deepest inconsistency in modern physics, offering a vision of a cosmos that is not smooth and continuous, but a vibrant, pulsing network of finite, woven connections. But what if the very idea of truth as a mirror of the world is itself a flawed metaphor? After exploring the outer reaches of physics and consciousness, we must now turn inward to the very language we use to describe reality. This brings us to a foundational theory that shifts the quest for truth from the world itself to the meanings of the words we use to talk about it. This is the semantic theory of truth, a sophisticated philosophical framework developed by logician Alfred Tarski in the 1930s. Tarski was not primarily interested in deep questions about the nature of reality. He was concerned with a logical problem: How can we define truth for a formal language without creating paradoxes that cause the entire system to collapse? The most famous of these paradoxes is the liar paradox. Consider the simple sentence, "This statement is false." If the statement is true, then what it says must be correct, meaning it is false. But if it is false, then its claim to be false is incorrect, meaning it must be true. We are caught in an endless logical loop. Tarski realized that this kind of self-referential paradox arises when a language is allowed to talk about its own truth. His elegant solution was to create a strict separation between the language we are talking about, which he called the object language, and the language we are using to talk about it, which he called the meta-language. Truth, according to Tarski, is not a property that can be coherently defined within a single language. Instead, it is a relationship between a sentence in the object language and the world, but this relationship can only be defined in a richer meta-language. Tarski's famous formulation, known as Convention T, provides a criterion for an adequate definition of truth. For any sentence S in the object language, a definition of truth must imply what he called a T sentence. The classic example is the sentence "snow is white" is true if and only if snow is white. At first glance, this seems trivial, almost comically obvious. But its power lies in its logical structure. The part in quotation marks, "snow is white," is the sentence in the object language. The phrase after "if and only if" is the condition in the world that must be met for that sentence to be true. This avoids paradox because the concept of truth is being applied from outside the language of the sentence itself. The statement, "This statement is false," is problematic because it tries to contain its own truth predicate. Tarski's theory forbids this, restoring logical consistency by insisting that truth is a semantic concept, a concept about the relationship between language and the world, that must be defined in a higher-level language. This approach is often mistakenly lumped together with the correspondence theory of truth, which states that a proposition is true if it corresponds to a fact in the world. While Tarski's theory has a correspondence-like feel, its focus is fundamentally different. Correspondence theory is a metaphysical doctrine about the nature of truth itself. Tarski's semantic theory is a logical and linguistic project. It doesn't make grand claims about what facts are. It simply provides a formal, rigorous way to define what it means for a sentence to be true relative to a given interpretation of the language. The deep implication is that truth is inextricably linked to meaning. You cannot determine if a sentence is true until you know what it means, that is, what objects its words refer to and how those objects are related. This focus on meaning and reference connects Tarski's work to a much broader philosophical current. The semantic theory of truth forces us to consider that our statements about reality are not transparent windows. They are complex symbols whose truth depends on a prior framework of definitions. To say "the cat is on the mat" is true, we must first have a settled understanding of what cat, mat, and on refer to in our world. This shifts the philosophical quest from asking "what is reality" to asking "how does our language hook onto reality?" The truth of our scientific theories, then, might depend less on a perfect mirroring of the world and more on the internal consistency and coherence of the linguistic and logical frameworks we use to describe it. A theory is true within its own semantic system if its statements consistently match up with observations according to the rules of that system. The implications of this view ripple out into our understanding of science and knowledge. If truth is a semantic concept, then a major part of scientific progress is the refinement of our scientific language, ensuring that our terms have precise and unambiguous reference. The shift from Newtonian mechanics to Einstein's relativity wasn't just a change in equations, it was a change in the very meanings of fundamental terms like space, time, and mass. In a sense, the languages of the two theories are so different that they are almost incommensurable. The semantic view suggests that we shouldn't ask which theory is truer in an absolute sense, but rather which theory provides a more powerful and consistent set of T-sentences for describing our observations within its own semantic framework. This doesn't lead to relativism, but it does introduce a layer of linguistic mediation between our minds and the world, suggesting that our grasp of reality is always filtered through the structures of the languages we invent to comprehend it. And finally, we arrive at a principle that takes the cosmic significance of consciousness to its most audacious and speculative extreme. Having explored how our existence might be a product of fine-tuning or a participatory act, we now confront a theory that suggests it is not just an accident but a cosmic imperative. This is the final anthropic principle proposed by physicist Brandon Carter, which ventures beyond mere observation into the realm of cosmic destiny. It states that intelligent life, once it appears in the universe, will never die out. Indeed, it must eventually spread throughout the cosmos and come to shape its ultimate fate. This is no longer a passive filter for our observations, but an active claim about the future, implying that the universe has a built-in tendency, a teleology, that leads inevitably toward the dominion of mind. Carter's own formulation was cautious, but the principle was dramatically extended by others, most notably by the cosmologist John D. Barrow and the astronomer Frank J. Tipler, who wove it into their Omega Point cosmology. In this grand vision, the final anthropic principle is the capstone of a teleological argument for the universe. It suggests that the constants of nature are not just compatible with life. They are fine-tuned to guarantee that life and intelligence will not only arise but will ultimately achieve a form of immortality, becoming an essential and everlasting component of reality itself. The universe, in this view, is not a cold, mechanical system winding down toward heat death, but a stage set for the emergence of a consciousness that will eventually master it completely. To grasp the sheer scale of this claim, consider the challenges intelligent life would face over cosmological timescales. Stars will burn out, galaxies will drift apart, and the universe may head toward a cold, dark, and empty future. The final anthropic principle, however, posits that a sufficiently advanced intelligence would not be a passive victim of these cosmic processes. Instead, it would become an active agent of cosmic engineering. Such a civilization might learn to harness the energy of entire galaxies, reverse the local effects of entropy, or even manipulate the fabric of space-time itself. The ultimate goal would be to ensure its own survival indefinitely, effectively becoming a permanent feature of the cosmos. In this light, the principle is a hypothesis about the ultimate resilience and resourcefulness of intelligence raised to a cosmic law. This idea immediately plunges us into deep philosophical waters concerning teleology, the idea that nature is directed toward an end or a purpose. Modern science largely expelled teleology from its vocabulary centuries ago, explaining phenomena through efficient causes, the push and pull of immediate forces rather than final causes or purposes. The final anthropic principle seems to reintroduce purpose through the back door, suggesting that the entire evolutionary history of the universe, from the Big Bang to the formation of stars and planets, is directed toward the goal of producing and sustaining conscious intelligence. Proponents argue this isn't mystical. It could be a consequence of the universe's fundamental laws, a logical endpoint of complexity and information processing that the cosmos is inherently structured to achieve. Yet, the scientific status of the final anthropic principle is highly controversial, to put it mildly. Most physicists and philosophers regard it as borderline metaphysical speculation rather than a testable scientific hypothesis. The primary criticism is that it makes a claim about the entire future of the universe based on a single data point, our own very recent and fragile existence. It is an enormous extrapolation to assume that because we are here now, we or some other intelligence will necessarily be here trillions of years hence. Critics argue it commits a profound sampling error, confusing what is possible with what is inevitable. Furthermore, it faces the formidable challenge of Fermi's paradox. If intelligence is destined to dominate the cosmos, where is everybody else? The overwhelming silence of the universe could be seen as evidence against the principle's central tenet. Despite these criticisms, the implications of the final anthropic principle are so profound that they force us to confront the biggest questions of all. If the principle were true, it would imbue reality with a meaning and purpose that is absent from a purely mechanical cosmos. Our struggles, our curiosity, our science, and our art would not be fleeting epiphenomena in an indifferent void. They would be the early stirrings of a process that is central to the cosmic story. The universe would become, in a sense, a self-aware and self-perpetuating system, with intelligent life as its nervous system. This transforms our role from accidental tourists to key players in a grand cosmological drama, responsible for shepherding the universe toward a conscious future. Ultimately, the final anthropic principle stands as the most ambitious answer to the question of why the universe is the way it is. It doesn't just say the universe is compatible with us, it says the universe is for us and for intelligence like us in the most profound sense imaginable. It is a theory that blends science, philosophy, and a kind of cosmic hope, suggesting that the light of consciousness, once lit, is meant to burn forever. Whether a scientific prediction or a modern creation myth, it challenges us to consider that the ultimate nature of reality might not be found in its beginning, but in its intended end, a future where mind and cosmos become one. And so, our journey through these 50 glimpses into the abyss draws to a close. We have ventured from the digital dream of the simulation hypothesis to the frozen eternity of the block universe, from the conscious dust of panpsychism to the mathematical tapestry of Tegmark's multiverse. We've seen reality as a holographic projection, a quantum negotiation, a network of conscious agents, and even as a grand cosmic misunderstanding crafted by evolution. The sheer diversity of these visions is not a sign of confusion, but a testament to the boundless creativity of the human mind when confronted with the ultimate question. It reveals that our quest to understand reality is not a single path leading to one answer, but a vast, branching exploration of possibility itself. What becomes undeniably clear is that there is no single, simple truth waiting to be uncovered. Each theory we've explored is a powerful lens, focusing our attention on a different aspect of the mystery. Plato's world of perfect forms highlights the astonishing correspondence between mathematics and the physical world. Kant's transcendental idealism forces us to acknowledge that we are forever trapped within our own perceptual machinery. Quantum mechanics, in all its strange interpretations, suggests that the very act of observation is inextricably woven into the fabric of existence. And modern cosmology, with its multiverses and emergent universes, expands the stage of reality to literally unimaginable scales. These are not competing truths, but complementary perspectives, each illuminating a facet of the diamond, while the brilliant, central light of its true nature remains hidden from view. This leaves us in a state of profound and wondrous uncertainty. The greatest insight from this entire expedition may be the realization that the true nature of reality is fundamentally mysterious and perhaps must remain so for beings like us. We are part of the system we are trying to understand, like a character in a novel trying to find the author. Our tools, logic, mathematics, empirical observation, are magnificent, but they may have inherent limits when applied to the ultimate ground of being. This is not a cause for despair, but for liberation. It means the universe is not a puzzle to be solved, but an endless mystery to be explored, a story that is constantly being rewritten with each new discovery and each new thought. The value of this journey, therefore, lies not in reaching a destination, but in the expansion of our imagination. Contemplating these ideas permanently alters our perception of the everyday world. When you sip your morning coffee, you can now entertain the possibility that the cup, the coffee, and the very hand holding it are a temporary pattern in a cosmic data stream, or a stable consensus reached by trillions of quantum interactions, or a flickering shadow on the wall of a cave you can never leave. This enriched perspective does not diminish reality, it infuses it with a deeper sense of awe and significance. The familiar becomes strange again, and the ordinary becomes a window into the extraordinary. So, as we step back from the edge of this cosmic cliff, we turn the question over to you. This has not been a lecture, but an invitation to a conversation that has been ongoing for millennia. Which of these 50 theories resonates most deeply with your own experience of being alive? Does the participatory universe of John Wheeler feel right, as if your choices are genuinely shaping the story? Does the silent, interconnected wholeness of David Bohm's implicate order match your intuition of a unified cosmos? Or does the simple, sturdy reality of materialism, for all its philosophical challenges, still align most closely with the world as you know it? There are no wrong answers here, only personal landmarks on the map of the great unknown. Share your thoughts in the comments below. Let's continue this most human of all explorations together, forever reaching toward the light of understanding, forever humbled by the beautiful, enduring mystery of it all.